Hi, guys. I think we're about to begin. Come on and join us. Well, welcome everyone. I'm delighted to welcome you to the Institute for Quantum Studies here at Chapman University to our general members meeting. I just wanted to give you a few words of welcome and just orientation before we begin, and then we'll get started. So you have a very nice conference agenda here that you should be have picked up a copy of. If you don't have one, there's one outside. We also have name tags, so if you didn't get one, there's one right outside, so you can.
Do we need?
Grab one.
You don't, Bob.
Unless you know everyone, Bob. But if you don't know everyone, it's nice to have.
Yeah.
So we have all of the talks and the abstracts in the little conference booklet. So just a few words of orientation. So this is indeed an institute hosted event, and so we're happy to welcome people from around the world discussing the latest advances. And just to say a quick thank you, if you have not yet met Sarah and Melina, they're right outside. They're helping to organize this meeting, and they've done a great job in putting everything together. So if you need anything, please take a moment and just go ask them, and they're amazingly helpful and capable. And so please don't hesitate them, or come ask me as well. So you already found us, so that's good. You've passed the first test. So we have our Institute for Quantum Studies is over here. The main campus is just a few blocks, 2 blocks over that way. And so if you have a chance to go over there, check out the main campus as well. And then here we are in our new Institute for Quantum Studies building. So this building we just moved into this past year. So it's really a new facility. And just to orient you to where everything is, we have a little diagram here. So you correctly found we're here at the conference room. We have a little commons area that has espresso, tea, snacks, and most importantly, maybe the restrooms are right there. If you get a chance, you can have a tour of John Howell Optics Lab. And then right over here, we have Armin Guglian and Ibrahim Zagarini's lab in the building next door. So that's a little orientation for our building. And then tonight, so our agenda after the scientific talks is that we will have a dinner tonight at the Culinary Dropout. So we'll just be able to walk together in a group. It's very simple. We'll just walk either this way. It's probably the simplest down Lemon. And then right over here, this is in the main orange circle. So this is so Melina should have sent you a very nice little packet, a welcome packet for you. And then they'll have lots of things to do. So tonight we'll have the dinner at the Culinary Dropout. Tomorrow night, you're on your own for dinner. And I'll get to Wednesday in just a second. So the conference schedule. So we already have. So today so we have our opening remarks. We have a slight change in the schedule, in that here after Ibrahim's talk, Lev Weiman unfortunately could not make it because his flight was canceled from Israel because of the Iranian war. And so we will. I think probably just have a discussion section at this point instead, and then we'll go on. So we have first Ibrahim and Lev. Unfortunately, he can't make it. So Bob Boyd, Taka at lunch here. We'll have a box lunch here, and then we'll continue with our afternoon schedule as well. You can see the names and titles there. For Tuesday, we have a similar kind of arrangement. Again, on Tuesday we'll have lunch here. Tuesday. But on after the schedule, you're on your own for dinner and evening activities. On Wednesday, we'll have a morning schedule. So we have those talks in the morning. We'll end after Marco's talk around noon. We'll have lunch here, and then we'll have our conference outings. We'll go to have some beach time and hiking. I'll tell you about that in a moment. And then a conference dinner at my house. And I'll give you the details just now about it. So the plan is for our workshop outing, we're going to drive to Crystal Cove and have a little beach walk. And so it might be a little bit chilly for swimming, but you're certainly welcome to take your swimsuit and do a little swimming. But I think the plan is just to walk along the beach of Crystal Cove and enjoy the scenery, which I think will be very nice. And then we'll be concluding at 6 o'clock on Wednesday. We will meet in my house. So the address is 2995 Alpine Way. And I'm happy to host you all for a conference dinner at my house in Laguna Beach, California. So it's about maybe 30 minutes drive from Chapman down to Laguna, but well worth the time. Okay, so that's the plan for the next 3 days. Unless there are any questions, we can go ahead and go to the first talk, which I believe is Professor Ibrahim Karimi.
Just getting the it would always easier to connect via Zoom.
Yes, and so we have the little so when you bring your presentation up to connect, we're gonna share by Zoom, and you're gonna mute your speaker, your microphone, and the Zoom code is right here on this little piece of paper. So you just type it in. Look at that. And I'll unshare my screen.
So thank you very much, Andrew, and of course Sarah and Malina for organizing this, and welcome to Chapman, I would say, to our guests. So today I'm going essentially to give a little bit of review of our recent works in my group, and this is a little bit of a little bit of everything. So my apologies for that. It's just only the recent works that my team they have performed. So I'm open. I'm sharing this just to get collaboration. So feedback, maybe new projects. And you will see at the end of the slides, I want to have your photo somewhere in that slide, adding to our gang, the quantum gang. So the first project which I'm going to share with you is optimal diffractive focusing. This idea came from a visit that I had to Ulm back in 2023, when with Wolfgang Schleicher and Maxime, we were discussing about what is happening with an optimal focusing. So how many people are familiar with the Fresnel lens? Oh, okay, almost. Who is not familiar?
They are, they just don't know they are.
So it's one of those beautiful devices, or I would say thoughts that Fresnel came up with, and essentially say that, well, in order to prove that lights they are wave, it came up with this proposal that if you have a wave that is coming over, and if you take such a wave, can you put some mask, which this mask will block some part of the light, and can you use such a mask and focusing in a certain regions? And it's very surprising because by blocking the light, you will be able to focus it. And this is coming as a surprise to people. And essentially, the idea is very simple. If you look at the point that you want to focus it, say that, well, I can go with a different, let's say, different wavelength out of the region. So this is the region that you have one wavelength, and etc. So each, these are half wavelength, half wavelength, half wavelength. And what is happening, you know that after a half wavelength, the amplitude of the beam will shift by a minus sign. So essentially, it will be out of phase. So what is happening, the light that you will get it here is essentially the superposition of all of them, which some of them, I would say each one, they have a negative phase with respect to the other one. So by only blocking the negative phase, you will be able to focus it in a given plane. So you will get a brighter light essentially after that mask. So you can do a little bit of calculation. This from our Bible, Born and Wolf. So you can do a little bit of calculation, and you will see that if you go half wavelength, you will see that you have different zones. So essentially, the odd zones, they are in phase, and even zones, they are in phase, but the even and odds, they are out of phase with respect to each other. So, it's a beautiful mathematical approach, and usually I teach it to undergraduate students. What you will get the minus I power of j plus 1, which is j is the Fresnel zone regions. So essentially, if you take away the odd zones or even zones, you will get a brighter light. You can focus it. So it's a beautiful example. Why this is useful? And this is one of the simulations. You can get such a mask, literally such a mask. Okay, you have to do a proper calculation, take a photograph of that. You shrink it down, you will get black and white. And then when you put it in front of light, you will get a focusing. Okay, so why we do care about this? Because for many cases, we don't have a proper lens. Of course, we are not crazy. You can get a glass, you can start to polish it, and you can curve it, and you can create a lens that you want. But we know very well that in certain regimes, we cannot create lens. For example, in X-rays, good luck, because we are talking about such a short wavelength. Or when we talk about ultraviolets, I mean, Bob and I, we have done a lot of work with Paul Kokum. When you go to 10 nanometer wavelength, good luck to cast such a lens. Or when you go with electron beams or neutron beams. So when you deal with them, either you have to go with electromagnetic lenses, or you can go with the diffractive lenses that you can create them. So it's very important to create such a lens. But there is a big question. Is Fresnel lens the optimal one? Can it give you the maximum intensity at the region? Well, there is no mathematical proof. Let's be mathematician for a while. You have to prove it mathematically. It is the optimal one. So then Wolfgang and I, with Maxime, of course, we had a lot of discussion about that. Assuming in optics or in matter waves, doesn't matter, because partial wave equation is very similar to Schrodinger equation in the free space for free particle. So essentially what you have a pupil functions, and then you let it propagate, and then you will get the wave function after a given time or a given distance. So what is happening that is given by the kernel of a propagator, which can be in a 1 plus 1 dimension, it can be 2 plus 1 dimension, then the intensity here will be given by such an expression. So the question is that, can I maximize this? So I have to solve the Lagrange equations for it. And then you will get to such an eigenvalue problem. And this eigenvalue problem will give you what is the form of the optimal wave function that you can get it. And not surprisingly, this is sine and cosine. Those people, they know Fresnel lens, they know exactly this is the form that appears in the calculation. And what is happening, this optimal intensity is given by the number of zones that you are going to cut and within certain aperture appears for you. Beautiful. So then we try to do the experiment. We did it with, first, we want to find this optimal number of rings based on the number of resolutions that we have it in the laboratory. We check it with a specialized modulator, and finally we create a liquid crystal device that when we shine the light, of course, is a mask, which is essentially take away some part of the light, and then we compare it to several different cases, even compared to the cases that you have only phase lenses. And this is the pattern of the amplitude that you expect. This is a pattern of the intensity. And that is what is happening upon the propagation for n equal to 14 rings that we considered. And that's experimental results. And we got almost very, very good results compared to the theory that we had. And essentially, mathematically, it was proven that the limit that we had it, compared to the Fresnel lens, has an improvement of pi divided by 2 power of 2. This pi always showing up in the calculation is interesting. So essentially, you have a 2.5 factor of the improvement, which is really, really interesting. And that are the different situations that you get it, either for optimal maximum intensities, that's intensity upon propagation, or that's what we have it for phase mask, phase Fresnel mask, amplitude Fresnel mask that you have it, and also finally for the cases of amplitude Fresnel zones that we have for even and odd number. And you will see that these optimal wave function always surpassing the Fresnel zone. Just over the past few weeks, we had a discussion with one of my postdocs. We say, well, does this work also for orbital momentum? If I have an OM beam, can I use the same Fresnel lens and focusing? And he said, well, I doubt about this. And Farid tried to solve the problem. And what he got that essentially the optimal wave function there is a kind of superposition of, let's say, the product of the Bessel functions and also the cosine one, which is very, very interesting. And of course, these lenses depends on the L value, and the optimal focusing also depends on the L value. And these are a few examples for L equal to 1 and L equal to 2. And this is what you expected upon free space propagation. So that's also is very important for the people that you work, for example, in state microscopy, and they are really going with a short wavelength and they cannot resolve the problem easily. And this is a mask that will give you optimal focusings in those kind of scenarios, or when you go with X-rays, or when you go with electron beams. And these are a few other examples. When you go with only amplitude cases, this is what you will get. And again, this is surpassing the Fresnel lens for the case of OM. And with this, I will stop here if there is any question. Yes.
That's very nice work.
Thank you.
Did you consider making a lens waveguide with this kind of?
No, good one. No, we didn't think about the lens wavelet. Yeah, we can discuss about that. And by the way, the last part is not done. I mean, we are setting up the experiment here, and Kerry is taking care of the experiment right now. Yes.
Have you tried to, instead of complete absorption, to shift by the phase from the dark area so that it will be even higher intensity?
Of course, I can do that, but there is no point. Because if I have a control on the phase, I will create a lens. The idea is that in the case of X-rays or neutron beams, I don't have that ability to control the phase. If I can control the phase, then I will shift it to 0 pi, 0 pi, 0 pi, then I'm totally fine. Here, I'm talking about a case which I don't have the ability to introduce this pi jump, then I can only absorb or let that beam to pass through. It's a combination of opaque and transparent regions, and then still I can get the focusing.
So in case of neutrons, there is no way to make wave delay?
Very, very little one. If you have a special coherency, then by diffraction, you will get that. In the case of electrons, also the same situations. I mean, we have done that almost 12 years ago. So when we introduced the phase mask for the electrons, but it's very complicated. But for example, when you go to X-rays, good luck.
Okay.
That's really the motivation behind of this.
I see.
Yeah. So the second topic is QKD. John, you missed it. What I promised you. But
Yeah.
I will give you a private presentation about that. So, the second part is about quantum communications, and at the end I will talk about the few improvements that we had. So, in the QKD, you have Alice and Bob. They have a channel. This channel can be free space, fiber, underwater, any situations that you consider. You have a generation of the state. You have different sources. You have different protocols. You have different degrees of freedom that you use it for QKD. And the other side also, you have detection protocol, detection of those quantum states, and detectors and detection schemes that you have it. And finally, at the end of the day, what we assume that Eve has access to everything in our laboratory. And then we want to share a secret key such a way that no one can get it. Or if one is entrapping, I should know about that. So I think it was last week they got a Turing Prize. So Gilles Brassard and Bennett, they got a Turing Prize. So it's coming to not only to the market, but also it's getting a lot of attention. So I talk about only the part that is related to the structural light, and I will tell you why this is useful. Well, when you talk about light, well, it has many different degrees of freedom. It's a linear momentum. It can have a polarization, which is two-dimensional space. It can have orbital momentum, which is infinite dimension. It can have also radial mode, which also is infinite dimension. This discrete, this two-dimensional space, that's a continuous one. So you can combine all of them and increase the Hilbert space dimensionality as you wish. And why we care about the Hilbert, increasing the Hilbert space? Because essentially in the standard QKD protocol, usually people, they work with 0 and 1s. So they work with bits. But you can, for example, add 2 orbital momentum here, and then you will get 0, 0, 0, 1, 1, 0, 1, 1. So you have 2 bits of information. You can add from -4 to 4, excluding 0, then you have 3 bits of information. And essentially, there is no bound on this. You can go really including the higher alphabet that you wish. Why is it important? Well, if you look at the secret key rates versus the bit error rates, these coming from the standard BB8 protocol, which has been extended to D-dimension, you will see that in the 2-dimensional space, if you have 11% of the error, your channel is not anymore secure. So you don't have a positive key. Of course, you can do QKD, but there is no security proof for it. So if you increase dimensionality to 16, this error tolerance will increase to almost 30%. So essentially, you can go even have in a channel which is extremely noisy, let's say 20% error. Dimension 2, dimension 4 does not work, but dimension 8 and dimension 16, they will work. So if you go up, you get 1 bit of information, and the upper one more than 1.5 bits of information per photons. You can still do QKD in a noisy environment. So we, with Frederick Bochard and Bob, Robert, many years ago, we showed that almost 9 years ago, we showed that, well, this is true, this is practically true. And what we did an optimal quantum cloning machine, which is what I learned in Rome many years ago. And then what we did, we tried to copy the quantum state, but this quantum state, it was not perfect. Of course, it's bounded by uncertainty principle. It's not any more pure state, but it's a mixed state. So we made 2 copies of that. We keep one of them to Eve, and we sent the other one to Bob. And we try to go from 2-dimensional to dimension 7. And we look at the introduced error to the channel. So that was the setup look like. And in reality, is something like that. I don't know if you can see it or not. So you always have to work in dot. So, and the result was, yes, very interesting in the dimension 2, dimension 3 until dimension 7. And this was a universal one. So it was independent of the state that you prepare. So it was a universal quantum cloning machine. In a dimension 2, we had about 84% of the fidelity of the state. So essentially, we had about 17% of the error that was introduced. So which was higher than 11%. So essentially, even an optimal cloning machine could not get the information because it's introducing more error than standard BB84 protocol security line. Dimension 3, you see that the fidelity decreases to 75%. If you go to dimension 7, it goes to 0.6. So going to higher dimensions also allows you to see if someone is attacking your channel much easier than the lower dimension. So, of course, we try to do the process matrix of the system. So we created a system which you had Alice and Bob communicating with each other. So we had 2 different scenarios. One that was, of course, we had the perfect channel apart from the experimental errors. The other one, no. We had a channel which we had the optimal cloning machine attacking to the system. The other one was the most trivial or stupid way of attacking a channel, which was intercept and resend the information. So you get the information, you, of course, randomly get a result, and you created this random result and send it to Bob. And you will see that going to higher dimension reveals them much, much easier. So the process matrix essentially is significantly affected. For intercept resent, which is the most trivial one, you will see the in higher dimension. Essentially, the state is not absolutely look like what you expected. Good. So, but we had one single problem. Always you need a random number generator, true random number generator in the laboratory. So essentially what you do, you create between the 2 mutually unbiased spaces, you switch between them randomly, and then you detect the system also randomly. So you need not a computer that randomly generates those states, but you need something that is truly contextual. And then you will get such a situation. So I was in New York last year at the beginning for this quantum internet meeting. And then I was thinking, well, I can create this EPR state. And this EPR state, you can send it to a beam splitter. The beam splitter acts for you as a true random number generator. So you will get either photons to be transmitted or reflected. And if you send the other state, also the same with the beam splitter on the other side also does exactly the same situation. So you can do the now measurement on XXS or P and PS, or you may be in a wrong basis depending on the action of the beam splitter, which is completely random in that sense. So I did a little bit of calculation and I came up with number of 4,000 modes. And I say that if it's true, then we should able to do QKD with a true random number generator in a dimension of almost 4,000. And that was during a lunch, I would say, or dinner. I think it was during dinner. Again, napkin issues.
What'd you do for dinner?
I don't remember. I remember the physics. So, and at that time, we had one of my students already setting up such an experiment for doing the beam tracking. And I asked him, can you also beams different regions in the position and momentum? And can you look at if we can establish a QKD based on a spatial mode? And essentially, he was able to do that. So he went easily to dimension 361. And this is the quantum DEET error rate that we had in the system. So of course, by increasing the dimensionality, these errors start to increase. This error has nothing to do with the presence of Eve. It's coming really from the experimental apparatus that we have in the laboratory. So it's causing a lot of problem for us. And based on the theory that he had and the Schmidt number of the entangled photons, we should easily go to almost 5,000 here. So they did the experiment and they looked at the different modes, and essentially they were able to send almost close to 5 beats per shifted photon. I think that was a record that we have never seen anyone doing with the special mode. With the time being for sure, but with the special mode was really, really difficult to get to 5 beats after shifting and error corrections. So, and the dimensionality that we had, it was almost close to 361 that gives this, to almost to 100 that gives that optimal situation. And right now we are also trying to do that and expanding to a higher dimension and also improving the binning, because you have to look at these extensions between different modes, and the binning came to be an hexagonal shape. I have no idea why, but this is what came as a surprise to us. And that also for sure will resolve the problem of random number generator in QKD. I think I have another 10 minutes, right, Andrew?
Yes, you do.
Yeah. This part is, I'm talking about how we can compensate for the kind of errors that you go to the free space. And over the past years, we have done a lot of QKD between the different buildings at the University of Ottawa. I think that was the first high dimensional QKD in the free space. Did we go to dimension 4? We did it in a swimming pool. People, they had the roof party and then pool party. And then we did it in a river. So we rent a cottage doing real science. And we went there and we did it in Ottawa River. And finally, we want to do it in a controlled environment, such a way that people they can do QKD with a submarine. And that was in a flume at NRC, which was almost 30 meters of water, and we were able still doing the polarization QKD and the mode QKD. And inside of a fiber, we got a special fiber, which also we can use it for doing the QKD. In all of those scenarios, we had one main problem, was turbulence. Even in water, we had turbulence. What the turbulence was a different regime. So we was much slower and much stronger. And in the free space was much faster, but less stronger. So that is our free space link at University of Ottawa, which hopefully also we'll have one here. We already installed the devices, but we have a little bit of challenges with the safety people. So, and it's about 5.4 kilometers. That distance is sufficient to send light to a satellite, because the density of the air upon propagation will change, okay? So we had centimeters over there, which these centimeters monitors what is happening with the turbulence, and we monitor it for more than a year. and we feed this data of the turbulence, which was a CN square, to a neural network, and we try to predict the turbulence. So why this is important? For example, in March 7th of 2024, this was what happening with the turbulence, and CN square is a factor that you have the turbulence to be strong, weak, or medium. If it's strong, you cannot do anything with it. If it's a medium, weak range, you can still compensate for it. So look at the turbulence that happens. So nothing happens until even 9. And the entire day and night, the turbulence was so strong that we couldn't do anything. I could send students up and still they couldn't do anything. It was just waste of time and energy. However, look at the next day. If I can see. Next day, on March 8th, then the turbulence in that window and another window here is in the range that they can compensate for. So, and we are able now to predict within 9 hours what's happening with turbulence. So we can tell people, hey guys, crew, get ready. We have to go to the roof. We have to do the QKD because we know that the weather is good and we can do the free space QKD within next hours or next 3 hours or 6 hours.
So let me ask a question.
Sure.
So how do you predict it? Do you see when it's going down? It's like, this is like the warning sign that it's about to get good, or?
No, actually, we can tell you in next 6 hours what is the CN square.
And how?
And 9 hours. But we collected the data for almost a year, and we feed it to a neural network. And we gave it to a neural network, and now, right now, I'm measuring the turbulence and the forecast parameters, and I say based on this, I know that next 9 hours what will be the turbulence.
And how good is that?
Oh, within 9 hours, I would say more than 90% accurate. 9 hours. 12 hours, it was 80%, something like that. And gets better and better by training.
Has anyone ever done that before?
No. When we did that, we will receive contacts from NASA and Canadian space agencies, and they asked us to help them. And we say that to them, well, our data, let's say the codes are available right now, you can use it. But if you provide us the data, we can even getting better and, and providing you the information. Right now, we are doing with the quantum satellites in Canada, and we have a network of, I think, 20 people, and we are collecting all of those information, and we are trying to provide it to them. But that is what is happening for our link. So a dream that I had, and I'd say to Andrew, is that having, let's say, about 8 and 9 drones up, and then with these 8 and 9 drones, I can just send light down, and I can measure what is happening with the turbulence at different layers, not only looking at the overall effect. And with this, for one specific location, I can predict it. You don't need drones. You can do it with the balloons. And I was thinking about that, even I wrote a proposal. But you need to be in the regions that you can have a balloons, not here.
Can you just sign a laser up and then look at the scattered down?
Based on knowing the physics, it should be possible, but I have never thought about sending the laser. Because what you don't need really lasers. Laser is too good to do these kind of experiments. You need a bunch of LEDs in coherent sources, and based on the fluctuation of the intensities that you have an aperture, you know what is happening with the turbulence. You measure actually the correlation functions.
There's a simple way to explain why March 8 was so good.
Oh, yeah. Okay, very good point.
The Women's International Day.
So that's actually the data and, the predictions that we had it. So those dots are really, if I'm not mistaken, those dots, they are the real measured one. And the blue one, they are the predicted one. So we predicted within each interval of 9 hours and see what is happening. And we plot it, and you see that really they are in a good match.
And how far in advance are you predicting these?
We look at 12 hours.
Terms right there.
We look at the 12 hours, each of them 12 hours, and then we plot them together. We were monitoring.
So let me just make sure I
Sure.
understand. So you're saying the yellow graph is what you predicted 12 hours ahead, and then this is what you actually observed.
Blue lines are the predicted one, and the yellow, let's say, rectangular, or I don't see very well. Those yellow dots are the actual measurements.
That's pretty stunning, actually.
Yeah.
Because I always think of turbulence as being
Random.
a random process.
Yeah, but look, those are the parameters that we had. Those are the forecast parameters. Relative humidity, that's what I'm fighting for it here to get the solar radiation, temperature, pressure, winds. I have forgotten that. So G sine and cosine of the time, and then C n square. Mainly, it depends on these two and the C n square. These are the real important factors that we have it to predicting the turbulence. And actually, the system gets much better because we have more than a year of data right now. We have almost close to 2 years of data, and it's getting much stronger. And also, we have a better neural network, or let's say an AI system which is predicting. And we call this tarocco. Who knows Italian? Tarot, right? The people that they can read your future. But with not C, but with Q, because it's a quantum channel. Okay, so that's the prediction. So now we can predict what is happening with the turbulence, but can we compensate for? So, and actually, this is an experiment which we were doing at the same time. We had Alice and Bob doing the QKD, and between we had the turbulence cells, which this turbulence cell was a hot plate, and we could increase the temperature there, and we were simulating what is happening with the C n square. At the same time, also, we were able to measure the C n square. So with the wavefront sensor, we were able to measure what is happening with the distortion on the wavefront. So due to the turbulence, so because the beam was displaced, and as soon as you know the displaced, then you know what is happening with the wavefront. And the other side, we had another deformable mirror, which was able to compensate for this effect. The entire this process was extremely fast, that the turbulence within that time window was frozen, and we were able to compensate for. So essentially, we had our QKD channel, and we had a reference beam, which was going through this and only monitoring the turbulence. And then with this system, we were able to compensate for the turbulence so quickly that the turbulence was frozen, and we were established a QKD. And this is the results. Oh, sorry. There's a video, if you can see, this is with the turbulence in the system, and that is with adaptive optics compensated for. And you will see that really the effect of distortions is removed almost. And by the way, that's only the beam quality, because usually they do it with single photon regime, and just barely to get a result for ourselves with the classical light. So previously, when you had no adaptive optic system, that was what you had. The fidelity of the channel was almost 22%. Now we had adaptive optic system, the fidelity increased to 99%. So essentially, we were able to freeze really the turbulence there and compensating for it. And the other side, you will see that, well, we were able to perform the QKD. Previously, we were not able to do in the dimension 2. With adaptive optic system, we were able to go to dimension 10. But as a physicist, we see an anomaly. One of the bases does not work properly. Of course, some people, they say, who cares? Leave it alone. But we are physicists. We care about these sort of anomalies. Why this basis always is not compensated very well? One of the bases is perfect. When you do mutual M-based basis, one of them was OM basis, the other one was a Fourier transform or another basis. And we saw that these, I asked one of the students that, can you look into the situation? Look at the OM. This was what the OM basis is. And when adaptive optics system was off, we had that amount of the crosstalk. And when adaptive optics was on, the amount of the crosstalk was significantly reduced. Okay, so it was able to compensate for. So the improvement was 56%. Okay, of the numbers, yeah. But when you go to any other mutually unbased spaces, is a dimension of, let me see, 1, 2, 3, 4, 5, 6, 7, 8, is a dimension 8. So I'm expecting, Bob help me, 9 mutually unbased spaces, right? And we had another one, yes, yes, because one of them is itself. So it's 9 mutually unbased spaces. And when you try with all of them, the errors, they're almost the same range. Always error is about 19, 18, 15, 17, 17, 18, 19, even after having adaptive optics on. So it seems that adaptive optics system has a preferred basis. And this was very surprising for me. So, and they try to do that and doing the measurement in dimension 2, dimension 3, dimension 4 until dimension 8. And again, they show the same situation. So we contacted the company, we asked them to give us some confidential information about how this adaptive optics system is designed. And it's designed based on the pistons that are on the back and moving around. But these pistons, they have cylindrical symmetry. That's the reason. So, and we were in touch with them how to have a better improvement for this.
So it's just tilt compensation.
And no, it's not a tilt. It's actually, you have 111 actuators, and they are a glass. At the back of these actuators, what you have, this glass, you have 111 actuators, and they are moving like a pistons up and down, okay? And you can control where they should go, and you can control the speed of them, okay? So the speed actually can go to 3 kilohertz. So you can go as high as you wish, essentially. In principle, you can go higher, but you may damage it with such a huge movement. And with neighbors, also you have another problem. You cannot compensate easily. So that's really comes from the nature that these actuators, they are put in cylindrical way. That was the main challenges. Yeah. And I think I have this slide, which is essentially showing what is happening with the QDIT error rate when adaptive optics system is off and when it's on, and comparing how you can compensate for. And you will see always that OM is is much better compensated for with this adaptive optics system, even if you go to angular basis.
Ibrahim, just as a side comment, I suspect that, I mean, we're at infants in terms of figuring out what we can actually compensate for. I'm sure the degree of things we can compensate for is much more than anybody's done so far. So as a general matter, but
Yeah.
I think it's kind of an open area of research.
Yeah, absolutely. Absolutely. So as I say, the quality that you can compensate for is the fidelity of the state, you can bring it back, and also the speed. Don't forget the speed. Speed is really, really important because essentially the turbulence speed is about 300 hertz, if I'm not mistaken, in air. Roughly speaking, is order of 100 hertz or 300 hertz. You should be minimum one order of magnitude higher than that to compensate for. You cannot go really compensating for 300 hertz, just would be 300 hertz or 500 hertz. I think, and even that motivates us to invent a new protocol, and we call it Ottawa protocol, or people they call it Ottawa protocol. We call it the Fourier qubits, or PUB, or partially unbiased basis. So what we knew that, well, we can compensate only in certain bases. Why not only using that sort of basis, let's say setting from n-dimensional, picking up only 2 dimensions and establishing QKD. So this is what we introduced, and we were lucky that a couple of years before with Chabad, we had a security proof for them, and essentially we were able to introduce this new protocol, and this is the scheme for the people. They know, if they look at the projection matrices, they see that if you go to this 2-dimensional space, that's what you expected, or to this 2-dimensional space, and etc. So essentially it's n-dimensional, but you pick up a qubit in each of those subspaces. And still you can get a key rate which is better than the higher dimension, which is very surprising. So I will stop. Maybe next week I will talk about the programmable quantum simulator. Yeah.
We have time for one question before we have to go to the next talk. Yes.
So there are now these fast phase modulators that work at 10 kilohertz?
Adi, you are right, because right now they are doing that. So they are creating these, sorry to interrupt, to stop you. They are using this scheme to create high rate OM generators.
But you can also do it for compensation, right? At 10 kilohertz, I think.
Compensation, you should really have a full control on waveforms. You should have really the full control on the wavefront.
A phase modulator.
Which phase modulators?
Okay, there is DMD, right? But
Yes.
this is amplitude. Now there is it's called PLM, but it's also, I think it's also made by Texas Instruments. So it's
PLM,
phase light modulator. Yeah.
phase light modulator.
It works at 10 kilohertz. Instead of
What is the technology behind?
So I think it's still MEMS, but it's kind of mirrors that move back and forth.
Oh, yes, I know about that technology. Fraunhofer, they were the first team that they created these MEMS, essentially. I contacted them many years ago when I was Bob's postdoc. They say that they can provide the MEMS by itself, and it was cost $100,000 at that time, excluding electronics. They say that the main problem is the electronic feeding that system so quickly. So it's really, really big challenge because we have to really go with the computer language. Everything was written in C because you have to really have no interfaces. You have to be able to communicate with them. Yes, MEMS, I know. I don't know if there is any other companies right now producing them.
So there is some progress in this field.
Okay.
Maybe we can talk about it.
Absolutely. Yeah.
Okay, let's thank Ibrahim again. Okay, so I'm really happy to say that I asked Lev if he would be so kind to zoom in from Israel and give his talk remotely, which I think because of the extraordinary circumstances is completely justified. And he was a champion and said, yes, Andrew, I'll do it at the last minute. And so I'm very happy to introduce Lev Weidman, who will give us the next talk.
Thank you, Andrew. It was little unexpected. I thought that if I'm not there, then it's difficult. And I hope there will be no sirens. I will have to think what to do. In fact, I think we had like several hours without siren now. So maybe there's a chance. Okay, so let me start. I hope it will work. Let me see. Do you see it? Do you hear me? Everything is fine?
Everything is fine.
Okay. So I'm really happy to be at least on remote in this beautiful building. You are there inside. And so I want to discuss issues which I was working with some of the people who are there and who are working for a while. So I believe that if I don't follow the advice of Bohr, don't ask where is the particle between clicks, I get something new. And so let's see what I want to cover. You see, interaction-free measurement, this is maybe what allowed me to be in academy. I think it's also happened because of this. So, although I was starting to think about where was a particle between clicks later, but maybe subconsciously it helped me even before. The second issue is counterfactual communication. There is a big noise about the option of telling something to somebody else by using some channel, but without putting any particle within the channel. Now, I think what I start with my PhD with Yakir Aronov is weak measurement, which led finally to practical application with all kinds of precision measurements. So it's also because I want to consider particle which is pre and post selected between two measurements. Finally, there is some recent thing which indirectly sorry, just, Mikhail, can you, well, okay, you have to be silent. Sorry. This is related to this, not directly, but maybe somewhat indirectly, but without thinking about weak measurement, I think I would never come to this idea about enhanced eavesdropping. And so let me just tell you what is this enhanced eavesdropping. I'm really far away, but let's say I have a spy near you, and the spy wants to know what's happening inside the building. So he put a laser beam on the window, and when you're talking, this window vibrates, and so the reflection is vibrating. And I put here some detector which is sensitive to motion of this laser when it go up or down. And so I'm trying to understand what is happening inside. I don't know if it's so this is kind of a message which happened inside. I'm not sure you hear it. Do you hear anything?
No.
This is some more signal. I don't know if now I didn't. So I hear it very clearly, and you were supposed to hear it clearly. However, when I put this device on, then what probably I will hear, it's kind of a noise because it's difficult engineering problem to get the sound from this vibration, although it's somehow there. So the idea of this enhanced eavesdropping is that making a small modification when I send my laser and when I receive my laser, I can reduce noise very significantly. What I'll have to do, I have to put a Mach-Zehnder interferometer when I send it in, and not just Mach-Zehnder interferometer, it should be Mach-Zehnder interferometer with a DAF prism inside. I will put a bright port out, then it will go out, and here we'll have essentially the same system. Mach-Zehnder interferometer, well tuned. So in fact, the dark port, it will go out. But in the dark port, I will have a reasonable signal. It will be not very dark. And this motion of this line and this signal will be significantly enhanced. And I don't know, again, if you hear it. Here I can hear. Now there is a noise, but also there is a signal. And in fact, this is kind of a real thing which we did in laboratory, and not with a window, of course, but with some mirror inside our laboratory. Okay, so this is where I want to go. But let me start the story. So, where was the particle? In this kind of situation, it's hardly interferometer. I have a laser, I send a photon, I put a mirror, and I put a detector, and I get a click. I like single photon sources, single photon detectors. Now, even it's a quantum particle, I think there is no much controversy here. It's pretty clear that the only way and the only path of the particle is just go from here, here, and then come here. There is no much question about this. So this is probably the trajectory. I think everyone will agree that this is where was the particle. Now, this is a Mach-Zehnder interferometer, and it is tuned Mach-Zehnder interferometer. If I make it dark, I arrange it that this is a dark output. Essentially, everything's supposed to go here. Here, it's really kind of $1 million question. Which the particle was on two paths, or it was in one path, or in this path, or maybe it still was in two paths. I prefer to say that it was moving in two paths together. So, but there is no clear question about this. I continue to discuss with Yakir, and he said that no, it must have to go through one pass. And I never get, unfortunately, all my experiments and all these ideas really don't tell us what is a true story. If it's two pass or one pass, it's still compatible. Everyone can believe in every story. I will try to persuade you that it's to think that it goes through two paths. Now, let's look on this system. So it's the same Mach-Zehnder interferometer, but I take this beam splitter out. What Wheeler did it during the flight of the photon, what he called delayed choice experiment. But I don't make a delayed choice. I just make a choice. I have it without the second beam splitter. So I set photon, and I get a click. Again, all what I'm always asking about something pre and post selected. So I know I have this single photon source. I know it clicked, so it sent a photon. And I already consider photons which were detected in this place. Sometimes the photon detected in another place. You know me, that I believe in parallel world it was in another place. But I look about this world where it was detected by this detector. So I think here this is pretty similar to the case which is kind of obvious. And there is maybe a standard approach in quantum mechanics. In quantum mechanics, we say we know where is the particle after we have seen. And if I will try to test it in non-demolition measurement, and today Rampy and MPQ doing this kind of thing. He can test the photon flying and let it go. So non-demolition detector of the photon in flight. So if I'll put this kind of rampant detector here, for example, there is this detector here. When I send the photon and click here, I know I will not find it. It cannot be, because if I'll find it here, I would never come, it will never reach this place. However, if I will put it here, I know the rampant detector must click with probability 1, because otherwise, it cannot, if it will not click here, it cannot come again here, so it must click. So the standard approach, I think, will tell us this simple story. In this case, since there is no any other way, this should be the trajectory. This is what Wheeler suggested. If there is only one possible trajectory for a photon, then this is the trajectory the photon took. So, so this is what really Wheeler says. We know the photon was, where the photon was if there is only one possible path. There is also David Bohm. For me, it's important. He was advisor of Yakir, and also he essentially maybe provided a good theory in which it's unambiguous where the photon was. He said there is a quantum wave, but really every particle, in fact, not photons, but let's not talk about this. Every particle has definite trajectory. And so one can calculate Bohmian theory, and Bohmian theory tells us something pretty strange. According to Bohm, it wasn't in this natural trajectory, but it was in this trajectory. It invariably, when it's 50-50 interferometer, then what will happen every time, if it's come from this side, the empty wave from here will catch it. If it would come from this side, the empty wave from the top will catch it. So if we got it here, and the Bohm says we cannot find a photon if it's not there. So if we found it there, so the photon arrived here, the Bohmian photon had to make this kind of strange trajectory. But I'm not a Bohmian, and I don't know if there are any Bohmian in the room, which in Chapman now. So okay, maybe clearly there are people who believe in a standard von Neumann approach. And the standard von Neumann approach says that where is the wave? This is where is the photon. So when we send a photon, it's go here, it's everywhere, even here, until it collapses here. So according to Van Neumann, it's everywhere in all these places until it collapses. So, and again, Bohr said, don't ask where was a photon between measurements. Maybe he foresees that there's kind of provocative question with unclear answer. So, 2013, in fact, it was like maybe 3 years before, but it took me a long time to publish all these things. I suggested another definition or criteria. I said, we start with a photon, then we detect it, and then we ask theoretically or in the end practically where it left a trace. And this is a definition of the past of the photon. The photon was where it left a trace. Now, for me, and there are local interactions, they never zero, so it's leave a trace all over the path. But we'll have to see which it lives here. But there is a one clear case where everyone have to agree. If there is a mirror and photon bounces a mirror, then it changes the quantum state of the mirror. So this mirror, in fact, will be kicked. Again, it will be kicked by a small amount, not so small amount, a finite amount, the momentum of the photon. And this one will not be kicked. It still may be much less than the uncertainty, so we cannot really, after later ask the mirror where it was. We can repeat many experiments like this and then ask the mirror, and we'll see that this mirror will change its momentum, average momentum. And this mirror, given if we'll only consider cases where we get this post-selection here, this one will remain as before. So from this point of view, the photon again took this natural trajectory, Wheeler degrees, and standard ideas that we can find it here. Everything is kind of very natural. Now let's come back to Mach-Zehnder interferometer. According to Mach-Zehnder interferometer, now I have a tool. I can tell where was the photon. Again, it doesn't, maybe I can tell because I have a definition. According to my definition, where it left a trace. And I know if I make quantum calculation, I know that the expectation value, the quantum state of this mirror changed, quantum state of this mirror changed. They all got this momentum. It will be half momentum of the photon, but it will be something non-zero. Both this change the state, both mirror change. There is a trace on both mirrors. So I will say that the photon was in both places. Okay, this is kind of a strange story, which makes sense. Essentially, only if not only, but I think, again, being in two places, it's really strange. And to understand it well, it's two-state vector formalism, which Yakir taught me a long time ago when I started the PhD, and he started it even before in 1964. And I don't think in Chapman I have to tell what it is, but so I spend just maybe a few seconds. We have a wave function starting from the pre-selection, and this is not enough to describe the system in between the measurement. The second measurement, detection at T2, tell us equal amount of information about where the photon in between. So really the two-state vector give us the information about where is the photon. And the weak trace, this is a simple theorem which can be easily proved. The weak trace appears in the overlap of the forward and backward evolving wave function. So here, this is a forward evolving. This is, I hope you see it, depending on the projector. And this is a backward evolving wave function. And in overlap, this is where there is a trace. So this is where is a trace. So this is maybe another definition, but I prefer the physical operational definition. My definition, the photon was where it left a trace. It's essentially an alternative. This is where there's an overlap of the forward and backward evolving wave function. Okay, so let's go to this other case when I take this beam splitter out. And again, this is a backward evolving wave function. The forward is the same, essentially. And this is, and so now we know where was the particle. But you remember I said that about 2010, maybe when I had this idea and started working on it theoretically, but I couldn't publish it. So to publish it, I finally had to make an experiment and ask photons. The experiments really told me, because I couldn't persuade these ideas, at least the referees of different journals. And then in fact, I made an experiment in Tel Aviv with Shimshon Barad and the students, and we asked photons where they have been. And this is the way how we ask photons. And again, the way to ask photons, we gave photons some information in one place, and then looked on these post-selected photons if they know this. The information was the frequency of the wiggling of this mirror, and when this mirror is wiggling, we have this beam going up and down. So we have a signal which is intensity up minus intensity down, and it had frequency of this mirror. And we have seen this in our spectrum analyzer. And the photons have been in C. Photons told us this. Photons told us in this simple experiment they've been in this. Very natural. Now I also have this experiment, and now I put two mirrors wiggling with different frequencies. This was frequency B, and also was frequency it's lower here of frequency A, and we didn't get anything here. The power spectrum, so although there were photons, but these photons didn't come here. In parallel worlds, it was maybe in A, but in our world, in which we could consider only photons, here, there of course we get only frequency B. Now, in Mach-Zehnder interferometer, tuned Mach-Zehnder interferometer, we get two bumps because unfortunately now I cannot ask the question. It looks like I answer the question. The photons were both here and here. This is what I want to say. This is what I like. However, to get this picture, we use like 10 to the 13 photons. And if half of them will be here and half of them will be here, we would get exactly the same picture. So I really don't know if they both here or everyone was both here and here, but at least this is the picture we got. And so at least I want to believe that the photons was both here and here, and at least this my picture tells me this. Now, when I got this idea about asking photons, let's see what it can tell us about interaction-free measurement. They were discovered before this works, but let's see how it fits together. So, interaction-free measurement, we have this tuned interferometer. This time it's tuned that here it's destructive interference. It cannot come to the right detector. It's all go down. However, if something disturbs it, for example, this super bomb which explode on a single photon, then we shouldn't see interference. So really, if the quantum state, half of the wave kind of go here to the bomb, and half of the wave go here, and a quarter goes to the detector. So if we are lucky, we can get a click here. When we get a click here, we know that there is no bomb. We know that there is a bomb here, because if there is no bomb, we cannot get a click here. We also know that the photon was not here because it cannot be in two places simultaneously, or at least cannot be detected simultaneously. I believe it can be two simultaneously, but definitely it cannot be detected simultaneously. So the photon tell us there is a bomb in A, and it also tell me that I was not here. The photon tells I was not there, but I know that the bomb was there. So this is interaction-free measurement, finding about presence of an object without being there, without touching it. And this is where was the photon. If you look later, you will see that the trace is only here. Only in this area there will be, I have not been A. You see, there is no any kick of this mirror. If you repeat many times, you'll see no momentum was given to this mirror, but there was a momentum given to this mirror. If we will use my method, we will see this wiggling and not this wiggling, that this frequency will not show here. So we have all reasons. The photon really tell us that it was here. This is photons tell us that they were only in B. And my definition, it was in B, all definition that the photons was not in A, but still we get information about it. Now, in fact, this interaction-free measurement is kind of counterfactual communication because I can consider placing it as a bit 1. So when I place it here, it's a bit 1. Now I'm really on this side. Alice in the bottom and in the left. Here is Bob. So Bob put a bomb or shutter. It doesn't have to be a bomb. And now Alice will get a click. So Alice knows that the Bob sent 1. And this is really interaction. Oops. This is really interaction free. Oops. Something was not. Sorry. Okay. This is interaction free because the photon was not there, but I know that it. But we get bit 1. The problem is it doesn't work for bit 0. Not putting a shutter, we get this situation. Without a shutter, we get this tuned Mach-Zehnder interferometer. We already realized that in tuned Mach-Zehnder interferometer, there are signals from here. The mirror is kicked. So there is a trace here. So from all points of view, the photon was in A. It was also in B, but it was in A. We cannot say it was not in A. So it's not counterfactual communication. So essentially, there is no counterfactual communication. So there are many papers I was fighting, these people who were trying to say that there is a counterfactual communication. We cannot tell that there is no bomb with A without being in A. Okay. Now, in fact, we have this. There is another reason why it's not counterfactual communication, because this Mach-Zehnder interferometer can tell us with certainty that the bomb is there. It cannot tell us with certainty that the bomb is not there. The way to make counterfactual communication, which will tell us that the photon is there, it's more complicated interferometer. It must include a device which tells us that the particle is not here without being here. And what can achieve this is this nested interferometer with a special tuning. What is this tuning? When we block this arm, then there is, of course, this interferometer has a leakage here and has leakage here. And here there is a big interferometer, and we can arrange that when this is blocked, then this is destructive interference. So it cannot click when there is something here. So, however, when it's not blocked, then this one is tuned outside, so nothing goes here. But of course, when nothing goes here, this can click because it's just a beam splitter and there is a beam from the left, so it can click. So when there is a click, we know that this place in A is empty, because if A is not empty, when it's blocked, it cannot click. So the photon, I can tell that there is no bomb in A. And I could not have been an A. Also, photon can tell that it could be an A, because if it would be an A, it would be inside this interferometer, then it's go out. However, this is this counterfactual communication for this idea was by Kwiat and Hostam. And when they found it, I was really kind of upset. I thought that they found a mistake, because I was pretty sure it's impossible. But it seems it's possible because it looks very robust. When I get a click, I know it's empty because I couldn't get a click without empty. And it looks like also I couldn't be here because I would be here, I wouldn't be here, I cannot get a click. But after 2 months, I realized that it is not true that the photon was not in A. Why I can claim that it was in A? Because there is really no difference between A and C. If I look quantum mechanically, pre-selection, post-selection, and A and C, it's exactly the same story. But mainly I have my definition. It's not in A if it left no trace in A. But my calculation really say no. And it was an A because there is a trace. If I look on this mirror, it changed its quantum state exactly in the same way like it changed this one. This one also changed on the same strength, but kind of strangely going toward it. So here it was kicked out, here it was kicked out the same way. So really the photon was there. So this is why I say the photon, if I look on this mirror, if I calculate it, even in fact I measure, it was not there. So this is why many people was very, I don't know, some surprised and some really don't believe until this moment that the photon was here without coming there, because no here, but it was kind of here. Anyway, I'm pretty sure that this trace tells me that the photon was here. And so this, another reason, I just make my preset forward and backward evolving wave function. This is a backward evolving wave function. It's inside interferometer and forward inside. Not here, not here. Not here, backward, here, forward, but not overlap. Overlap only here and on this normal side. So I really cannot say that it was not here. So, and the photons told me until we got this picture, until photons showed we're wiggling all these mirrors, until photon told us that there is a wiggling here, it's of the same size, the same signal like wiggling here, the same wiggling here and here, and the same signal here and here. And no signal from here and no signal from here. Okay. So this told us that there is no counterfactual communication. No counterfactual communication. Now to go to next story, I have to go beyond the idea of kind of the classical idea. According to classical idea, I can be or not to be. Quantum mechanically, I can be a lot, I can be less, I can be maybe negatively or imaginary. The weak value of local projection operator, this is what's the description of a presence of a particle. This is kind of new definition of presence. I want to define presence, I said, according to the trace, and the trace directly related to this weak value of projection. For example, in this example, there will be weak value. Weak value here is 1. Here it's -1, but -1 is still presence, negative presence. This is explained why it's pulled and not kicked out. And weak value presence here, it's also 1. This tells that the trace here and the trace here, it's exactly the same. But again, why there is 1, there is 0, -1, it's the same strength, maybe opposite. But it may be also different number, or maybe mentioning here, it's 0. So this is why I say that it was not here. So this weak value of projection tell us when it's a good works for all examples which I showed before. The photon was in A and in C with presence 1, in B with presence -1. Maybe look on other example which I discussed. In this discuss, I said it was not here, but it was here. And yes, weak value here is 0. There is no wave. The post-selected one doesn't come from here, the backward evolving wave function. And the photon was in B, only in B with presence 1, in A with presence 0. All signal scissors and all my definitions. And now we use this formal definition, weak value of the projection. And Mach-Zehnder interferometer. You remember I got this half trace. If I calculate the weak value of projection operator, I'll get half. I will also get half here. So also this, but this is kind of unusual, half presence. Classical particle cannot have half presence. Is it there or not? I claim that here my photon is kind of both here and here. Here is half and here is half. Now, more interesting is when I take the same Mach-Zehnder interferometer, but here you see it was tuned. Nothing come out here, and 100% come here, and I look on the pre- and post-selected photons, which come here, and I found it in a bright detector here. If I will look again on Mach-Zehnder interferometer, but I will arrange that this port is dark, not completely dark, but most of light will go here. And here I will give only small amplitude. Then, when I'll calculate my weak values of presence in A and B, I will get interesting results. I can get here, in principle, 100. It depends. If there is a very small amplitude here, when this scalar product is very small, I can arrange whatever I want. Experimentally, 100 is difficult, but in the first experiment, the people do maybe 80. People do this kind of in this kind of experiment, maybe with Sagnac, which is more stable, well, we can arrange a large number. So here it's theoretically I can theoretically have 100 here. In the moment, the weak value 100 in A, it must be first. It corresponds to it's really 100. The mirror will be kicked 100 times stronger, still very weakly, but 100 times stronger in relative to the real one photon which I go here.
Lev, just let you know you have about 5 minutes left, okay?
5 minutes left. Okay. So to see impossible. We'll see. So here it's 100. Here it might be minus 99, and because the sum should be 1. But we'll get what will happen. Everything we shall do here will be amplified. If I look on my experiment, instead of this signal, now the signal will be very big. It doesn't see if it's plus or minus, so it will be very big signal here. And this leads to precision measurement, because now I'm much more sensitive to this angle. And this led, again, this was before 2010 or 2013. Andrew and John made this beautiful experiment that uses and gets some big amplification, huge amplification using this weak value of essentially this theoretical idea. Now here, and then Andrew came with other things which led me to this talk, because he somehow realized that my picture here will be spoiled if I will put a dove prism here. I don't have to hide the picture here, and I don't have the time. The Dove prism changes this picture. This is what Andrew found with Alonso, and it changed it. Suddenly appears the signal from here, which according to my logic, it should be, because there is no overlap of the forward and backward wave function here. But still, there is a big signal. So, how to explain this big signal? And maybe to use it. Instead of this experiment, let's put photon just from here, because some miracles happened in this Dove prism interferometer. So let's move our source here. If we move our source here, we'll see a big signal here, as should be, because it's 100. A big signal here, it's minus 99. Here, the weak value, the presence is just 1, but we see a very big signal here. Here it's 1, and this is a signal which should see according to the presence. But we see a very big signal. So what exactly happening here? The photons are lying about anomalous presence. Because I believe their presence had 1, but they show me a big signal. How it happened? Because the shift here give us the same as shift here. This shift also translated to the shift here. Here there is amplification, here there is amplification. If there is no Dove prism, one is 100, another is minus 99, I add 2 of them, I get 1, so it's not amplified. But if the prism changes the sign, this is what the prism does. It's kind of flips. So I had 100 minus 99, so I'll get 199. This is why the signal from here it's so bigger. And this is the experiment which I started thinking about a long time ago, discussed with John. It didn't work in Jerusalem, but finally it worked in Munich. And this is what we got. And we got this amplification. It's more proof of principle, because this is a signal without amplification, and this is a signal with amplification. Still, the factor is 9, but maybe not so bad. And here it was a weak value about 5 minus 4, and 5 minus 4 will got us 9. And this is the people involved in this experiment. Harold is a leader, the boss of the experiment, of the laboratory. Carlota was the main leader in the experiment. Gregory helped me. Jan, without Jan, Jan was very important for all the thing, and Florian helped. And and this is exactly this, maybe now it's just amplification. Also, the Jerome experiment, you see, this is theory, this is weak value, and this is what we got. So this is how well it worked. And maybe just one more thing. You remember I showed the 2 things. The dark port was amplified. The bright port was cleaned. All these disturbances, they went to a dark port, so we can get signal. But the bright port was very clean. So when you send a laser and you use this and you use bright port will be stabilized. And this is how we see stabilization. This is our shift, and this is how it was stabilized in position and in the direction. So then we can send now with our system the signal. And the signal, you see, it was done still in last year. So the signal which we used is, now you can see in the top of the, this is the cipher of this Morse signal. You can see it. Thank you.
Thank you, Lev. We have time for questions. Please.
So I have a question. Since you have different frequencies you operate, what about I mean, in principle, they become distinguishable. So interferometer, there's like a partial coherence with interferometer.
So the frequency is the frequency of the wiggling of the mirror. Now, the wiggling of the mirror doesn't really it's not supposed to change the length. It's on a second order. It change second order effect. It's change. It's a make leakage, and in fact, there is no miracles. Like before, I said that I get signals from the particle where it was not present. There is a small leakage which also interfere with the big signal, and then I can reconstruct it. But now what I really tell, it's about practical amplification. So I really get your question about conceptual. This is how I get the practical amplification from precision measurement. And from this frequency, it's not. I don't believe in miracles, so I cannot get signal. I don't. This is my second part. No counterfactual communication. I cannot get information from the place where I have not been. So then there is a tiny leakage which goes from there.
Okay, other questions? All right, let's thank Lev again.
Thank you. Thank you, Andrew, and thank you all for allowing me to.
Very well. Okay, so we have our coffee break now.
When do we come back?
We come back at 10:40, so we have.
Quick coffee.
Quick, 10 minutes, yeah. Supposed to be long.
Of course, that was a rhetorical question.
Yeah.
I knew the
We'll come back when
answer.
we come back.
No, I knew the answer. I wanted you to say it very loud so that people knew when to come back.
I'll ring the bell.
Have you moved your whole lab or no?
Oh, well, I never did.
You left the old, that's right, you left
I,
the old lab.
I had a full working lab in Rochester. And I set up a brand new lab. And it's still there. And that will remain there. Without me. And that's okay. In some ways you ask, what can a professor do for the world? And the answer is you go to a third world country and you set up a laboratory there.
Yeah, first grade.
Third world country here being Canada, yeah.
Right. Is that a third? Is that?
Yeah, so the laboratory will be there. I think the university right now is trying to figure out what to do with it.
Yeah.
Because then they get to do playing space.
Oh, for something else. It's-
You know, for something else.
Is it really more than?
Yes,
yeah.
Oh, yeah. Otherwise, they would have done everything to keep you.
The people who wanted, the people who hired you, that's it.
Well, what happened?
Presidents, university presidents have limited.
You're gonna have to be the one.
Well, I mean, this doesn't bother. I think. Because I saw you, now I didn't see it, but I knew that you said.
We have our. Right out. And so. As I want to do, I want to understand it. And I don't want to.
Everything that's translated tributes to. Understanding, but how about stress?
I was okay.
Okay, so that's a mild stress.
Yeah, stressed enough to do something, but not enough to say. Yeah. So it's okay. I just, I had so much in my brain that I was worried about going to class and then getting lost and then brain was so working.
If you didn't start working on it. I was about to. I went kind of lost. It's the first time I was at on age. That problem was that when you change plans. There was a first sentence saying, as a frequency. It's basically. I actually in the end, so it's all in check. We started assuming that they frequency. Up or down or getting out of the vote, it's enough. You don't need to fly.
It's I got something. I've been thinking about it, I got like.
It's a little bit tricky, but it's not. Well, I think. So, you're.
I have, like a general.
Oh, okay, so you don't have any stress in terms of your variables.
I do.
Okay, well, I don't do a lot.
I just need to like check.
We can solve that.
I was trying to find. Today.
You can solve that. You say you have general expression difficulty.
In terms of
Yes.
the velocity at any point.
Depending on the position.
And the.
Okay, so that is.
The Y. So, like using.
Yeah.
You like it?
What else needs to be, they're not really that. No. Confused, I'm confused, no. If you have the velocity as a function of that position, then yes, that's not.
Yeah, he's very fine. Yeah, that's right.
Yeah, that's the
Oh, okay, I didn't know.
Okay, that's why I didn't,
Emails, right?
yeah, I don't read much as long about like this.
说一下，你每个学期130可以，因为跟没关系。我们还可以去那个证明。Oh yeah, yeah. 我的意思是你们这都是必交的吗？买四个。 如果你不用的话，因为不是跟 insurance 有关的，不一定要去门诊看上面。我去那里也知道。门诊他是调查贴片啊，什么摆，差不多是。因为这是 insurance 它是这个属于人身的。因为我去了，他有，但是他说我100。Now there's always favorites.
Yes, yes, yes.
Coffee now, fresh coffee.
Walking in our bro.
Yeah. 后过来的，也不带死药。
It's a gay.
要高，因为我刚刚干掉那个我自己的例子。
There are two ways of
I'm
looking.
sure I don't miss this.
There are two ways of looking at this.
Are you all set up?
I was.
So it should work fine.
Would you recommend? Yeah, so this is what I was trying to look.
I said that I wanted Andrew to announce publicly that he expected people to work at 10:40. I knew I was the speaker.
You had an ulterior
So I
motive.
guess he and I were the only people in the room who knew what I was talking about.
It doesn't have a nice schedule.
He's very bad bagels.
Yeah, you're able to come back if you go very important, like, okay. Oh, sure, but. Okay, it's Wednesday. Yes, I know, but it's already being recorded, yes?
So we do have coffee now, you guys saw that?
Maybe sure. I'll ask you, but I'll make sure it's recorded. How you guys been? Really,
It's fine. How you finish your vacation? Vacation, you said you had vacation.
Oh, no, it's in the middle.
In the middle of it? Why can't you
Oh, no, no, so sweet, I wouldn't dare.
continue what you were doing?
I know that was my son. It's supposed to.
Okay.
My friend Robert.
Same way, but pronounced differently, so.
Yeah, yes, I'm great. Lots of money.
Last year, we were.
Okay.
Now we have a new.
Screen. Hey, Bob. Good to see you.
Good to see you.
Hey.
Glad to have you with us.
Ready? So I'll call everyone in.
Yeah.
Oh, yes, be so.
It's so good to see you.
It's like your smile. I missed that. I was, yes.
Okay, everyone, let's come back to order. So I'm happy to introduce our next speaker, Professor Robert Boyd from the University of Rochester. Happy to have you here, Bob. I'll turn the time over to you.
Okay, thank you. And thank you for the very short introduction. Thank you for inviting me here, which is the whole point, I guess. So the title of my talk is Research in Quantum Photonics. That sounds so generic that you might think that I just made that up on the spur of the moment. But actually, I spent a long time thinking about it, and that's really what I meant, because here's the subtitle. This talk, I highlight some of the major themes that have motivated research in this topical area. That's what we say in public. I meant has motivated my research in this topical area. So I'm going to give an overview of what I think has been exciting in quantum photonics, going back a few decades. And many examples will be from my own work, but certainly not all of them. Now, I have a funny story, and I was limited time, but I can't help myself. So, I love Chapman University, but you do things a little bit differently here. So the invitation for me to come here, I mean, not the verbal invitation, but the written invitation is from one of your vice presidents, I think. And it's more like a legal contract. And if you read the fine print, which you should always do, but which they probably don't want you to always do, it says, I'm obligated to give a 60-minute presentation. Wasn't clear to me whether this was a bi-directional commitment.
Yeah.
But I'll try to keep it.
It's
I'll
okay.
try to keep it noticeably shorter than 60 minutes.
No, Bob, in the after you, that's what I will give the talk. It's after my view on.
Okay, so let's get started. Why did you screen that? Okay, so I said this already. So I'm going to talk about some of my research, former and present. And when I say quantum optics, I mean this in the loose sense, not the strict sense. In the US, always in a physics department would be the quantum optics group. And the quantum optics group would contain all the laser physicists, the people who did nonlinear optics, and Rabi splittings, and self-induced transparency. Now, today, that's not quantum, but okay, so but there's the tradition of using quantum optics in this broader sense, and that's what I'm doing today. So I know what I know what I mean, and you can be unhappy. Okay, so one of the things I was very intrigued by is controlling the velocity of light. And we used to talk about slow light, fast light, and backwards light. Here we're talking about the group velocity, and light can be made to go slow, meaning that the group velocity is much less than the speed of light in vacuum. Fast, that the group velocity is bigger than the speed of light in vacuum. This makes some people really, really worried, which makes them even more unhappy when I say, well, I did the experiment. And it can go backwards, meaning that the group velocity can become negative. Backwards. Every journal editor removes the word S from backwards. Anybody who would talk in speech, we say backwards. But they say, well, the S doesn't do anything. It's backward. Okay. I will be an iconoclast. I will call it backwards light. Okay, so how do we control the velocity of light? Well, there are structural resonances and material resonances. A Bragg grating is an example here. For a beam of light to go through the structure, it gets reflected forwards and backwards many, many times. And just geometrically, it goes along a longer path, so it takes a lot more time to get through. There's also material resonances. If you have a sharp absorption feature, then by Kramers-Kronig relations, there's going to be a very rapid change of the refractive index. And then here, the group index has two terms, the refractive index and the derivative of the refractive index. So when you have a steep change in refractive index, that's when you can get a very large modification of the velocity. And of course, the ND omega can be positive or negative. Okay, what sort of got this field really excited was this paper of Lena Howe from Harvard and Steve Harris from Stanford and Lena's students, in which they showed that by using electromagnetically induced transparency in a rubidium vapor, that they were able to slow the velocity of light to 17 meters per second. They pointed out in this paper that a fairly athletic person can pedal a bicycle faster than that, so that they've really slowed the speed of light down to human terms. Now, what about backwards light? I mean, this is more intriguing because it's highly counterintuitive, entirely consistent with established physics, predicted by Garrett and McCumber, 1970. Ray Chow, well, he was my number 2 thesis supervisor, but Garrett and McCumber had the problem of coming too soon. They did their work before people cared about these things. Ray Chow did it when people cared about these things. Now, no matter what you hear, a movie that you've written 15 years ago is not going to play today. It just isn't. These are some frames taken out of the movie, which is actually more clear than what's. So this is numerical prediction. What happens when a pulse of light enters a material with a negative group index in this region here. And you see that as the pulse of light approaches this region, a disturbance appears out of nowhere at the exiting face. It splits into 2 discrete peaks, one moving forward, one moving backward. This is the backward light thing. The incident light and the backward light interfere at the input face and go away, leaving only the forward going light, which is very much advanced with respect to what would have happened if you had allowed this pulse to propagate just through vacuum. By the way, I say it's a numerical prediction. Go to your simplest integrator and solve this equation here, and you'll find this behavior. It falls out of the paraxial wave, the reduced paraxial wave equation. Just the simplest thing in the world has this behavior if you look for it. Okay, so we did the experiment. I mean, anybody who hears the prediction that light can go backwards, and if you're an experimentalist, you just plain want to do it. So we did it, and you can trace through this, and you see we did it. Of course, it's much more pronounced here in the theory than it is here, and the reason why is that in the laboratory we have group velocity dispersion, so we can't send short pulses. In the theory, we did a short pulse. In the experiment, we had to do a longer pulse, so we didn't have a lot of group velocity dispersion. You see, in my computer simulation, I turned off group velocity dispersion. My laboratory does not have a knob where I say turn off GVD. So how did we do it? Well, just real quickly, because I don't think anybody, including myself, cares about the details. We used an erbium doped optical fiber, and an erbium doped optical fiber. Well, the idea is you pump it here and you put population in the upper level, it relaxes to here, then it becomes an amplifier and a saturable amplifier. If you don't pump it, it becomes an absorber. So you can change this from a slow light material to a fast light material simply depending on how hard you pump it. And this shows the input and output pulses, how much they're delayed. In Fourier decomposition. So this is theory, but this is the actual data here showing that the output is advanced with respect to the input, in this case by 0.3 milliseconds. And here is a whole variety of data. Okay, what's the significance? The second one's the real one. But the significance is that this can reduce latency in a telecommunication system. We are not going to violate causality. The signal is not going to get there sooner, but it's not going to get there later. Or you can reduce the tendency for it to get there later because we've reduced the latency that's present in many systems. But the point is, isn't it cool? I mean, it's on the campus, of course. But children will walk up to me and say, "You're the man who made light go backwards." Okay, next, physics of sunlight. How in the world does this fit into the topic of this conference? Let's see how I've distorted history to make this appear to fit. First, let me remind you, and this is just to remind you, how does parametric down conversion work? You take a laser, you excite a material, a pump photon breaks into a signal and an idler photon. It has been so entrenched in our community that you need a laser here, and that the coherence of the laser is a crucial aspect to this, because how in the world will a nonlinear optical interaction work if you don't have a coherent excitation? But there's been a small rebellion against this, and I'm a member of the rebellion, saying that, no, look at the equations. The coherence of the laser doesn't play any appreciable role. So the first thing other people did, they took an LED and they shined it on a BBO crystal, and they got signal and idler photons coming out. But they didn't check for entanglement. So we repeated their experiment and did the classical tests to show that yes, the signal and idler photons are entangled. And then the next thing is, well, if you could do it with an LED, why not sunlight? So Hani Fatih at the Max Planck Institute in Erlangen, I guess, has a similar perverse sense of what's important in science, because she has built this solar collector that can collect sunlight and pipe it into her laboratory. You can either call it a light pipe or a optical fiber. I mean, it's highly overmoded as an optical fiber, but she brought it into her laboratory. We brought the laboratory setup from Ottawa to Erlangen, the nonlinear crystal, the detection, the coincidence circuitry. So we measured the concurrence and the purity, which was enough to convince us that these two that we produced entangled photons pumping with sunlight. Why would you care about this? Well, for satellites, sunlight up there. Don't ask me why you just wouldn't put a solar a voltage source, a solar energy source up there and drive electrically pumped laser, but it's so much cooler to do it the way we did it.
That was my question in Max Planck. That was my question that I asked you, why not going with a solar panel and getting electricity and then doing SPDC?
Yeah. There's a theoretical maximum to the efficiency. Okay, this is what I have to practice this to talk to funding agencies. There's a theoretical maximum to the efficiency of a solar cell given by reversibility, and that does not apply to the way we were doing this. Okay, that's the answer. if I had to do it, if I had to make it work, I'd use the solar cell idea. Okay, now, what does sunlight have to do with this? Well, let's go back a few years, or should I say a few decades, to my PhD thesis. And I was building an imaging up converter. This was proposed by Midwinter and Warner. Well, you know how up conversion works. Laser and infrared photon go into a second order material. They produce a some frequency photon. Why would you want to do this? Well, because in 1975, infrared detectors were far less sensitive than visible detectors. In 2026, infrared detectors are far less sensitive than visible detectors. It's not as compelling now, maybe, as it was back then. But back then it was compelling. There are not a lot of ways you can do this. This is for infrared astronomy. And Charles Town is my advisor. He was extremely interested in infrared astronomy for a whole bunch of reasons, but that would be a whole talk on its own. So I built an imaging up converter, and first of all, you would calibrate in the laboratory with some test sources, but then you take it to, in my case, to an astronomical observatory, and you start looking at things, and you find that your signal to noise ratio is not enormous. So what are you going to do? You do atmospheric propagation experiments, and we want to see how sharp the limb of the sun is in the visible and compare it to how sharp it is in the infrared. It turns out that theoretical predictions say that it'll be sharper in the infrared if you're limited by turbulence, which you always are. So there's a lambda to the 1/5 improvement. As you go to longer wavelengths, you get better resolution, not worse resolution. David Fried, the famous David Fried, if you do atmospheric turbulence, the Fried parameter. The famous David Fried came up with this prediction. So we did the experiment, and you see that the infrared image is sharper than the visible image. Okay, so that's the end of my talk about sunlight. Next topic: how light behaves when the refractive index vanishes, and this research field is often called epsilon near zero. Of course, the refractive index is given by the square root of epsilon times mu, permittivity, permeability. So when the epsilon is near zero, that means that the refractive index is near zero. So the whole point was what exciting things can happen when the refractive index approaches zero. If you've heard the talk by me or by other people, Nader and Geta was the person who really got this field kickstarted. He was not the first. He was the last. Like Christopher Columbus. He was the last person to discover America, not the first person to discover America. So anyway, let's talk about the physics of epsilon near zero materials. And remember that the wavelength of light in matter is the vacuum wavelength divided by n. So as the refractive index approaches zero, the wavelength becomes stretched. And you have this sort of behavior here, that the wavelength gets stretched and then the limit approaches infinity. The phase velocity of light is c over n. As n approaches zero, the phase velocity becomes infinite. So it means that the wave appears here simultaneously with arriving here. So you put all these together, what does it mean? For n approaching zero, the field oscillates in time, but not in space. So everywhere inside the material, the field is going up and down 10 to the 15th times per second, but in an entirely stationary manner. Okay, so everything you learned about Maxwell's equations is still true, but the specifics are entirely different than what your intuition comes with you. Now, some fundamental physical processes become modified when the refractive index becomes very small. For example, the Einstein A coefficient becomes n times the vacuum value. So that means you can suppress spontaneous emission. You can essentially turn off spontaneous emission. Einstein B coefficient has the refractive index in the denominator. So it's a strange situation that you have a huge amount of gain, but you don't have any spontaneous emission. So you say, I wonder how superradiance works. You can, it worked very well, except there's nothing to initiate it. Okay, so, but if we can inhibit spontaneous emission, we can build thresholdless lasers. If you stop for a minute and ask, what is the fundamental limit to the efficiency of a laser? And the fundamental limit is that you can pump atoms into the upper level, and instead of contributing to the output of the laser, they decay by spontaneous emission. So if you don't have spontaneous emission, you can build thresholdless lasers. Okay, some other optics of zero index materials, well, they still obey Snell's law, except one of the ends is equal to 0. And that means that light always leaves perpendicular to the surface of a material. If the light tries to enter a material at any angle other than the surface normal, it gets total internal reflection. So consistent with Snell's law, consistent with Snell's law, but in a limit that we almost never study. Okay, now how is this related to nonlinear optics? And first of all, why should you care? Well, because engineering photonics is an enormously important field. And the basic element in photonics is the switch. And at the most conceptual level, how does a switch work? You have an input and an output, and you have a control. And the idea is that this control there it is. And this control is for on-off switching. You want a situation in which the presence of this control beam can turn on or turn off the transmission here. So you want a switch with fast switching times and that operates with a weak control field. So that and you need a nonlinear interaction, because if you want one beam of light to control another beam of light, that is what you mean by a nonlinear interaction. So you want a strong nonlinear response. And there are two ways in the community in which people describe how strong the nonlinear response is. You can ask, how rapidly does the refractive index N change with the intensity of the light? And this coefficient, people call it N2. Or if you must, it's the coefficient of the intensity dependence of the refractive index. That's why they call it N2. The other is from a more fundamental level, you can ask, how is the polarization? Polarization in the sense of dipole moment per unit volume. How does the polarization depend on the strength of the applied field? And this coefficient here is the third order coefficient, or chi3. So these are the two things we have to play with. Now, but why do we care about this at all? Well, nonlinear optics, I said already, is useful for producing photonic devices. Also easy to overlook is that it's used to create quantum states of light. There's no linear transformation that can turn classical light into quantum light. You need a nonlinear interaction and one that will mix A with A dagger. I think would be the way to put it. And you can't mix A with A dagger in any linear optical interaction. And just for fundamental understanding. Trouble is that the nonlinear response is usually much weaker than the linear response. So for the past 5 decades, people have been looking for ways to enhance the amount of nonlinear response. Resonance interactions, plasmonics, electromagnetically induced transparency, composite materials, metamaterials. So our approach is to use metamaterials based on epsilon near zero materials. So that's what I'm going to talk about next. Okay. What is the connection between epsilon near zero and nonlinear optics? There's actually a very fundamental reason. I told you that N2 and chi3 are the two main parameters. Chi3 is the more fundamental of the two. N2 is, like to think of it as how the nonlinearity shows up in a laboratory situation. The relationship between these two quantities is given by this formula. And you see that the refractive index appears twice in the denominator here. So if you have a very small value of the linear refractive index, you're going to get a very large value of N2. So that was the motivation here. So I started going to the library and looking at tables of values of the dielectric permittivity. And the one that I came up with was indium tin oxide. But before doing that, let's talk about this at a, how do I get rid of this?
Your little trash can there, does that you can get rid of it?
Oh, yeah, but I wonder if I was going to get rid of my talk.
I was worried about that too.
You can see. Okay, so, but more generally, how do you go about choosing a good epsilon near zero material? Well, if the material is an electrical conductor, you just work at the plasma frequency, which is obvious. When somebody points it out to you, that at the plasma frequency, epsilon vanishes. That's what you mean by the plasma frequency. Okay, but what if you have an insulator? Well, if you have a polar dielectric, there will be you can work at the phonon resonances, and the phonon resonances in a very real sense are much stronger than the electronic resonances. The phonon resonances routinely drive epsilon negative. You've heard of the Rush-Strahlen bands? Sure you have. Remember, that's how they work. There's a whole region, there's a whole spectrum out there in which light will not propagate through a polar, I say polar, through an ionic crystal. They will not propagate because the phonon resonance is so strong that it drives the dielectric permittivity negative. There's more to life than quantum information. So after a wasted childhood studying things like solid state physics, it all comes back to us. Okay, but those are two ways. But with metamaterials, you just design it to do whatever you want. And the challenge always is to lower the loss. I mean, loss hurts, and of course, in quantum science, loss hurts even more than it does in classical science, I think. Okay, no, our favorite material is indium tin oxide. I said I found this by going to the library and looking at the books, and this one seemed to have the best properties. It's a degenerate semiconductor. We use a very thin sample of it, only 300 nanometers thick. Why? It is so highly nonlinear that we only need 300 nanometers. Real reason, it is so highly absorbing that we can't get light through anything more than 300 nanometers. But luckily, the first reason comes to save us, that even 300 nanometers is enough to give us pi/2 radians of phase shift, which is enough to do most things you would want to do. So we got a commercial sample. We put it into into a spectrometer. We measured the real and the imaginary parts of the permittivity, and we find that the real part of epsilon crosses the zero axis at 1240 nanometers. So that is where we chose to work. By the way, ITO is not stoichiometric. So any two samples of ITO might have different EMZ wavelengths. So here's some results. Here's N2 plotted as a function of wavelength. You see there's a very strong peak at the EMZ wavelength. and you ask how high is the peak, well, it's 300,000 times larger than that of silicon glass. And silicon glass is often taken as a calibration standard. So, but that's, in any case, 300,000 is strong. By the way, the overall change in refractive index can be 0.8, which is unprecedentedly large. I mean, people think that a change of 0.01 is almost unheard of and has some picosecond response time. So this lends itself to a lot of applications, and we're still working on applications, are sorting our way through what this could be. Oh, this red line down here, that is N2 for chalcogenide glass. At one time, like even as early as the year 2000, chalcogenide glass was considered to be the most linear material in Scotland. I like to give the talk and saying that ours is so non-linear that that the response for chalcogenide glass just blends into the horizontal axis. And this is the one that the Bell Labs people were bragging about for so many years. At that point, Wade Knox raised his hand and said, "Yeah, I was one of those Bell Labs people." Well, not all of you know Wade Knox. Okay, metamaterials. Okay, so with our ITO, the ITO was good, but why not do more? So we functionalized it by turning it into a photonic metasurface. We put an array of gold antennas on top of it. Here's the actual SEM. So the gold antennas modified the response. It gave us an even larger response. And there were two physical processes that led to enhancing the nonlinear response. One was just the lightning rod effect. Antennas would concentrate the electric field into the antenna. And the other is coupled resonators. You have the ENZ resonance, where electrons are sloshing back and forth, and you have the resonance of the nano antennas. If you can put those two on top of one another, they will add constructively. So here are some results. N2 as a function of wavelength. You see N2 can be either positive or negative. N2 is extremely large. And this wavelength at which it crosses from positive to negative is controllable. The length of the gold antennas will allow you to tune this wavelength here. So you have a ultra-fast, highly nonlinear material in which you can tune whether N2 is positive or negative. So it's not only that's my job to hold my word, but I think I really mean what I just said. So now nonlinear responsive layered metamaterials. Now this is something.
Just a quick question for you.
Yeah.
Can you control the antennas once you lay them down, or are you just saying that you can put the antennas, you can fabricate with a particular size of antenna?
That's what I meant.
Okay.
Not after the fact.
Okay.
Well, after the fact, you probably put a voltage, you get a tiny amount of tuning, but
Can you do
that's not what I mean.
temperature effects could also affect.
But you tilt things so the project. We're still working our way through that.
Okay.
We're still working our way through to what extent can you do it better by coming in at the normal results.
Okay.
Okay, so John Sipe is my close collaborator. So I've been working on layered metamaterials with John Sipe for 30 years or so. I like to tell people I've been working on metamaterials before the name was invented. So anyway, the John Sipe and I were, first of all, just this system here, you can calculate the linear response. And you can take the linear response and turn that into a field enhancement. How much stronger is the field inside the materials? And you can turn that into an enhancement of pi 3. And I will not go through the details right now. We are this system from 30 years ago. We're now using it in the context of metamaterials and indium tin oxide. And we ask, well, we're studying a metal dielectric composite. Okay, epsilon is positive for a dielectric, it's negative for a metal. And by controlling the relative amounts of the two, we can tune epsilon to be whatever we want. And we want to see if the materials displayed enhanced nonlinear response at their E and Z wavelength. Both my group and Velshlayev have shown that this gives enhanced response for TCOs, transparent conducting oxides, which is a highly limited class of materials. So let's see if it works for this type of metamaterial here. And the answer is yes, it did. Now, maybe it's more important to ask why we did this than the fact that it worked. If it didn't work, you already know it worked, but I wouldn't show you. Okay, so question is, do layered metamaterials also show an enhanced nonlinear response at their E and Z wavelength? And by the way, how do you define the E and Z wavelength for a composite material? So we want to use what's called effective medium theory to allow us to calculate an effective value of epsilon. Epsilon is defined for a homogeneous material. So you put two of them together in a sandwich. You can define an effective dielectric constant, but does that have any reality? So here's the experiment. We have alternating layers of metals and dielectrics. We can control the fractional amount of metal that we put into here. And here is the dielectric permittivity plotted as a function of wavelength as we change the metal content. And you see it crosses the zero axis. Where it crosses zero, that's the E and Z wavelength. And you see you can tune the E and Z wavelength anywhere from 300 nanometers to 700 nanometers just by changing how much metal you put into it. So we chose one example for our experiments. So 16 nanometers of silver, E and Z wavelength, 8 nanometers, and here. Without going into details of how Z-scan works, if you know, then you know, and if you don't know, you don't need to know. You just look at this and you see that the composite had a much, much higher response than pure silver itself. So this sort of structure does lead to an enhanced nonlinear response at its E and Z wavelength. Here is N2 plotted as a wavelength. And as expected, we get a peak at the E and Z wavelength. The dotted line is the theory curve. In retrospect, I think we should have killed the theory curve. I mean, the data is beautiful. The theory isn't. Okay, so E and Z response in artificial materials. It's just to show it's not just us. There are other people who are doing the same thing. I'm a very talented former postdoc senior scientist in my Ottawa group named Marga Cordova. And she has personally fabricated all of these structures here with the idea of studying them well, for many applications, especially in quantum information, such as building single photon sources. So, that's her quote. There's a lot of room at the nanoscale, which is a restatement of Feynman's similar statement. And Feynman's was his version of a quote from Daniel Webster. So these things go back. There we go. And here's a picture of her. And just reminding you how these things work. It's the local density of state. How does this work? You want to control the emission time. So you want to control the density of states, but you don't have a homogeneous material. It's the local density of states that we were talking about here. You control the local density of states by the immediate environment. And here are two pillars. And here is a dye molecule that fortunately for us happened to be trapped between these two dye molecules. And this is a histogram of the emission lifetime for different operating situations. So yes, we can control what is going on here. Now, Andrew, how much time do I have left? This is a break part of the talk. I could sit down.
You have 2 minutes left.
Okay, I'll wrap it up. Okay, so there are a bunch of exciting things you can do. First, just phase matching. Interactions need to be phase matched, which means that delta K has to vanish, but K is n times omega over C, and n is 0. That means that K is 0. That means everything is phase matched because 0 plus 0 is equal to 0 plus 0. And we did that experiment and it works. The context here was that it was four-wave mixing in a waveguide. You expect it to work in the forward direction. What you find is that if you set it up just right, you have 2 photons in going in this direction, and one of the emitted photons is in the backwards direction. And again, your first thought is, wait, that can't work. That doesn't conserve photon momentum. Say, but yes, it does conserve photon momentum. And that's a good time to stop. Unless you're going to give me the other 30 minutes that your vice president ordered. In the unlikely event that you wanted me to talk for an hour, I wrote a 1-hour talk. Okay, so thank you very much.
Thank you.
Oh yeah, these are just thanking all the students.
Very nice. Yeah. Questions?
Yeah, well, I don't know if I asked you this question previously or not, but would you remind me what will happen with the momentum of the light when it goes to E and Z? Because I assume that you will have also an imaginary part. So what will be those concepts? Assuming that we accept one of those Abrahams or Minkowski, one of them.
Yeah, I'll think about that. Oh, boy, is that not the sort of question. That's not for today. I've not thought about this in a couple of years, except for giving this talk.
Okay.
Yeah, no, I love the question. I love the question. Of course, this is photon momentum, which is not like, we're getting into the Abraham Minkowski game. This is not necessarily the same as kinetic. It's not kinetic momentum that's relevant here. We want to talk about phase matching. So that's phase accumulation. So it's not canonical momentum. It's probably canonical momentum that is the key issue here. Oh, but I think, and then we talk. All right. And these do not commute. I want to talk. I want to think first.
So about the SPDC pumped by the sun.
Yes.
Can you measure the size of the sun by measuring the correlations?
Probably. Yeah, I mean, that's what Michelson did, but not for our sun.
No, but now the correlation of the signal and idle after the SPDC. No, I know that you can measure directly.
Yeah.
This is what the Andre Brown and Twist did, but
Well, I guess we didn't try to collect from the entire rim, from the entire disk of the sun. So only a small fraction of the sun's surface ended into our instrument.
yeah, but in principle, can you measure the size of your source? An infrared source, like this kind of.
I will think, in this specific case, it seems unlikely, but in concept, sure. Betelgeuse is incoherent. So the fact that the source is incoherent doesn't prevent this from working. Michelson and then others, Henry Brown, measured its diameter using similar methods. So I think you can do it.
Yeah, I mean, the only difference from Brown and Twist is now we have now a nonlinear crystal. And what I'm asking is if you are measuring now, not what comes directly from the star, but what goes after the SPDC.
Something unprecedented for a professor. I'll say I don't know. But it might easily depend on whether we're talking about the one photon wave function or the two photon wave function of the signal idler. I mean, the two photon wave function of the signal idler presumably has all this information. The statistical information about the pumping for the sunlight.
Why don't you come set up and we can take one more question while.
It needs to be done.
All right, so John, you have one more question.
So a paper we wrote about 20 years ago, we said that if you took two absorption dips and then worked between the two strong absorption dips, then you could get a very large pulse delay with very minimal group velocity.
Yeah.
I was wondering if you could just rearrange that and say, take two gain peaks, two strong gain peaks and work between there, you should get anomalous dispersion.
I think so. I
But
think so.
you should minimize the group velocity dispersion.
I think so.
And so I was just wondering if you could repeat that same experiment and actually get multiple pulse advances without worrying about group velocity dispersion.
Good question. That's very, very exciting. Because in Rochester, at both universities, we're doing nonlinear optics of atomic vapors again. So this is something that could be set up quickly. We'll talk.
Yeah.
We'll talk afterwards.
You can use four-way mixing and get two.
Do you have atomic vapors here?
Sorry?
Do you have atomic vapors here?
I do. I just haven't been setting them up. So.
It's just, it's easier for me to do the experiment.
Yeah.
If I understand correctly.
Yeah.
Right.
Okay, can you unshare your screen, Bob?
Yes.
And you talk, I'm sorry, I have to miss your talk now.
Yeah, it's okay.
Stop share.
Okay, great.
This is another thing that I'm not sure if it commutes. If I quit Zoom while I'm still connected, does that mean I'm connected forever?
Okay, so for our next talk, I'm happy to introduce Yutaka Shikano from the Scuba University. So Yutaka has been an IQS member for many years, and a friend, and so we're very happy to have you with us, Yutaka.
Yeah, thank you so much for that's the kind invitation, and also thank you so much for introduction to my community, and also today's that's a brand new thing on a research team on Julia Power meets on the Yakira House in the Hoyer's delayed choice experiment, delayed choice interferometer. Yeah, that's that brand new project for me. This is the why. In that before that, this is that when I introduced to you what's happened. Okay, good. I want to introduce to my university where it's located there. This is Japan. In that, as you maybe know, in Japan, that's Tokyo. In that the center of here. And also my university near to located in that Tokyo. This is zoom into that Tokyo downtown area. And that's far away from that 60 kilometers far away from the Tokyo downtown to my university there. And also two international airports. And that's roughly speaking 90 minutes on the by bus. In the 60 minutes by bus to my university. When you visit, when you come to Japan, please consider to visit to us. And also, that's my group membership right now. That's like here. Today, that's the most important person. And that's my undergrad student. And that's now is working on that causality in the social science. That's why this my affiliation is now in the Department of Computer Science. That's the students want to come to my lab. This is the no motivation quantum information science, quantum mechanics, no teaching, no classes. That's why he begin to study. Is that initially, accidentally he met the causal inference. That's the textbook. Then today that's talking about it's the causality. That's why. And also why is that needed to consider that the causality issue. This is that's remind to me on the field delayed choice experiment, as you may know. First of all, we are standing for the double slit experiment. This is the BBO, that's the Bob in the explain that spontaneous down convention in that phase thing. And also that two photons coming from each of other. one side in that's the to go to the screen, the other side on that's the fitch D4 and D3. This is the fitch one, it that the fitch slit can be photon coming through. And also that thereafter that the beam slit, we are missing on it in that the fitch information can be erased. Then that's the D1, D2, such kind of cases, erasing on that's the fitch path information. That's why it does to open the screen on that's the coincidence on the D3 and D4, D1, D2, such kind of cases. D1, D2, that case, in that's the D1, D1, D2 cases, sorry. Oh, what's happening? Okay. Still work for my Zoom. That's happened.
Okay.
We'll be back. Okay. I don't know why. It does accidentally, this is that the D1, D2 interference pattern that can be seen. D3 and D4, such kind of cases. And that's the fitch one slit we have already known. Then that's a no interference pattern. That's the standard case on that's the direction experiment. That's point is screen is now in the hitting on that's the D0. After that's in that this event is occur. Such kind of cases, that's fitch one information is we detected or not. We infer as if in the we infer to that sort of screen at the screen spot on the measurement outcome, fitch one device. That's why this seems to be mysterious issue. That's today. That's the take-home message. This is a cluster layer on that intervention. In the sense on that causality, and also the quantum layer is we are casing. We are meeting on the weak value. That's why this is today's title is. Anyway, that's what is that Julia Paul means on that causal inference is. This is that standard sense short time course for you. First of all, then there are changing on that choice of the measurement, and also the selecting of the data on the dependent on the measurement outcome. This is different, of course. That's mean on that in the case on that textbook on the causality between that Julia Paul, that's intervention in that changing on the changing the choice of the measurement. We can do that for example, which one that's the fitch path selection measurement. We want one intervention, another one in that fitch one information we cannot measure. That's intervention. That's we selecting there. Such kind of cases, and also conditioning. Conditioning is that's a completely different one. That's I want to explain to that's the classical example. Classical example cases. For example, this is please consider forgetting about the physics. That's a standard case is a social science example. First of all, X and Y in that we want to know in that the causation of the X from X to the Y. X now in that taking the medicine. That's Andrea and me and a little bit cough today. That's why I'm taking the medicine. And the Y is the healing or not. We want to know that that's easily. It's an epigenomic issue. But some of this is the kind of case of the severity. It does depend on that's the healing or not. Such kind of cases, we want to know that's the measuring on this. Why is the hearing the case in the depend on that's taking the medicine or not. We can measure, but in some case, in that even if that's we are taking the medicine, this medicine is not healing. This is why that's so many data we can take care of it, but unfortunately, this medicine in that so many people in that severity people, that's the much more seriously on that serious medical condition people drinking about taking the medicine. Such kind of cases, this probability should be low. In such kind of cases, we want to know that all the people doing that, taking the medicine, in that after the taking the medicine, this is a weak healing or not. That's why it's a probability we are hearing exactly we treated on that taking the medicine or not. This effect only this we can extra out. That's why in the general sense, it's not this probability and this probability exactly not equal. That's why in the do calculation in the case on the in the terminology on the Julia Powell, this is the result in the causation. Common this causality causation is eliminated out. Such kind of effect on that which one that this condition exactly yes, we want to taking on this probability or not. And also, sorry. Okay. Another classical example, in that taking on that entering on the passing on that entering school or not. This is that simple example. And also the two class of the people coming on the that's applied to this school, for example, Chapman University. In that some of this one people of the class, mathematical ability should be high, can be passing through that Chapman University. Other cases, sports ability on that should be high. In the case on that passing through that this university. In the condition is on that now in the case, both one that passing through that university entrance exam of that university. But unfortunately, we are knowing on the passing through passing on the university selection on that mean only due to the post selection. Mathematical ability and also the good mathematical ability people might be is a less sports ability. This is a tendency. But vice versa, sports ability should be high. Such kind of cases on the mathematical ability should be low. In the apparent correlation can be seen due to the post selection. This situation, this we call that the conditioning on the collider. In the case on that causal inference. That's why in that how was the quantum cases in this example. Quantum cases on that example, we are now in the fourth setting. First one, we are setting on the initial condition. We are preparing on the double slit and thereafter the BBO. We are selecting on that which information can be measuring or not. Or thereafter that's the final measurement. Final outcome means on the interference or not. This is the final screen measurement. Later setting means on that's the which one information means which person information we measure or not. This measurement choice we are setting after that. This is that's the case. This is we call that the late setting in the tentative. Such kind of case is the probability now in that coming from lambda is the common causes between in that z and x or z x and y. In that due to that probability rule on that we can calculate there. And also we are knowing that treatment on the late setting, for example, we measure on the speech passing information. Such kind of cases, final outcome, what it is. This is the probability distribution we are knowing. Such kind of one, we are inferring on that no setting on the probability distribution on that fix my information in that knowing after that this conditioning after that we measuring this conditional probability that's exactly equal. This is why completely randomized on the sort of later setting on that mean on fitch my information fitch path of information we can measure or not. This is a totally randomized. That's why in that this exactly equal that should be satisfied. This is a randomized measurement, randomizing on the processes on this. Okay. Oops. That's a little bit. That point, this is a beam splitter in that Ibrahim said in the totally random number generator. That means totally random is we cannot predict. That photon coming through through the way that's photon through this way we cannot manually select it. That's why this is a truly beam splitter is randomly selected on the photon by photon, event by event. That's why in this it's random procedure we satisfy. This is we call it a backdoor condition in the sense on the classical terminology of this causal inference. That means on the later choice is not later causal as a classical layer. This is the exactly main point on this example. And also, same setting on the affecting of the colliding. Why it's now in the outcome? Outcome in that fitch one path in that photon is coming directly go through up or down, up slit or down slit passing through, or just a late setting fitch by information we have measured or not. This colliding on this conditioning colliding on this, that's the opening on the dependence on that interference pattern we be seeing or not. That's why it's that's the Foilers direct choice experiment. Normally we are little bit confusing intervention on the S mean on the fitch by information we detect or we can measure or not, or just a conditioning on the Y. Conditioning Y mean on selecting on the data of that from the screen. This exact that event is not exactly equal. That's why we want to knowing on that this is the same setting on that exactly parallel world on that Julia Paul languages can explain to that. It's called Foilers direct choice experiment. Then, how much do that? Can we characterize intermediate path? Intermediate path means that photons go through that upper path or downward path or not. That means that Z mean on the fitch path information. Is that exactly Z mean on the or up or down. Y means on the interfere not. In the S equal S means on the fitch by information can be measured or not. Such kind of cases, Z is not projection measure in the interference run. That means even if we measure on the fitch by information directly, upper path or downward path, we are destroyed completely. That's why in the no information at all. That's why in the classical sense of the causal inference languages, it's not enough. That's why we are extended to that this random variable can be generalized. This is that one candidate is now is that y is that y equal y is the final screen of the outcome. That's mean on that post selection, which one information is. That's why in that intermediate path weakly measure. That's this random variable in that can be taken as a weak value. That means this language can be meet all the weak method. Sorry, Yakira weak body as I mentioned. And also that's as I reminded to you, this is the definition of the weak value of the A. The pre-selected state is psi and the post-selected state phi. And this is the inner product. And also the denominator A as well. And also this is the probability now in the case, projection of the Z. Z is the up and down. Right? This is the two choices. Such kind of cases on we denote in the QZ. That's the notation. But in the weak value is not mathematical. We have the mathematical constraint. We have the two mathematical constraints we found there already. First of all the possibility on the measurement outcome. Intermediate path. Summation up to the nothing to do on the either one this upper path or downward path. This weak value should be the summation up to the weak value. This should be 1. This is the completeness of the condition. And the second one, this is a little bit tricky one. There's A and B on the weak value. This is a two type of thing. First one is the upper path, thereafter the downward path, for example, or just the vice versa, or just up. Similar kind of situations. Such kind of cases, that statistics on the A and B in the volume at the expected value can be written by summation of all the post selection on all the case on the weak value on the asterisk times B weak value asterisk, B weak value times that's a small correction. Such kind of case, this is because it is easy to calculate it. A and B, this is actually so easy. A and B on the weak, that's the expression value through the Boron rule. In the inferring on the inserting on the completeness condition, phi f. This is now in the case on the we call the post-selected state. Such kind of case, we inferring, and also that's the divider and conquer. This is psi f over inner product of phi f times the between the phi f psi and psi. This is the remaining on that issue on the this is the absolute square of the phi of the start of the inner product. That's condition in A weak value. That's the complex conjugate and B on the weak value. And also, this is the transition probability in that psi and phi f. That means the pre and the post selection and that's the transition probability. That's what we are taking out. That's why this is this mathematical constraint can be limiting on the weak value. That's why it's a weak value are not arbitrary retrocausal quantity, but are restricted by quantum statistics. This is one of the candidate, another candidate of this weak value. That's kind of intermediate quantity. That's going back to the Euler's experiment cases, much more simpler version, 2-path interference pattern, interferometer example. Such kind of case, psi in that now in that changing the initial condition, upper path or lower path, yeah, and also that should be additive on the phase. Exponential I alpha. Now in the change the parameter is alpha only. And also post selection is a two possibility is the up plus L or up minus L. This is the two possibilities. Such kind of case, intermediate path of this the two the sort of up project of the weak value on the post selection case on the plus cases. It is so easy to calculate it. 1 plus 1 exponential I alpha. And also, L is at the lower pass cases, exactly the same. And also the change in the post selection, this is the same thing. This is the four possibility, all the case. It is easy to calculate there. Late setting means on the changing the post selection, we can measure which path information we measure or not. Which path information we measure or not. Post selection basis we can measure. We can change on this. And also anomalous weak value. Anomalous weak value means exceeding on the eigenstate on this the pi u and the pi l. This is less than the plus minus 1. This is a normal weak value we call. Anomalous weak value cases exceed on such kind of case condition can appear near the destructive interference pattern. That means on that the change in alpha case, this is the destructive interference pattern we can see. Just the interference pattern where we are characterizing or not. That's why weak value can be can be taken as counterfactual quantity on this example. That's why this is a weak value we are changing. Weak value is that now is a powerful tool. That's a counterfactual quantity to be captured to that. And also left side on the counterfactual communication on that left example might be adapted to do analyzing on this languages. And also we are now in the context dependent density operator. We are now introduce that's when I go back to that 15 years ago work, and that's we introduce the double operator. Double operator means preselected state in the eye, going through that some of the time forwarding of the time of evolution. In the post-selected state, it has a 2 time on the condition in that sense of the Yakir-Hanoff. And also going back to that time on the phase. This measurement operator, density operator, we can call that the double operator. And also we are generalizing on the sum of the effect on that in that previous example in my old paper, there's a coupling environment, how much change to that this density operator double is that we call that epsilon w we can effect to do. That's inspiring on this work. We are generalizing on this weak value is of context dependent on the or just hypothesis dependent in that value. We can generalize it. This is the first one, AX. X is now in the causal one, in that pi, that's the Fitchman information you need to do. And also rho X is written by the double operator. This is because that's the hypothesis now in that we are setting. And also that X is now in the depend on the initial cause. That means the precedent state. And also final one, this is the final cause. Pullback effect on that depend on that measurement operator describing. That means on that effect on this previous example, previous slide, EM and FM, this is a measurement operator. This is that can be taking us. This is a similar kind of sense. Oh yeah. On that effect on that pullback effect, we can characterize it. That's why there's a slightly generalization on the double operator, exactly same thing. On the AX, on the some context on the hypothesis dependent weak value. let's see that this using this value qubit example as a qubit X-ray model in this example. This example coming from that late in that 2015 in that the Kevin Dish on that this is the experimental paper. This is the now in the we want to call in the coding on the A to B, but there are two possible choices. First one, we are preparing some of the state. Thereafter, that's the B cases changing on the some unitary rotation. This is one possibility. This is we call it the directory cause. Second one is a common cause. We are preparing on the better measure, better state. Thereafter, that we measure on the environment. Such kind of cases being what it is. That's the example. First one is the direct considering the direct cause. We prepare that's the D on the state of the plus, and the unitary evolution exponential minus theta sigma z. This is very simple. This is a qubit rotation. Such kind of case, post selection on the plus state only, and Q0, sorry, Q0 operator, this is the intermediate path. Intermediate path, we have two possibility, two level, 0 or 1. This is a very simple. Such kind of case, Q0 in the weak value, we can calculate there. This is so simple. Q1 cases is also. But transition probability to that this one to go through that post selection state is a cosine theta over 2 square. This is that's very simple. How about this the common cause cases? Common cause cases. First one, this is a better state we prepare. Final one is the post we can calculate that only this R side only to be measured. That's simple case on the previous value. Sorry. This is using this value. We call the effect on that. We can construct it. We can measure. We can calculate it. Q the weak value, Q1 weak value with the post selection in the plus state cases. And also common cause cases, transition probability that's 1 over half. 1 over 2. That means theta equals pi over 2 cases, exactly same probability, transition probability, but different causes. QCE, that's a direct cause. Weak value case, we can calculate there, this kind of thing. But the common cause cases, 1 over 2, 1 over 2. That means in the term of the sense, on the from the viewpoint of post selection, we are intermediate path, we are weakly measure, we can weakly measure and the weak value. Such kind of cases, these two values are different. That means there's the same cause rate, but the different internal weak value geometry. That means that the weak value can be captured on that cause is different is. This is one of the good example I see. Then let me conclude, and also that's a little bit much more. This is we characterize it from the viewpoint Fields choice experiment. Julia Powell intervention is the classical layer, and also the Akira and the weak value is the quantum counterfactual layer. This is a 2 point. And that's the lateral causality causing effect on the collider due to the post selection. And how about this other paradox, for example, 3-box paradox, Hardy's paradox, for the pigeonhole experiment, and also the left side on the photon asking the pass this experiment. I did not know that. Identical paradoxes on that last year, that's the presentation here. And the meaning of the weak, imaginary part of weak value is also that I don't understand it, not yet. The quasi-probability distribution, this is one of the good excuse to be explained on this example, but Z is a random variable. Random variable in the probability distribution slightly just different in the mathematical sense. Then that's I have not yet understood such kind of more. And also that's going back to the Hardy paradox. How much do we time?
Yeah, you still have time. It's okay.
Yeah, you have. I have time. That's going back to that Hardy paradox. Hardy paradox cases. How to consider there? This is that Hardy paradox in that as a briefly recapturing on this what it is. Electron and positron interferometer, and also sorry this is that all the style function on this one. Intermediate to this point is simultaneously electron and positron. This should be annihilated. That's why. Yeah. I don't know why. Okay. Now in the positron that's coming through the bright port only, electron goes through the bright port only. And also, this is also that this electron, single electron coming through this interferometer. This is what we call the bright port and dark port. Positron gets a case, vice versa. How about this? That's the simultaneous cases, pair annihilation, as I said, and also outer path. Electron goes through the outer path, passing through. Electron and positron can be go through the simultaneous. Is not be affected to electron passing go through. That means that the bright port should be two. But this is a detecting a port in that bright and port. This electron that's exactly same speaking on the opposite side on the beam system, sorry. And also that's the bright port electron can be go through that bright port and the dark port. That's the two possibility. Bright port or dark port bright. Vice versa, a positron goes through the outer path. This is the electron nothing to have, not to interfere, that's the positron. But the case, electron goes through the bright ports directly, but in the positron, that's the possibility to see bright port or the that means on the bright port or the bright port, but dark port. But unfortunately, quantum mechanical calculation in that the dark port, quantum mechanical tells us clicking on the dark port. Probability is that 1 or 12. This is the questioning about in the Hardy paradox. Normally, this is what's happening is in that why is it coming from? Where is it coming from? That's this paradoxical issue. Before the annihilation, this is a four possibility. In that inner path, outer path, outer path, inner path, outer path. This notation, electron and positron, sorry. If that's the case, annihilation on the case, this is one was third on that inner path, outer path, outer path, inner path, outer path, outer path. Such kind of cases, thereafter that, this is the dark port jointly detecting on the calculation in that 1/12. That's how about this experimental confirm. This kind of cases, outer path, electron goes through the outer path, positron goes through that inner path plus outer path. This is simultaneously can be go through. And also we identified electron goes through the outer path, positron nothing to measure. This event exactly same. In the condition is the psi on that's the initial condition. And that's also the same cases, vice versa. Analogically, electron goes through the inner path, should be that the positron should be go through that outer path. Electron goes through that inner path on the positron we do not see. This condition exactly same. In the condition on the case on the psi is selected. Such kind of case, in that we are knowing on the state dependent equivalence I want to introduce. That's the kind of example. Normally A equal B is the operator case. Any psi we are normally equal. But state dependent equivalence means A minus A to B, this A minus B square, that's this condition, that's the inner expression value should be 0. This is because that's A minus B exactly, A minus B in the condition of the psi exactly 0. Such kind of cases, similar calculation is happen. A weak value and the B weak value, all the post selection exactly equal. This is also the same state. Or the counterfactual quantity should be equal. Such kind of to apply to that, this example, this quantity should be 0. That's all the counterfactual quantity should be 0. That means psi in this condition satisfied if and only if preselected state psi is given by this is the initial condition. That means the normal condition we have already know. That means counterfactual quantity can be characterized by in the preselected state. That means that we can inferring on the cause as well. In the time ordering is different. That's why this is experimentally checked realizable on this condition. Okay. Then I think on the already ongoing on the project on this example. Why not to be that in that we are interested in? Let's not speak again. Sorry.
That's exactly right.
Sorry, fine. No,
You can
sorry.
share your own talk.
No, sorry. I was a little bit sorry.
All right, so questions for Yutaka?
No.
So I think the root of your talk is you're trying to distinguish causation from correlations in these experiments.
Yeah.
And so do I understand correctly that you're able to tease apart, in which sense, that this, like, for example, in your first example, the delayed choice experiment, that this way of acting or not acting by, say, for example, removing this beam splitter is able to cause this interference pattern to appear or not. So what is your conclusion? Does it cause it or does it not cause it? It wasn't entirely clear.
Okay. That's the kind of case. On this causation coming from, normally this is a retrocausality.
Yes.
Retrocausal inference, we infer from the viewpoint time backward on the selection. We are screening on the selection of it. But unfortunately, in the case on final viewpoint of our final outcome, it's random, not just only this rate setting mean on the which information we can get in or not. This measurement choice and also intermediate path. Intermediate path mean and that the photon coming through that upper path or lower path. This apparent correlation will happen in the normal case on the Fourier delayed choice experiment. But slightly just a completely different one. This language is that the beauty of this language is clearly distinction between those two. Which one is the information we measure or not? This selection it's not directly close to that intermediate path. That's why it's not apparently correlation will be seen, but this is a fake correlation will be happen on the post due to the post selection.
Yeah.
This is the message.
Okay, so you say basically it's not causing it.
It's not causing.
And the reason you believe that is because you calculate these probabilities and they're equal.
Yeah.
And that's the basis of this judgment. You do this little calculation because you say for the causation to happen, you have to have this difference of probabilities.
Yeah.
And you don't find that.
We don't find that.
Okay.
Yeah.
Right. Other questions?
Yeah, for example, in the way imperfection,
Yeah.
imperfection on the meaning, on the sort of another kind of the code, we putting on there, Z and X, or G and Y, S and Y, sorry. Such kind of cases, another different situation will be happen. Yeah, that's the modeling on the point on this languages. In that normally it's the time ordering on the we are seeking on it. First one is preparing on the station. There's the intermediate pass. The final outcome means that's between before the screen is hitting. If in the late setting on the Fitchman information can be getting or not, we decided. Thereafter the final outcome. Normally this is the time sequences. Initially we are thinking about it, but no time ordering on this graph. Just only the causation on this.
Right. I understand.
That's the point.
Okay. All right. Let's thank you, Taka.
Yep. Thank you.
Okay, ladies and gentlemen, we have lunch just outside and we have some nice picnic tables in the garden outside, or you can come eat here wherever you like, and we'll reconvene at 2:00.
Yeah.
Too cold outside, or is it too hot outside?
I think it's California. It's just right. It's all.
And the weather report, it was gonna be 90 degrees.
That's
hot.
it's today is not.
It says, oh yeah, that's
now
right.
it's not.
Thank you. That was very good. That was some of the best explanation of that.
Yeah.
But
Not yet in the past. I don't know.
there's such a confusion. There's something that confuses me.
Yeah.
See, saying there has to be a difference in the probability, but of course,
Oh.
if that were,
Even
okay,
controversial.
I understand, that makes sense.
Yeah.
If we'd have a cost effect. But if such a thing were true in terms of weak values, then it would be actually retro, I mean, you could actually violate.
Story of this.
It can never do.
Actually.
So I'm confused.
That's causality means on the two causality. In the sense on the standard sense of the causality in the physics.
Which is so recently published.
This is we are now not inferring on my measurement choice. It will not instantaneously directly affect to your
Yeah,
measurement.
but his.
This is normally causality in the physics.
This a lot.
In the sense on this causality,
They published.
that's only the causation.
Mass E equals to MC square.
Causation means on we don't have in no time of use meeting at all.
And then we found
That's why
Schwinger's derivation.
is that
Logically.
apparently on the weak
Gives you
value.
more. It says
Yes.
the text.
Anomalous weak value cannot be no violative on
Vacuum, the Gauss units, right?
causality in the physics
Looks like
sense.
I see.
No causation.
Yeah, yeah.
Just only this can be captured
You
as
have a energy
counterfactual.
acceleration, you have a
So
acceleration of momentum. Sorry, energy.
there's no time ordering.
No time ordering.
You can actually.
I mean,
Let's skip this part.
Of course, there's a unitary evolution.
oh, you still,
we
still have before after, or no, you don't have before after? No time.
No time.
Then,
Yeah, that's
doing some
only this,
trivial
that's
calculus,
only the situation we
you end up with the equation that looks like.
in the case on the two boundary condition.
The
in
total
some-
derivative of this
In
integral.
this
You
pre
would-
and post selection.
Yeah, exactly.
In the between, what's happening is,
Yeah.
now we wanna know that.
He is this. So this is stringer, right? What stringer is?
This is-
He's this.
In this
I'm gonna
situation,
introduce
no time of
PPP.
evolution at all.
Where I will take talk.
On this,
okay,
the after,
local-
completely
yeah,
after,
the global.
in this
global energy. Oh, because it's in a vacuum.
that's why this is no type of
The integral of
evolution.
is one by
I wanna mention.
definition.
Okay.
Right.
That's-
because it's a
that's fine.
constant, you can take it out.
That's,
It's
yeah,
always positive.
that's
Okay.
inside,
It's actually from
that
zero to
situation,
Okay.
how to
So it
explain.
looks like probability.
Wait, wait,
This language is not the causality.
He is.
Causality means on the, sorry,
you're
causation,
on-
sorry.
Causation.
I get it.
Energy
That's the
density.
real.
Have you written this up?
No, no,
or
it's
no?
not, it's a total energy.
Have you written?
It's total
Have you
energy.
written this up?
Yes, total energy
No,
of
no.
the- of the electric, of the pulse.
Yeah, that's annoying, that's this is brand new protocol.
Oh,
No.
have you talked to Pearl about it?
Positive, everything is positive.
You spoke with-
integrates.
No,
yeah, bro, no.
No, this is the first time in presentation.
Yes.
Because he's
No.
local, right? He's at, where is he? At UCF? No,
Yeah,
UCF.
yes, yeah.
Yeah.
Yeah, I should do that, I
I'm
should.
sure he hasn't followed,
Committee packet.
he doesn't follow what we do, I'm sure.
Yeah, but I don't know exactly speaking on that.
That's a question
Don't
for
contacted how to do that.
Shrink-
Yeah, this is much more
Right.
than
He's in the,
In this form.
where is he?
But,
Is he in the philosophy department? I can't remember.
and that's the
Excellent.
department in that's computer science,
Oh, okay.
and that's
Center
cognition,
geometric
cognition
energy center of the Big Bang.
yeah. This is that's the key, that's the particularly interesting in that's the,
Okay.
I think on the brain science, the
It's classical.
cognition.
Yeah.
Mm-hmm.
Classical.
That can affect that's
So
the
you
here,
get this equation,
thinking
Yeah.
about this.
Where
That's why
the
in that
total-
kind of thing.
total,
Very good.
momentum.
And by the way, when do you go back?
Of the pulse.
Wednesday night,
And so
After-
this looks
after
at-
the Andrew's house,
What time is the flight?
and that's
Then
one
is, of
AM.
course,
Oh, okay, no problem.
Yeah,
over
just,
C squared.
Yeah.
Very good. Thank you.
yeah, thank
You're
you.
talking beautiful talk.
So this is
Really
where Schwinger stops.
really nice.
Yeah.
But here's the fun part.
Which book does Schwinger do this? He wrote.
No, it's not the all one.
That's
Oh,
a little bit now.
Yeah, so.
This is not the, this is not the not yet written on the papers.
Second edition, the first edition was in nineteen
Anything
something.
like the presentation.
Early. Yeah. Another student. So. Science.
Yeah.
But the key is that this is what's cool.
I didn't know this.
Yeah, this is a really cool part.
Mhm.
They talk
Is that-
about how
Mhm.
you.
He assumes that the velocity of light is c. He actually assumed that.
Okay.
In fact, we don't need to assume this. We can actually take this equation and turn it upside down.
Because it has
and
exact
this
relation. Yeah.
is a operational definition of velocity of light.
You know,
And that's why that's truly hard.
Right, so it's the ratio of two conserved quantities.
and it's related to the fact.
Net
how
momentum
minority-
divided by the net energy.
Yes.
And c squared is basically unit square.
Yeah, yeah,
It's not that.
That's another point.
It turns out, of course, you can show that in vacuum, it's limited to c.
Mhm.
It's like you just c, that's it.
This is a statistics in that.
That inspires us, okay,
How
let's
does
go to the medium,
escape
homogeneous
Maya
medium where you have epsilon.
Right,
minority or
Uh-huh.
something like that.
I guess.
Of course,
we could say equal.
It's not the probability, it's a
Then
Pretty-
what happens is that you
such kind of
we
case.
can actually,
How to deal with it.
we can
This is a-
scale classical
What is the
vacuum
making
equation into
Well, they know how to.
ideal equations. Basically, this substitution turns homogeneous and
They
vacuum
know how to
equations into
phrase
homogeneous
questions
medium.
in such a way.
Right,
And then automatically you get a definition for the velocity in the medium,
but
Yes.
right?
this is a
Homogeneous
skill
medium,
that
where epsilon mu appears in
there are
there.
some cases.
As well
That's why
as
in the-
automatically
We do
you
not
get the
know
definition of
how
mass.
to deal with.
So that means that in
That's,
EMZ,
Quantitative in social science.
mass is literally zero.
Social science means
And the velocity literally goes to
Evidence-based,
infinity, even if you don't
evidence-based
assume c to be the velocity of light.
statistics.
And there's a nice little proof that you can prove that this definition of
kind of
velocity
drawing.
can never exceed phase velocity. It's always the phase, it's always like,
Hitting the
it does not never exceed
Oh,
phase velocity.
yeah, that's some kind of ethical proof,
And
BBC.
yeah, so.
So you are.
So the interesting, so, and also I did some mathematics. So this theory, this derivation assumes
That's the sort.
homogeneous
That's it.
That's,
epsilon
that's.
is like frequency independent, right?
So you change the
They're not
department.
really
Yeah, no, but that's
Because
this
they-
kind of.
Some simulation.
Yes.
And it turns out
I offer
that this formula 37 does work very well, except that, of course, I did two different simulations, like
That's a starting point.
P is Abraham and Minkowski.
Oh, it's
So
now 3 and a half.
and actually, turns out that this equation,
It's a good
let me
one.
just show you the.
And also that,
I never
yeah,
know which
yeah,
is.
as a PI.
When is the mass of the photon?
The mass of the electromagnetic classical field.
Yeah.
Say again?
It's not X.
Oh, yeah, that.
Now I'm into this.
That's,
Okay.
I think that's the.
Okay, bro. Okay.
Yeah, I think on that.
It's similar to
On that,
photon.
That should be related, right? But,
At the
but
time,
I'm not,
we did not
So I
meet,
took
no,
indium,
we are briefly chat,
so
briefly chat.
indium,
That's the say hi.
Okay.
niobate,
That's
right?
normally this is not the
This is
come to.
simulation.
Not really, it's so much more the same.
This is the key.
Okay.
Yeah, that's the
You think
simply thing on the.
Minkowski
It's roughly the same area.
definition of momentum in
That
the
that's
medium.
mean on the
Then
California
this
scale,
formula
this is the same.
Okay.
For us, that's
Mass.
different.
Yeah.
works, and this analytical formula gives you basically Minkowski.
What's mean on
If
the.
you use momentum in sense of Minkowski, so, but Abraham is like 2 orders of
The
magnitude.
KO is that's near to Yokohama,
So
then that's
basically,
half of the, half of our train.
this Einstein's modification, like identification to Einstein's energy momentum relationship works for EM.
Two of them,
If we
two and a half.
can be used if we accept
That's why
Minkowski
that's the same area.
definition of
I
mass.
don't know exactly
So-
what to say.
So this is like a realistic simulation.
In California,
The-
it's a, exactly the
So
same.
I think it's pretty nice because that consequences is that you have a zero,
Twice, actually.
right? Zero mass.
You met in that,
Like basically,
this is the first time to meet.
In the material carries no mass.
At the time that when I was at
This carries no mass.
Institute for Molecular
So this is
in Japan, this is what in Japan.
and yeah. So
the
this is
first
just
thing, and
maybe,
that's
I'm just I know that you wrote a lot of things about this.
No, I.
And in all these
Yes.
three places.
So but
This,
I.
oh, more than
Institute for Molecular Science, University of Tokyo.
no, I know it's a very
I
so
haven't thought about these things in about 10 years.
these five
yeah.
places.
So the key is that
Teach in any
both
of them.
speed of light
Mhm.
and a mass of light
Yes.
For fast two.
could be derived
No,
by
part
consequences
The first
of
three you taught.
energy.
I thought only that
conservation.
I completely.
And now
The last two.
Last
They work
two
in
that
tandem.
education, last
and
month,
the,
previous
these
Umma
and
University.
the mass modification, mass specifically,
Oh.
this for if you take realistic material, this formula, simplified formula,
not-
which works
it's
only
not-
for homogeneous material, which is
Really
dispersionless, absorptionless, right? The
Mineral.
sorry, dispersionless and absorption rate, right?
This is not
Actually
education.
works
No, I understand.
if you accept Minkowski's definition of momentum.
Similar like that's a chap,
Right.
that previous, sorry. That's a-
Of course, because
Long
in
time.
realistic material, I cannot derive anything. It's just hard.
Yeah, that's the
It's just too hard. It's too many things. But we can do
Not the
simulations. right?
Bigger and bigger, sharper. Then that.
Yeah, so, but
Yeah,
in
that's
the
right.
literally, whatever you do,
Is that
there is no mass.
should be that.
Light has no mass in the
Different university.
It's still not our
Say
one.
that again?
We have these categories.
Light has no mass. Light has no
The
mass.
highest universities in the US, the highest, the top
In
one.
the correct to this analysis.
Harvard,
Yeah.
our one.
Yeah,
This is
There's no mass.
Hard to
No,
get.
all momentum.
Yeah,
But aren't
they need a momentum
It's
no
still
mass.
up, there is other.
So it gives
Nice,
nice.
nice.
No, not.
It's for, but it follows from,
Simplistic.
yeah, but this is like follows from classical.
Honest, there's
It's not even,
three,
Yeah.
maybe there is no.
yeah, exactly, like, so your
When I
conclusion
come
is
to
confirmed.
Jeff. At that time,
Yeah, you want to-
There is
But
other.
I remember that
Maybe
Jeff,
there's not even.
Jeff said to me.
Sure, if you care.
But.
It falls off, it doesn't stand. Oh, my.
That's a.
But it won't, if it keeps falling off, then you don't want it.
It's the education.
That acting vector, just like K vectors, A hits each one individually.
Yes.
So I'm trying to make sure in my mind if I apply this to a K vector, what is the operation? The I hits each vector.
Yes,
Alright, so it's the I matrix or?
Later, I can show you the new lab.
Yes, oh, you can, whatever do you like.
Yes.
These three talks are over here.
Yeah.
Well, it's not the front of it.
Okay, very good.
Tomorrow we sit in place.
Okay, very good.
Right, takes us to that.
You are.
No.
Where it is.
You should.
How are you?
Good, very well.
Yeah, it could be.
And by payback. Yeah.
Okay, I need to get my, my little,
Correct. Yeah, any vector, you can write it like this. We have to be the standard basis. I mean, the thing is that. Yes, absolutely. Yes.
But as close to the farm, I feet.
Yes.
I think
it will be immediate.
That's your chairing.
What is this?
No idea.
It's
I have no idea.
So they also.
Thank you for
So then, because I want to write this in the note.
Speaker is already there.
Yes, yes.
We need to write it like, to speak that, we have to write like that.
So it isn't.
Okay, okay.
Yeah, we just.
The moment you do the basis, you're done.
You got.
This is what you're saying, this is correct.
Good.
The moment you write the structure of the basis, you're done. That is the Koshibina. Yeah, absolutely. So.
That's not a bad place. I mean.
You see. Cesium.
That's all we get.
Yeah, so we had separation.
Right.
I know. They would stop. When we stop.
So the starting now,
But teacher, so I.
speaker is now in the off.
You go down?
Andrew.
No, down, now is the speaker.
Don't worry, Andrew.
That's not possible.
Very good kids.
Yeah, but then the impression.
Oh, yeah.
Well,
I guess the top, yeah. Did I shoot you?
yeah, well.
Sherry?
You can be my chairman, Yutaka?
Yeah. Okay.
There's information, right?
Okay, shall we? Okay, shall we start the session? Oh, yeah? Bob? Okay.
Right here.
So let's do it.
Be careful. Yeah. It's okay.
Yeah.
Okay.
You haven't talked to Mark.
This is already time to pass to the, a few minutes. On that, shall we start on the session on this afternoon? In that, this afternoon, a meditation. Two speakers in that, after the break, and then one speaker, and also the discussion. The first speaker in that, Andrew Jordan, on that initiative, director of this institute. That's we are longtime friends. Yeah, that's the thank you so much for that. In that today's, that's the direct measurement of the quantum should distribution via its generating function. That's it. Yeah, please stop.
Okay, so I realize it's somewhat bad taste to give a talk at your own meeting. But this is a general institute meeting, so I'm a member of the institute, so here I'm in my capacity as a member, not as the director. But I wanted to tell you about something, some of you I've already spoken with about it, so thank you for your patience bearing with me. But about some new work I did recently about the pseudo distribution, connecting to Kirkwood-Dirac pseudo distribution, but trying to think about this concept more generally. And there is a preprint of the paper, so if you want to follow along at home, there's a QR code for the preprint that should hopefully be published, whenever the referees are happy with it. So I'm going to tell you a little bit about pseudo distributions, a little bit about weak measurements and weak values, which for this audience is somewhat redundant, but I'll do it anyway. And then I'm going to propose an experiment. This is how you could measure these pseudo distributions in a direct manner. And of course, it's tricky to do this. Why? Because the idea is that we want to have a probabilistic description of certain experiments or results in quantum physics, but we know that we can't do that with a positive normal distribution or regular conventional probability distribution. So we have to expand the space to include things like complex numbers and negative numbers and numbers bigger than one. We want to do this, but of course you can't measure those things as frequencies. We have to do something else in order to directly measure it. So I'll propose some experiment, and the route to do that, as you will see, is through its characteristic function. And of course, feel free to stop me and ask questions at any point. So this is work done in collaboration with two people. David Arvidsson-Shakur is my collaborator at Cambridge. Then Ephraim Steinberg. I roped Ephraim Steinberg into being my co-author because that way he's actually invested in actually doing the experiment, not just running equations. And so we have some funding. I think I mentioned on the first slide, this was funded by the John Templeton Foundation. So we have some nice funding to have our Quantum Foundations Hub. So several of you here are involved with our Foundations Hub here at Chapman. So very well. So what's this all about? So we all know about the weak value proposed back in 1988 by Yakir, David Albert, and Lev Weidman, with the ingredients of a pre-selected state, a post-selected state, and some weak measurement of an observable A. The famous controversial title, How the Result of a Measurement of a Component of a Spin 1/2 System Can Turn Out to Be 100, which got people all angry and ornery, which was sort of the point, I think. Anyway, so there are nice ingredients that I certainly have written many papers about over the years. It's time symmetric. It's sort of an extension of the concept of an expectation value, but it can do weird things. It can exceed the eigenvalue range, and it's complex in general. So this should be ringing bells if you're thinking about pseudo distribution, because those pseudo distribution shares many of those properties. And so one simple way of doing it is with the Stern-Gerlach apparatus, where we have two different Stern-Gerlach apparatuses with a fringing magnetic field. We have a weak magnetic field to do the weak measurement in, say, a p direction, but then a strong splitting, say, in the x direction with the second field. We do a post-selection. Here it's taking the form of a beam block. And then I'm going to measure the deflection in a conventional Stern-Gerlach apparatus like so. And so this splits you in the z, this splits you in the x. The idea is the spin can come along, and then you're looking for the rare post-selection in this case, where you get the anomalously large deflection, and you read that as the meter as the anomalously large weak value. So yeah, so these are the ingredients in the cookbook recipe to be able to do that. So good. So that's the weak value, and if we have the distribution like so of events that you would have in the transverse direction, a splitting up or down. If this was, we correspond this to, if I spin up, for example, spins, this was like h bar over 2. If I send and spin down, spins, this is minus h bar over 2. And then the idea is that we get an expectation value when you post-select way out here in the tail of being, say, 100 times h bar over 2, for example. And the distribution, of course, the trade-off is the fact that this overlap is small in order to do this. So that means the number of events is greatly reduced when you post-select. So these are rare events, but they have this distribution. So much smaller in height than the original. So we've done a lot of work in this over the years, with Justin and Robert Boyd, who's right here with us. We have this beautiful review article. It's been very popular over the years. So that was a good decision, Bob, to write that review article with Justin as the first author. We can implement this optically with polarization or with, where's John? John Howe. There he is right there in the front row.
There's something funny about the fonts choice.
What's so
I
funny?
approve entirely.
What's that, Bob?
Maybe I'm wrong. It looks as if you wrote my name in a larger typeface than the others.
Conservative. It should be bolded.
I'm not complaining.
That's all you're saying.
Quite appropriate. Anyway,
So nice optical realizations of this experiment, and of course, not just to demonstrate the experiment like you would here, but using it for very precise beam displacement measurements, and then many other follow-ups we did over the years with John and company. Good. So one way of thinking about it is if we have two operators, say an operator A and a second operator B, and we have a particular value of the second operator, we call it little b of J star, that would be the post-selected state. We can write this weak value as a preparation on the initial state psi I, post-selecting on this value Bj star. This is the traditional weak value formula. I can write it a little bit differently by multiplying and dividing by the complex conjugate of the denominator. Now this becomes the probability of measuring that final state, Bj star, with a weak measurement in between. And then we have this combination right here. And so in the weak measurement limit, we have this probability of measuring this quantity. And we notice that it satisfies a nice sum rule. So if I multiply the weak value times the probability of the result, and I sum over the outcome J, it turns into the expectation value of the operator A. Okay, so that connects the operator A to some other operator B. So this is our weak value stuff. That's a property that it must obey. But now let's talk a little bit about quasi-distributions. So there are many quasi-distributions in quantum physics that have been introduced over the years. The most famous is that of Wigner. But we also have the Husimi function. We have the P function, the Q function. So this is work done by Kirkwood and later by Dirac. And the idea is that here it's for a mixed state. So the idea is I introduce a quasi-distribution Q such that this thing plays the role of a probability distribution, but it takes on values in the complex unit disk. So it's formally defined with two objects. So if I have this A operator and the B operator together with their eigensystem, the idea is that if I have a quantum state rho, I take a sandwich of the state AI with Bj and the overlap of those two things, and that defines the quasi-distribution as if I have basically two values, two results. And what's nice is that I can define these lambda operators, which is a ratio of the outer product divided by the inner product. And with these mathematical things, I can reconstruct the distribution rho. Okay, so the main lesson from this slide is that the quantum state rho is mathematically equivalent to the Kirkwood-Dirac quasi-distribution. So if I give you one, I can construct the other with this construction. And here again, I'm using the eigen decomposition of the operators A and B in order to calculate this. And you see immediately that there's no reason that this thing should be real, or so indeed it is generally a complex quantum. Okay. And yes.
Andrew, can you tell us, my apologies for interrupting you, can you tell me about what are the eigenstates AI? I mean, should be any operators or a specific operator?
Yeah, so these are general operators, completely general. I think here we're using Hermitian Hermitian operators. So these eigenvalues are considered to be real numbers, but other than that, I want to be completely general. So the idea is that with these sets, these two operator sets, I can use this to construct this distribution.
So for example, A and B can be identical as well?
They can be identical, but then it's kind of boring. Right?
Yeah, it will be
because then they have Or usually what you want is you want them to not commute, because then you get interesting, the non-commutation that shows up, and that's where you get the interesting pseudo distribution.
Thank you.
So you can see immediately that there are certain properties. For example, if I sum on the first index I, that's a complete set there. So I can take this out. And then if I sum on the second index J, that's going to be then summing over eigenstates sandwiched between rho, which is the same as the trace of rho, which is 1. So you see if I sum over both indices, I just get 1. So it's acting like a joint distribution, but with these weird properties. Okay, So now I can think about not, so that's like a joint probably, this is like, so the idea is that you can imagine I have an outcome I and an outcome J. So this is analogous to a joint probability distribution that's quasi. So now we can generalize this to a conditional one. So with the weak values, I'm always conditioning on a second measurement outcome. So we can do the same way. So I can write now this Q tilde I/J indicating a conditioning on the second outcome J. So I define that using a generalization of Bayes' rule. So I take the joint probability, quasi-probability, and divide by the marginal. And what I find there is that, yes, so this quantity P then is defined as the probability of obtaining outcome J, Bj, given the preparation rho and the measurement in the B basis. Okay. And so, right, so this is, I can define it this way. So I can, it's equivalent to then marginalizing over the first index, which as I showed before is the same as the expectation of rho in the B state. Okay, so like the probability of obtaining result B. Okay. And so then I can then take my, now a conditioned average. So I take my operator eigenvalues, I weight them by my conditioned probability. And so this is the same thing then as a conditioned average of the operator given conditioning on state, on result, a particular state, Bj star. So this is exactly what we define as the weak value, but now I'm expressing the weak value in terms of this Kirkwood-Dirac quasi-distribution. Okay. All right, so what do we take away from that? We see that if I have an average A under the quasi-distribution, and now I exceed the eigenvalues, if I get something bigger than eigenvalues, you see here I'm bounding this. Obviously, I'm weighting the eigenvalues by something here, but this is going to be bigger than the maximal eigenvalue. I can't have a normal distribution here. I have to have an anomalous distribution in order to get that. Okay, so I have to have negativity or complexification for it to exceed the eigenvalues of the anomaly. So now you begin to see why these things are useful to be able to get my hands on the quasi distribution. Okay, so just a little bit of mathematics here. So this is my condition. This is my definition of my weak value. I'm going to then expand that out in terms of the eigenvalues AI times these Kirkwood-Dirac expression here. Right, so this is like a weak value projector on AI. I can then write this, I multiply and divide by the same thing to write in terms of the probability. So this goes from the weak value expression down here to the Kirkwood-Dirac distribution. So basically it's saying in a direct way that the weak value formalism is exactly the same as applying conditional Kirkwood-Dirac to calculate this out. Okay, is that clear? So they're equivalent. Good. Yeah. So this is a takeaway. Yeah. So the weak value is an average of the eigenvalues of A under a conditional quasi-probability distribution. So it must have negativity for it to exceed the eigenvalues. So that's the takeaway message there. Okay. So now I'm going to give a proposal for how you can actually measure this quasi-distribution or pseudo-distribution. So we're going to think about an experiment involving 3 time points, like with the weak values, some initial state, some generalized measurement, and a post-selected state. And the question I want to ask is it possible to empirically measure the quasi-distribution directly, despite it being impossible to find from frequencies? Because frequencies only give me numbers between 0 and 1. So I need to employ something like a correlation function in order to do this. Okay. So the idea is we're going to imagine we can assume we can measure any power of some operator A. So I'm going to imagine A to some power n, okay? And I'm going to think about measuring this weakly. So we'll have the weak value of A to the n. And so I'm going to basically take those same formulas and now apply it to the nth power of the operator. So now I have something like this, weak value of A to the n. So the important idea is that this is nothing more than the eigenvalue of A to the nth power times the same quasi-distribution conditional right there. Okay, so and that's true simply because of the fact that the nth power of the operator can be written as the eigenvalue times the same quasi-distribution. So that's an important assumption. Yes, the eigenvalues of A to the N are just a little AI. Okay, so that's going to be our idea, and now let's unpack that a little bit. So what is involved in that? So if I start writing that out, something like this. That'd be one weak value. But if I had a squared weak, this would be the same thing, but now at the second power, and so on. A n weak. Like so on. And so imagine I do a series of measurements where I collect this data, this data, this data, this data. And then what this is it creates a chain of equations. And if I write these out in terms of these values, remember I had this sum over J, J, Q, I'm sorry, I given J. This one would be the same thing, but I have here AI squared and so on. And this was going to be AI to the N, UI given J, and so on. The idea is if I have this as sets of data, I know what the eigenvalues are. So given enough of these equations, I can figure out what I want, which is the values of these guys, every value ij. Okay? So if I take those equations and I assemble them into a matrix, I get this equation here. Okay? So the first one has just ones across the first row. The second one has all the eigenvalues squared all the way down to the nth value, like so. Actually, I think there's a typo. I think it's n minus 1. Doesn't really matter. And here are all the things I don't know. I know this, experiment gives me this. And so I can simply invert it to be able to find out what these values are. Okay, so that's the idea. And the important thing is that because these can be complex, the weak data, I have to measure both the real and the imaginary part in order to do that. Okay. So in this way, this gives us an empirical way of figuring out what the Q's are that satisfy this relationship. Okay, so we just, at the end of the day, so this is a kind of matrix that appears in mathematics. It's called van der Maan matrix. And so we can simply invert that, and that has very nice mathematical properties that are well known in the literature to be able to invert this matrix and figure out what the values of Q are. So that's the idea. The trick is, of course, I have to make n of these measurements and collect data and statistics and so on. So this takes time. And so let's get a little example. So if I just have a two-level system, I just need two measurements, or actually just one measurement, really, because the first one is just the identity, right? It's just one. And the second one is the weak value of sigma z pre and post-selective. The little matrix, the van der Maan matrix, is very simple in this case. It's 1, 1, 1, minus 1. So if I invert that, it's very simple to do. I can say that QIs is just going to be 1 plus the weak value, 1 minus the weak value divided by 2. So quite simple. But now you'll be able to see the direct connection between these two things. So if we take Yakir's example, the spin is 100, right? So here I have 101. Here I have negative 99, whatever, over 2. And we see that, we see that we have to have, then these guys have to then exceed 1 and go below, become negative in order to achieve that. Okay, so that's why it's a pseudo distribution. What else do I want to say about that? Yeah, I guess the other thing, it still obeys the marginal properties. If I add these together, right, you see that this term cancels that term and I get 1. So it does indeed sum to 1 as it has to. All right, but now what if I have not a discrete Hilbert space? So here maybe it's important to say I need as many measurements I need to go up to the dimensionality of the space in order to be able to invert uniquely this matrix. What happens if I have a continuous thing? Well, then I'm in trouble because I can't make an infinite number of measurements of higher powers. But what we can do is something kind of like that, which is that we can, rather than thinking about them all the moments, we can think about the generating function or the characteristic function of the moments. So if I write out the analogous thing for a continuous thing, instead of summing over all of the eigenvalues, now I have an operator O. Operator O has a eigenspectrum. We'll let the eigenvalue be lambda. So now I'm going to integrate over all these lambdas. If I take the nth power here, this becomes the nth power of the eigenvalue. And now little q, I call this the pseudo distribution for the continuous case. Again, pre and post selected. So what I'm going to do is I'm thinking about the generating function or characteristic function. So I sum over all moments like this with a new parameter, let kind introducing with an exponential sum. And because this is, I can simply do this sum directly here, because I have this expression, I swap the integral and the sum, and this becomes a complex exponential e to the I chi lambda. Or equivalently, I can just do the operator sum directly, and this becomes a new object. So now this is going to be the characteristic function of the pseudo distribution. So I consider this as the fundamental object I'm going to think about. So rather than thinking about the moments, I start working with this characteristic function, and that's the fundamental object. And I think, how can I measure that thing directly? And that becomes the fundamental. What else do I want to say about this? Just the fact that if I look at this now, if I can measure this thing directly, what is it? Well, it's nothing more than the Fourier transform over lambda, my eigenvalue, of the pseudo distribution. So that's really appealing, really nice, simple. How can I extract, if I have data about Z, how can I get Q? I just take the inverse Fourier transform. It's very simple. So it's an interesting result. So the thing I want to measure is not this infinite number of moments now. It's this new function Z parameterized by the single parameter chi. So I want to be able to think about this, measuring this thing. Now it becomes an experimentally realistic task because I can simply imagine scanning over this chi, taking data for different pre and post selections, and then doing an inverse Fourier transform. But I think about the pseudo distribution generating function as a direct object. And if I put in a complete set of states, I can write also equivalently, I can then make an identification of what this distribution should be quantum mechanically. It's nothing more than the weak valued projector of my operator eigenstates, my outer product eigenstates. Okay. So either way of thinking about it brings you back either to weak values or to this Kirkwood-Dirac pseudo distribution. So this is in the quantum mechanical prediction for what these things should. So here is the experimental proposal. So the idea is we are thinking about encoding the state and the transverse degree of freedom of an optical field. So we have a light source, like laser works. I expand it with a lens. I then imprint the quantum state of this transverse light, for example, with a spatial light modulator or your favorite hologram. That will be the state we're working with. And so then how do we then, that sounds like our pre-selection. How do we do the weak measurement? So the idea is that I'm going to think about using a particular operator. So rather than generically being some operator O, we have the special choice to just be the position operator X, right? And we're going to post-select on some momentum, P, for example. And so what I can do then is, in this case, how would I measure something? So I need to measure something weakly then. I said, remember, I need to measure this parameter e to the I O, right? So now e to the I O, maybe I'll call it lambda here or something other rare, like alpha. This becomes, I need to measure weakly e to the alpha X, the position. How can I do that? Well, that's just a translation, right? what I can do is I can then put a polarization modulation here later on in my field, which is just a sinusoid. And the period of the sinusoid is just that, the inverse of that parameter column. So the idea is, okay, so this has a weak polarization encoding, it's my weak measurement of this global quantity, this e to the I lambda x. And then to do the post-selection, I have another lens that focuses, that brings me out into the, by a Fourier transform property to the momentum space. I have polarization optics here, like a polarizer or polarizing beam splitter, and then I have a single pixel camera that can then do all of the measurement in that basis P. Okay, so that's the idea. So in this way, by scanning the wavelength of this polarization pattern, I can then be able to reconstruct this weak generating function, or characteristic function, Z. Okay. The thing I didn't mention, I'll come back to later, is at this point D, I can optionally put another lens in here, Fourier transform lens, and I'll use that later in the talk. So this is basically a schematic of the experiment Ephraim's trying to build in his laboratory. So the predicted results, so for this particular case, if I have the initial state psi, I post-select on P, now I have e to the I, I'll write it as K x here. We see that's nothing more than a translation operator of the momentum, so I can write this as a ratio of these two quantities. And this is simple now because this is like a momentum space wave function of P minus K over the momentum wave function of P. Okay. According to our prescription I told you about earlier in the talk, once I have this data, I collect this with my experiment. I simply inverse Fourier transform from K to X. And this gives me my predicted quasi distribution. And it's just going to be this quantity here is the prediction, just the weak valued projector on a particular position X. So this is like a momentum space version of collecting everything all at once and then rapidly scanning through the different wavelengths K. Okay, so one interesting thing that we can do with this is we can try then to directly measure the canonical commutation relation in a direct way. So what I can do is I can think about a generalized thing where instead of Z, I have Z tilde. Now I have two operators, my e to the ikx. I have another operator, e to the I lambda p. So with this kind of thing, I can jointly measure moments of both position and momentum. Okay. So if I have this characteristic function, now I have two arguments. I have k and lambda. I can still use my property of Kirkwood-Dirac, so I can write this in terms of a pseudo distribution. Now these are scalars. This is my pseudo distribution Q. Kirkwood-Dirac for position and momentum is just this quantity I showed you at the beginning of the talk, but now I have a pure state psi. I have position x and momentum p on the inside. And I can then imagine if I switch the operator order, I write a different distribution, either k or k tilde, depending on how I do it. If I measure first p, then x, or first x, then p, I have two different pseudo distributions. So here's the cute thing. I can then, with the pseudo distribution, I can calculate the correlation function xp. Now, xp in the pseudo distribution doesn't care if I have an xp or px, but the pseudo distribution, so what I can do in the experiment, if I go back, is I can put this Fourier transform lens here. So I can first go to momentum space and then weakly measure, for example, position here, and go back to momentum, to position, to momentum space. Or vice versa. So depending on if I have the lens there or not, I can reverse the order of the operators. And so that the idea now is that I can think about these two correlation functions, either with the lens in or with the lens out. I can calculate just xp, and then I can subtract. And the prediction is, it's just going to be xp integrated 2I times the imaginary part of this Kirkwood-Dirac distribution or quasi-distribution. And from this expression, it looks completely arbitrary. Like this could be anything, right? There's no rhyme or reason to this at all. But it's easy to see within a few more steps. I can write these things if I put these guys back in terms of the projectors of position and momentum. This is nothing more than either px or xp. Okay. And so we know from the canonical commutation relation, this has to be IH bar no matter what. So we have a universal prediction over any quantum state the difference of these correlation functions has to be IH bar. So it has to be a complex number and a universal complex number. It's not at all obvious at all why this has to be from this equation, but it has to be valid. So we can then for any state, we can then probe directly the canonical commutation relation with this idea. Okay, so that's really all I wanted to tell you, other than the fact, this is related to other experiments. So there's some nice experiments, for example, by Jeff Lundin and collaborators that looked at trying to do direct measurements as a wave function. And the way they did that is with like a little slit of, like a little tiny sliver of birefringent material here. And they sort of scanned it over the profile of the beam. So it's related to those experiments as well. The idea there was to figure out directly what the wave function is using these sort of similar kind of weak value measurements. So that is a connection there.
Is that the equivalent to doing your position measurement in the?
That's right. So that's like a position measurement schema, like, but now ours is like a sort of like a momentum space version.
Except when you have that second lens there, then you went to the position domain, then you could scan that.
Exactly. So then, so that gave you either be in position first and then momentum, or momentum first, then position. Yeah, and so this is one of the topics. I'll give a plug to our Quantum Foundations hub here at Chapman. So this is one area, but we have a number of other topics to work on with Emily and Kelvin, Matt and Kai and so on a variety of Quantum Foundations topics. Okay, so here's my conclusion. So I told you about weak values, the pseudo distribution. And I just want to maybe give a little plug. If you want to learn more about these Kirkwood-Diracts, we have a nice review article written with David and Ephraim and other colleagues. It's now published. This is in New Journal of Physics, the review. This is the paper I just explained for you today. And I also make a little plug for my book, and I'm happy to give copies of my book to visiting members of our conference. So just let me know, and I'm happy to give you a copy. So thanks very much for your attention. I'm happy to do questions.
Thanks, Andrew. Do you have any question? Yeah.
Yes, Vincenzo.
Just you were speaking about how you can retrieve the distribution through Fourier transform. Is that, but that I understood, I want to understand, is that related at all with the fact that you are doing measurements in position and momentum that you go from one space to the Fourier space? How is this connected or is not? Does that depend on the choice of
Yeah, that's a good question. So if I go back to my equation, so you might think it has to do with going between position and momentum. But that's true in this specific case, but it's true more generally. So if I go,
that's what I was thinking.
yeah. So if I go back here, right? So all I have is this. How did I define it? Yeah, so I have any operator here. So you choose your favorite operator. This could be Hamiltonian or angular momentum or whatever you like. This is the conjugate variable. And as long as I have a pseudo distribution representation, I can write that in this form, where now lambda is just the eigenvalues of its continuous operator. And so then once you have that, and you see it's just a Fourier transform. It doesn't have to be position momentum, it can be more general continuous value.
But you need to have an operator and then you have a conjugate value. You need to consider conjugate value.
There's a conjugate variable, yeah.
So it will work with any pair of conjugate observable in a sense.
Yeah, I think that's.
But you need to have that as a condition to have. So it's key to have the conjugate aspect there.
That's right. So the conjugate aspect comes in through essentially the parameter of the generated.
That's right. Yeah.
I can use this to generate moments, right? Or I can then take the inverse Fourier transform to find the pseudo distribution directly.
So I would assume it's more key for the experimental implementation to have conjugate operators, but maybe for the general theory, it seems fairly general.
It's quite general. That's right. I don't have to necessarily have an operator corresponding, or for example, the eigenvalues of chi don't have to be some operator in general. Right? They can just be parameter. It's fine.
Do you have any more? Oh yeah, down on the back first.
Andrew, can you generalize this idea to work, for example, with more variables?
like position, momentum and orbital momentum or whatever?
Sure, yeah. Yeah, so we have some expression in the paper for like doing two, so here I did like one weak value thing, right? Yes, thanks for the question. But you can do the following. So the idea is that I can think about the expectation value e to the I lambda 1 O1, e to the I lambda 2 O2, e to the I lambda n ON, something like that. Right, so that would correspond essentially to measuring correlation functions of the form like O1 to the N1, O2 to the N2, O N to the NN. So that's the more general formulation. So that would be for like an endpoint correlation function. You can define this kind of multi-parameter characteristic function that involves this vector of generated parameters.
Yeah. So I was the whole time I was thinking, oh, this reminds me a lot of Jeff Lundin's work. How do you feel like yours is different, or where are you taking it that hasn't already been done?
Right, that's a good question. So Jeff's motivation was to find the wave function, and he does it by looking at a particular value, like post-selecting on like the p=0 case, and then looking at how that wave function, and then mapping that out. And that's a fine way of doing it. So this is really focusing on this quasi-distribution as a sort of a different object, mathematical object, but then also doing it with this momentum modulation. This gives us sort of another complementary handle, right? And so one thing like with Jeff's work, he has to like scan this little sliver of material through the beam, whereas this can be all done very quickly, like on a SLM, and so you scan over all the momentum very quickly, for example.
Well, they have generalized it to more higher dimensional things as well. But anyway, it like putting spatial light modulators and stuff it was actually an experiment we did, but where we got a billion dimensional state space that looked like the Kirkwood direct distribution. But anyways, it seems very, very similar. And I was just curious. The thing that I thought was really interesting is your ability to like find what your commutation relation is. That seemed really interesting for any set of
Yeah, and I guess the other point is that once you have your pseudo distribution, of course, that allows you to calculate any moment or any observable average you want.
More? Is that I have? Yeah. Sorry.
Questions when you were doing this Vandermoor matrix inversion, in principle, you said that you need n measurements because n is the dimensionality of the space. But maybe one could try like for press sensing, where you have less measurements than you're still able to recover some type of information.
Yeah, that's a good point. Yes. So if you do less than n, then it's an underdetermined set of equations. But you could still do like more Penrose pseudo inverse, right? And then you would get some approximation to that, and you would get like some the optimal in some least squares sense, right? If you do more Penrose pseudo inverse. And so I think there is a connection there. It would be interesting to see practically how many n's you would have to have in order to get a good enough reconstruction of your pseudo distribution. Of course, you can also even do more, but yeah. Yeah, it's a good point. So I think John did some work on compressed sensing with this kind of thing. Right?
Yeah, the interesting thing about that is almost any distribution is sparse in some basis. And so if you have a sparse distribution, then it can be represented by a very highly underdetermined set of measurements. So you probably could represent that very sparsely with very few sets of measurements.
Do you have any more? I have. You need to know the basis.
In which it's sparse.
In which is sparse.
Yeah.
Go ahead, you talk.
I have two questions. Is there one thing related to several previous questions? Is the endpoint function that's generating more? How much to do that? Do you consider the connection cumulative expansion and also that in that endpoint correlation function? It seems to be sort of strongly correlated. That's why in that long time ago, Grammy-Mitchell, that's the work on the cumulative expansion can be simplified as the endpoint weak value.
Yes.
Yeah, that's why in that I thought of that relationship. Did you consider that? This is the one question.
Yeah, so maybe let me start with that one.
Yeah, sorry.
You talk about. And just to say, yeah, so once you have, or at least focus on one, right? So once I have, bless you. This guy.
Yeah.
V, right? So I can think about taking the logarithm,
Yeah.
right, and then taking dd chi.
Yeah, let's see.
Right, so this would be, give me the cumulants of the operator O,
Right.
right, something like that.
Yeah.
And so that's that's a more efficient way of encoding the operator.
Yeah.
It's like removing the disconnected parts of the correlation function.
Yeah. And also that's related to, that's the issue. That's the same to be modular variable as it looks like.
Yeah, so this
That's the,
next to modular.
yeah. That's kind of saying on that your case in that Dirac-Kirkwood in that quasi distribution can be directly measured on modular variable or just much more beyond to be meaning. Oh yeah.
Yes, so I think indeed what I'm using in the formalism there is the fact that because this is a translation operator,
right?
I can use that property of it, which has a connection to these modular variables. So even if I measure in principle all the moments, maybe I'm missing something, right? But the characteristic function captures it. So that's a good point you talked.
Yeah, thank you, son. Okay.
And then you had a second question.
Yeah, that's a second
Oh,
question.
okay.
Yeah, that's
And then I guess you know that it turns out that Haruki, your student, right, was working on a similar.
Yeah.
So we had a kind of a meeting of the minds about that. So it's interesting that independent work was being done on this characteristic function.
Right. Okay, it's all remaining time. Is it let me thanks to the speaker again? Second speaker, Dennis on the border. Yeah. He's talking about how can we add the optical problem? Oh, is that the Chinese title? Theory and the experiment.
Excuse me.
Oh, yeah, sorry. This is. Well. It's okay. Let me start. Yeah. You are ready? Let's start. Yeah.
Thank you very much, Andrew, for inviting me here. It's great to be and meet some people whom I know only through Zoom, like Andy. So I don't know. You guys tell me, do I need to take microphone because I a little bit lost the voice due to some infection from my daughter last week from school? Can you guys hear me back there? Okay. I'm going to present you a work which we have been working on for a long time with my former postdoc, very talented. I owe a lot to him. This work also a lot to him. And yesterday on the news, New Orleans, I'm at Tulane University, which is in New Orleans, here at the campus. And it had a bad publicity, because of the lines, and I was actually for 3.5 hours in the line.
Oh wow!
It was pretty bad.
At the airport?
It was insane. But it's actually it's very interesting. There are interesting things around New Orleans. And first of all, the first stage of the Saturn mission of the rockets were actually built in New Orleans, and there's a plan. And the very same plan right now builds the first stage of the Artemis mission, which should take again people to the moon. The launch has been delayed, but it's there. And also, of course, we have a LIGO nearby. So when I was a postdoc in Princeton, we asked ourselves a question, could we revisit alchemy, but from a kind of quantum angle? In a way, you want to think that alchemy is really solved by quantum, but using nuclear physics, which is a quantum physics.
But it's not very practical and it's too expensive. So we ask ourselves the question, can we make optical properties of one element, say lead, look like gold? So can we only perhaps for some time change the properties of the transiently change the property of the system? So so this actually question is part of the more is equivalent in a way is to ask ourselves, given some system, to which degree you can change input output properties of the system, right? So you have some input field, and then it produces some output, which is, as we know already, it's called polarizability. And if your input field is very weak, then the relationship between input and output is given by this very simple formula. It's a cartoon formula, obviously, many of you know it has convolution. And if I am asking ourselves, how can I make lead look like gold? I'm essentially asking, what should I use as input in order to get the output so that the outputs from two different elements match exactly? And that question has a very simple answer in this case. So here it is. Like if you want to have P of t, given P of t, right, giving output, you just have to divide by chi1, linear response function, and that's what your input has to be driven. So there's a unique one-to-one relationship between input and output. And that means like you take if you want lead to look like gold, you wear yellow glasses, right? And it looks like gold, right? Or shine with the yellow light. So there's nothing interesting here. But of course, it's great if you do spectroscopy, if you do astronomy, that's a good thing, right? There's a one-to-one relationship. But who said that we have to use weak input? You can use principal strong laser fields, and those will start producing very complicated nonlinear responses. In fact, according to Nobel Prize of 2023, it's given for a discovery of higher harmonic generation. This actually polynomial can go to the degrees of like 50, order of 50. So this is extremely high nonlinear responses which exist in nature. And now if you ask a question, what input should I use in order to get the desired output? If you use this hugely complicated perturbation theory, you cannot answer this question. This is just, it's not answerable in any means. So in order to answer this question, we needed to change a perspective. And that's what we did. We actually asked this as a quantum control problem. So in other words, we actually, using perspective, and I will show you a little bit details in a second, but we were able to prove a general statement that under a dipole approximation, that's the only requirement here. And it's a good one as far as experimental situation is concerned. It is always possible to find the input such that for a given system, we get any desired output. So once again, give me output you want, tell me what's in the bottle, I will, under the dipole approximation, will be able to find input that will actually give you the output that you want. Interestingly enough, this problem has been solved for 100 years. It goes under the name of Ehrenfest theorems. It's basically, it's just different interpretation of Ehrenfest theorems. So basically, let me just give you some details. So this is like a sketch of a proof, but it's actually essentially that's the whole story, is that if you have let's say for simplicity, you have this electron, this bottle is a single electron in one dimension, one quantum particle in one dimension given by this Hamiltonian. And under the dipole approximation, the coupling between the field, the control field, and the quantum system is given by this x times e, right? That's the dipole approximation. And now the output, optical output, is actually under dipole approximation is actually given by second derivative, time derivative of expectation value of x. So this is like an acceleration, right? Yeah. And this is where Ehrenfest theorems comes about. If you use this Hamiltonian, you get that this formula, this right-hand side, and E of t is something that you're looking for. The right-hand side is something that you know is given P of t, right? And this part characterizes the bottle, what's in the bottle. So here you go. You can just invert E of t. What you're looking for is equal P of t, what you want, plus this expectation value But it's not quite true because expectation value is done with respect to wave function, and the wave function itself depends on the field. So there is a field implicitly here as well. But that's not the problem. We just take this E of t and replace it here, and we end up by having a nonlinear Schrodinger equation, which actually has, which always has a solution. So you solve nonlinear Schrodinger equation. So Schrodinger equation itself finds the field that it needs based on what you want it to produce at the end. And once you solve it, that's it. You go back to this equation and you calculate the input that you need to apply. So this is how it works. It's very, very straightforward. And the key here is that this solution always exists. It's always possible to do this procedure under dipole approximation. Maybe there are questions about this so far. So this is a universal property, right? So here's a simple illustration. Okay, sorry. So simple illustration, 3 very different systems, 3 very different inputs, but they all produce identical outputs. This is back in our original paper where we use a single kind of effective electron approximation to do these simulations. By the way, this trick also works if you even have classical system or classical or quantum system, doesn't matter. It's true for any dynamical system. So you can make classical run look like quantum and quantum look like classical, as long as you have ability to modulate the inputs. It doesn't really matter. Later on, we actually looked at many body systems, and we took as a paradigmatic model of a one-dimensional Fermi-Hubbard system. It's a very nice model from a theoretician point of view. It has only 2 free parameters. It's just a kind of chain of sites where electrons can move around the sites, and they move around with a kinetic energy T0, and when they are on the same sites, they undergo electron repulsion. These are if U is comparable to T0, basically Coulomb repulsion is comparable to T0. It's actually it's a very interesting phenomena. It's a strongly correlated system. Actually, it's a very strongly correlated system. Whereas if U is 0, it's a kind of traditional metal, simple metal. So in this case, photo-driven property is rather photo-induced electric current, right? The current that you induce. And we were able to prove exactly the same universal statement there as well. So here's an example illustration. We have a metal. Let's start with here. We have an insulator, insulator. It's called Mott insulator, the strongly correlated system. We shine a simple transform limited pulse on it. Theoretically, of course, we shine. When you get a highly nonlinear response, very highly nonlinear. It's a very high harmonic generation process. And these nonlinearities are precisely signatures of electron-electron interactions, strong correlations. And now we use the algorithm along the lines I showed you before to actually pre-calculate the input that you need to shine on the metal such that it exactly produces the same current as the insulator. And you may notice that they are actually, the input looks the same as the output pretty much, the shape-wise. And it's true because this algorithm really discovered the fact that metals are perfect mirrors. So you can, it's a literally perfect mirror. So it's nice to see that it does something reasonable. But in a different illustration, we did the opposite. We actually took a simple transform into pulse, shine on a metal, also produce harmonics. You can see some extra wiggling happening. And now we ask ourselves, what is the input pulse should be used such that insulator makes the same current. It has a very non-trivial shape, and unfortunately, there's no any more interpretation what that shape, why that shape is. So once this work was published, we were pleased to see that there was a public coverage of this work received, and in particular, Ido Kaminer actually brought this opinion piece about our work. Basically said, look, not only you can make something look like something else, but rather you can create something exotic. You can take, a pulse and take a common material like a rabbit or wolf and make a unicorn, right? So in one of this media actually made an animation. I like this animation. Take a rabbit and make it. It's actually unicorn. It's not very obvious, but if you see carefully like this, it has a hole. Unfortunately, they don't show you this. Like they just make it, and you cannot. There's no editorial kind of feedback. So So we decided to exactly like this. Let's just create something that doesn't exist, like doesn't exist. But before that, we actually were extended our thinking and discovered something absolutely amazing about nonlinear optics, overlook phenomenon, and we call it twinning fields. My postdoc called twinning fields. So I would like to once again remind you that up to now I was having two different materials, two different inputs, but they were making the same output, right? So two different inputs with two different materials, the same. The same is here. Two different inputs, two different materials, but the same output. But it turns out that you can do even more. There is a class of inputs and outputs such that for two different systems use the same input and it exactly produces the same output. And this is not a, sorry?
How is that possible?
Yeah, no, it's insane, right? It's possible. We can show it. It's very easily. Basically, yeah, it's a nonlinear response. It's also a nonlinear response. It's not a trivial fact. And frankly, this is a, yeah, like I myself want to study more because this was shocking. And this is a fact is, I think we're nice to show it experimentally. Actually, I have some ideas about this, but again, the same input, the same response for two different systems. In fact, for like if you have a lattice system, you can prove that it always exists in 1D, in 2D. It's also like there's some technical conditions, but it's basically also. So it's a very and it's not a single it's not a single pair. This is the whole point. It's a class. It's an infinitely large class of systems of input-output relations.
May I ask you?
Yeah.
Question? My apologies. I was in the lab coming back. So how did you treat the system? Did you treat it classically, or you say there is a nonlinear regime? Did you treat it classically or semi-classically?
No. This is fully quantum treatment.
Okay.
The quantum system is fully quantum. The input is a classical field, and output is an expectation value of the current. Okay. It's fully quantum. It's a cold quantum theory.
How sensitive is this choice to specific values? Is it like a fixed point of some iteration? How do you get this?
No, it's a good question. So this is the way you get this is you take one system, for example, this one, and you sort of push out of equilibrium a little bit. Like how much? Like it depends of how much you want. We push out of equilibrium, and then the way you calculate these pairs is that you solve a couple system of nonlinear Schrödinger equations. So it's very easy. It's not iteration. It's just like you solve it once. That's it. You get the answers. And this pair depends on the way how far you're from equilibrium. The more you are from the equilibrium, the more crazy the input-output pairs looks like.
Actually, equilibrium source, fixed points of some iteration.
Probably you can reinterpret this as a fixed point. Of course, you can there's no doubt about this. But the point is that it doesn't require that, right? In terms of computations, it's just a initial value problem for two couple Schrödinger equations. Yeah.
Do you have any ability to control either the input or output so that you get kind of a nice, well-behaved signal?
This is a great question. So not in the way we phrase the problem in the paper, but probably but basically not in the way it's phrased originally. That's like whatever is given. But if you phrase it some kind of optimization problem, that's where probably iteration scheme is needed. We could probably have them in a more decent shape.
Can I ask one more thing? Yeah. This is, of course, very nonlinear. It's too much to ask, but is there any reversibility underlying this?
It's a good question, reversibility. I mean, in some sense, it tells you that it's not reversible, that by knowing input-output pairs, you cannot recover what's inside uniquely, right? I think that's like a kind of counterexample. Right?
Yeah.
So
meaning if you turn the time arrow the other way.
In that sense. No, it's fully because it's a Schrödinger equation.
It's fully.
Yeah.
So then you can, in the previous setting, you can feed the same output to the two systems and get the corresponding input that if you feed back, you get the same output. Or is it not?
No, because you change the Schrödinger equation effectively, right? You're basically solving two different Schrödinger equations, time dependent.
Okay. Thank you.
So if I think about this correctly, are you basically saying each one of them have a different set of chi's? Like you have chi1, chi3, chi5, and each one of them have a unique set of chi's for each one of those systems. And therefore you can find a system that satisfies a set of coefficients that satisfies both types of materials.
So the chi's are fixed, but the field is the one that we are allowed to change, right? And the output. So we're asking.
But the chi's are different. They'd have to be different.
Yeah, they're different because they're different materials. Yeah. Of course, it's the same as trivial. And yeah, you shine. If the systems are the same, of course, they produce the.
So there could be an infinite family of.
Yeah, that's the exists infinite large family. And of course, if it were only single pair, that's kind of experimentally, pointless, like needle in a haystack. But this is precisely why it's interesting, is that it's an infinite family. So there's more to nonlinear optics than meets the eye, meets the perturbation theory kind of argument, right? We did it nonlinearly precisely to show the referees that this works even in a crazy nonlinear settings, like with strongly interacting systems.
You assume that this time response is limited it goes from minus infinity to infinity.
No, it's a finite time.
It's a finite time. Okay, so this is how it explains.
Yeah, it's a finite time.
Because if you go from minus infinity, it can never be the same.
Minus infinity to
infinity. You cannot not have two materials with different coefficients.
So you can do it from zero, like on a half infinity line, like from starting from 0 to plus infinity. that's you can do that.
The thing, you cannot have different polynomial coefficients, and then it will get the same response for every time. So the reason it works is just because you limited your time window.
Because I can get, as long as my interval can be infinitely long, but not from, like, it has to start from 0 to plus infinity. But not from minus
maybe
infinity
it
to
can be like semi-infinite.
Yeah, semi-infinite. Yeah, that's the maximum we can do is semi-infinite.
It's possible.
No, from minus infinity to infinity.
Minus infinity.
No, it doesn't matter that it's non-linear.
It has to have at least semi-in, or like finite or semi.
For minus infinity, you cannot have two functions with different polynomial coefficients that are.
Yeah, that's true.
It's impossible. It's not related to nonlinear optics, no.
But yeah.
It's just mathematics.
It's basically kind of dynamical systems. But it's still optics. So another interesting aspect is that we can start driving superconductivity, actually. So here's the joint work, collaborators' recent work, where we kind of tip our toes in this area, where it turns out that if you take a strongly correlated system, kind of Fermi Hubbard type of system, and you have a monochromatic pump, this is just kind of amplitude versus frequency, and you do different simulations. So this is order parameter. This is how for certain values of frequencies and amplitudes you see that you bring order parameter above 0. Unfortunately, once you turn off the pump or like turn it off smoothly, you actually order parameter becomes very, very small. But if you kind of combine the pump plus a version of what we do, or which is known as Lyapunov control, where you sort of try to find an input that your order parameter is not decreasing. That's the idea. It's not decreasing. Then it turns out you can actually maintain and drastically more enhance the order parameter. And now you can do even opposite. Here we start from a normal state, bring it to superconductivity, but you can do opposite. You can actually start with a superconductor and bring it down to normal. So you can have a photo switch. We can turn on, turn off superconductivity at desire. So this is another interesting aspect. Another application that we looked at is the fact that what I just showed you, that for any output, there is input that drives this output. In a way, it tells you that nonlinear optic has enough computational power to be Turing equivalent. So what does Turing equivalent means? It means a Turing machine, current digital electronics, right? It has this property that if you have a correct input, which is the data plus software, right? You can produce arbitrary result, and it's always, digital machine is always works like this. You have some impulse coming in, and it transforms it to the output pulses. But this is exactly what I just told you. Like in nonlinear optics, you have the same power. Give me the correct input, and I will produce arbitrary output. And that motivated us to think about using a single nonlinear optical element, and the single nonlinear means like actually taking a single atom, because atom is already a very nonlinear system. And you're able to show that it has enough computational power to do meaningful computations. What's interesting about that is that in this way, you don't like try to make optical transistors and then integrate them, because that's very bad. Optical transistors don't work because photons don't like each other. They don't like to do nonlinear interactions. But in this way, each single one nonlinear element already does enough calculations. And this work was followed up by Manfred Blake's group, and they call it ultra-fast intelligence, because ultra-fast artificial intelligence, because in principle you can have it at petahertz speeds, basically, if you do an optical domain. So that was the theory part, and now a couple of experiments. So this is actually the experiment was done by the Thomas Alsazer group at Max Born Institute in Berlin, and the idea was to actually turn water into alcohol. So this is the actual experiment. So these three liquids, isopropanol, this is like alcohol or glycol. This is alcohol is glycol. Isopropanol is like antifreeze, and water. They have a common property that they're all polar liquids, meaning that the molecules of the liquids have permanent dipole moment. So what happens is that if you are able to ionize a molecule, one of those molecules, then just a single ion will be enough, because the free electron will interact with these dipoles and rearrange dipoles drastically, and you will have a kind of a quasi-particle polaron, which is this is a solid state analog to this type of particles, and that polaron totally dictates optical properties of this liquid in a terahertz regime. So what the experiment does is that it performs 7-photon ionization using infrared laser light to ionize liquids, and the only parameter you need to just have enough of those polarons. In other words, you have to basically just do amplitude shaping of your pump infrared pulse, and then you use terahertz a probe that actually measures the electric, in this case, the electric permittivity as a function of frequency. It gets measured, and here's the result. So first of all, here's the electric function as a function of frequency. If for normal liquids without any pump pulse, right? So this is 3 different measurements, and you can see very different properties. You can easily distinguish between these 3 liquids. But then if you adjust correctly the infrared pulse, then this is what you can get. This is what you can get. You can basically make them, you can prove that you can make them the same at a single frequency and approach each other at different frequencies. So this is actually first experimental, implementation of proposal made 2,000 years ago. So, but there is more to this. Look at this. The electric constant reaches 0. Of course, that's, as we heard in the morning, is epsilon near 0 material. And immediately, we follow up with that. So first of all, I mean, Bob did already the job of introducing, so I'm not going to introduce. But enough, you can start thinking about creating epsilon near 0 material as a kind of a quantum control problem in itself. So here, the idea is that you actually take a boring material, because water, is boring material. It's not nothing exotic, not like idiot, not some meta surface, etc., and you just correctly drive it, right? And epsilon 0 in this sense is like your input and output should basically have 0 phase delay, right? And that you can claim that you actually dynamically created epsilon near 0 material in this bottle, and. And here's the experiment using isopropanol in the same lab of Thomas Alsazer. And here's I will just be quick here and say that here's so there's a terahertz pulse in blue light going through vacuum, no liquid. So this is how it looks like, this terahertz probe, right? Then what we do, what Thomas's student does is he turns on a liquid jet of isopropanol, and you can see that, and he measures it's a black curve, and you can see that there is a delay between black and blue curve because right, the phase velocity of light in liquid is slower than the vacuum, right? So that's why it arrives later in time. Does it make sense? Like it arrives later, right? Now, we turn on the palm pulse, the infrared palm pulse, and what happens is that you can see that this is a red curve. These are experimental plots. The red suddenly starts arriving earlier than the black one, right? And it's actually not cool, but you may say, okay, but that's okay. Like it's earlier, but it's not more early than the blue, than the vacuum, right? It's not even, it's not like phase delay is zero. There is some phase delay. It's smaller than the black, but it's not zero. But then we have to be careful because this blue curve is a very short pulse, right? It only has 3 cycles. So it has a huge bandwidth. So we have to now be careful, look at the frequencies that make this pulse. And if you do a Fourier transform, you see this is it spans 3 terahertz, this pulse. And now if you analyze the refractive index or epsilon, you can see that for some basically, so these are different concentration of the polarons, which means like different palm pulse. So let's look at the blue data. So it's what happens is that you sort of make material have 0 refractive index for a very broad range from 0.5 to 2 terahertz. But then after this cutoff, it becomes a normal material. Whereas your original pulse spans the entire spectrum. So only half of your frequencies corresponds to n equals to 0, whereas the other half are just normal material. So if you, and this is already shocking, like the ordinary liquid became an epsilon near 0 material for this extremely wide range, right? And you can, again, this cutoff can be controlled at will. Moreover, another advantage, interesting advantage, because we're not bound by Kramer-Scoring relationship, is that imaginary part is being very tiny, actually kept being tiny. So what we do is now we actually take and separate, we do low pass filter, apply Fourier transform, and separate the low pass frequencies and to look, here they are. This is this pulse, low pass, after pass through low pass. And this is it. This is really, there is 0 phase delay between red and blue. So it's literally for these bandwidth, these frequencies have no phase delay between input and output incident light. And now if you look at the high pass part where N is, like a normal liquid, then you can still see that, yes, that's like that arrives as a normal, it behaves like a normal liquid. Red pulse comes after the blue pulse. Kind of closer to the black, but this is a dynamically shaped epsilon near 0 response. Maybe there are questions. So this is really shows that you can create a smart material like a meta material to do some things and use this like a dumb light, right? Or you can try to create a smart light but use a dumb material, right? So this is what we are trying to do: is to create a smart light to use dumb material. And also, my nearly last slide is that recently we have been looking at the fact. So this drawback to all this research is that you need to be able to do pulse shaping, right? You need to be able to create an input light of sometimes extremely crazy, insane complexity, right? So is it possible to do it without any shaping? And it turns out that theoretically, yes. As I said, all you need is amplifier. So the system itself can calculate the pulses, synthesize the pulses it needs to achieve alchemy. So here's an example, a system You just use optical input of transform limited input. Let's say this metal produces some harmonics, that you would like to insulate or to match. The way you can achieve is that simply make a copy of this output and make a phase delay by minus, basically subtract, find a difference of two inputs, and then pass through an amplifier, and then combine the amplified difference with the input to insulator. You can prove for very different system that as long as the amplification is high enough, the outputs will coincide. So in other words, the system will literally find the pulse itself. So all you need is amplifier. Like you don't need pulse shaping. You need of course, sometimes amplifier will need to be broadband. That's another problem. But in principle, there's a different, more like active way of replacing this alchemy than passive. And I see the chair is already pushing me out. And
No pushing out, no pushing out.
So yeah, so we have by looking at nonlinear optics as a kind of quantum control problem through the quantum control prism, right? We were able to discover interesting new optical phenomena, and that we like to study. I also didn't mention if you're able to manipulate the responses of the system, you could also have a more advanced spectroscopy techniques tailored for mixture characterizations. If you have some complex mixture of chemicals and you would like to characterize them efficiently, you can. That also gives you an advantage. And now, guys, I'm going to ask you a question. What was before the periodic table of? What was before the periodic table? Does anyone know? It's not a real periodic table, but you guys.
Before periodic table,
Yeah, what was before the periodic table?
we believe in 4 elements, that's it.
Yeah, no, I also thought that was the case, but
Wind, fire.
but apparently, before chemistry, there was alchemy, right?
Yeah.
And alchemists, they were already doing tables. They were trying to already organize, elements and compounds and try to classify. So this is a table of affinities. This is literally the table from Galileo Museum in Florence. This is, you can find them many places. That's like I don't remember.
1,000 or something like that.
So no, it's recent, like it's 1700s, like what? Yeah, it's like basically it's this transition where there was like already, like alchemy was there, but people were doing it more for science. They still were using these weird notations. There's, by the way, a very interesting story of chemical notation, how it got from this to like proper to modern notations. It took like a French and American Revolution to do that. It's Lavoisier actually was the one who abolished this.
I think it goes back to the Islamic Golden Age.
Oh.
So at that time, they believed in alchemia, essentially.
Yeah, no.
And they do that.
So there is a very good book, by the way, on the history of chemistry. So every civilization had its own version of alchemy, interesting enough. Yes, so this is true. And so the European tradition of alchemy is closely related to Islamic because this is where they got this, as long as Aristotle, the classical period. But this is we're talking about late alchemy. Like this is already kind of almost the end of it, right? It's more science than, and by that alchemy is in a way that has to be viewed as it's a merger of the way I like learn about it is that it's not some kind of people were cheating trying to make. They were trying to. So before alchemy, there was basically like crafts, right? Crafts and some professions, right? And there was a philosophy. They were disconnected. So alchemy was basically the idea of how to bring crafts and philosophy together. So it's a first step towards real science, right? Where philosophy is sort of theory and crafts are sort of experiments, and this is like attempt to somehow synthesize different skills together. But you probably already know that there is some interesting. And it means lead. Actually, it means lead in the yeah, right. That's interesting enough. Also in astrology, it also denotes Saturn. which is also amazing. I like it because, right, we know that quantum effects exist on all scales, not just small, right? There are quantum effects on a scale of the universe, so this is nice. So, of course, this letter exists in several European alphabets, like Maltese alphabet. Also, Hebrew has, I believe, something very similar to this character. But actually, I don't know personally who actually brought it to quantum mechanics. It's very clearly that Dirac consistently used it throughout his work. But before him, people like used h divided by 2 pi, h divided by 2 pi. Even Bohr famously has these pages of discussion about measurement problem, and he uses h over 2 pi, h over 2 pi. But Dirac actually is the one officially that I don't know. So maybe somebody could clarify the last point. But Dirac definitely consistently used it throughout. So that's it. Thank you, guys.
I have one question and maybe I can contribute to this debate. So in my country, apocryphal story is that it is introduced by Einstein via his wife, who was Serbian, and this is Serbian literature.
Oh, really?
We don't buy this Dirac thing.
No, I just
But now seriously, if I understood correctly, this method of mapping input to the same output, kind of fixed point, does it works for different classes of operators? Because you actually give us one with different parameters.
So it works for, we can talk about this in more details, but basically it's not just for, there's a class of operators, it works always. Other cases you have to study, there's a class for which you can make generic statements. The other ones you have to study case by case example.
Can you show back the feedback? Yeah. So the way I see it here is like the lower part is some sort of a reference tracking system.
Oh yeah, it's a proportional controller. Yes.
But the stability is not guaranteed because if you have very high gain, it's not necessarily stable. Like the input to the insulator would not be exactly the signal you're putting in. In principle, for example, if the signal, the unshaped transform, doesn't even go through, you just cut it off.
So are you saying like if you're in the high gain limit where you're turning over, or where you don't have to be in the linear gain?
First of all, the stability, because this is a feedback loop at the bottom, could be non-trivial.
Oh, it's not trivial, very much non-trivial. We showed in 2 cases analyzed that it works, but in other, may not work.
Then the other thing is that the input to the insulator may not be exactly the signal, the unshaped transform that you're putting in. The amplifier is going to have some response.
Here would not be, yes.
Not be that.
It will be complicated. Yes.
Yeah, it would be completely different. Yes. In fact, there's not even need to feed the unshaped transform down there below.
No, you still need it. It's a good question. I think you still need it.
Still, it's a reference tracking system. You just put.
The metal has nothing to do with the insulator principle.
Yeah.
So why should the unshaped transform have to go into the insulator?
It's a good question. I think we still need it for analysis somehow. It's a really good question. I think it would be good to have it because usually this is bright, so we want in practice this to be weak.
I mean, this
is like this delivers power and this delivers bandwidth, basically.
If the dynamics of metal and insulator are more or less okay in some regime, then putting it will reduce the effort.
Yeah. This is exactly what this is. Yeah.
But other than that,
but I think yes, for now, no, it's so this scheme does work for these examples that I showed before in open loop control. So I'm just saying that look, this can be wrapped as a closed loop, and you don't even need to have a shaper.
So you wrote the relation between polarization and electric field as a scalar, but in most materials this is a tensor.
Yeah.
Right? Can you really take the entire all the parameters of this tensor, or this is just one for
Yeah, you can do this.
linear approximation?
I had some hidden slides, but basically I'll tell you that you can, then you need to, but also you need to be able to explore also polarization in your input light. No, you cannot just have a linear polarization. Yeah, if you allow to change input field correspondingly, then yes, you can do more.
Yeah, but you will have many, but even if it's just, you just consider the linear response, you already have 9 terms, right? And now you go to higher non-linearity, so the number of terms that you need to.
No, but that's why we look at through this non-perturbative way, right? So we treat this non-linearity as a dynamic problem, not as a perturbation series expansion. So it still works, but again, you need to be able to. Assumption is that you have to be able to control field.
Yeah, I mean that it will not help you the fact that it's because the response is different for every set of input polarization.
No, it does help. So I have this example where we took 2D Haber system isotropic, and we draw it such a way that it looked like insulator in X direction and metal in the Y direction. Right? So this is like extreme example of how you can create extreme anisotropy, the same, to the system.
Yeah, so I want to understand what is really the significant difference between this system and the platform that people they use it with ENZs. So essentially, are you familiar with the work of Nader and Guitar? So if we assuming that you want to do any computations, any wavefront that you want to generate, okay, let's put it in this way. You want to take a derivative of the wavefront that you are giving it. So he will come up with an inverse problem, and he will give you the structure of the metamaterials with, insulator, whatever you need to do. So it will imprint that, and of course, as soon as you go with a pump, you will get such an output as a beam. Okay, so there is a way of engineering rather than going with one unique materials. You can go with a design one. Okay, so can you link the two together?
Yeah, no. First of all, the Nadar's work is basically very important. We do engineering by part. The computation part is done on the probe. So that's the difference, right?
So essentially, you shape the pump.
Yeah. Yes.
Okay.
That's the difference. And then you can do probe whatever you want to do, but you need to shape the pump.
So essentially, shaping the pump creates non-locally, or let's say a specific distribution which they are non-linear, that allows you to modify the probing. Okay.
But as I like to say, like we take a dumb material, right, liquid, and use smart light, right, rather than smart material, right?
Okay, so yeah, so sorry, time is up. Sorry, we have a more question during the coffee break or more day to do. Let me time to speak again. Next session started. 2 minutes break or just a break? 10 minutes, okay, on time to do.
Dennis, very interesting. I really like that. And I've wondered, so when it's epsilon near 0, then you're just sending the terahertz pulse afterward.
Yeah.
And how absorbent is that inside of the water?
Zoom. Yeah.
Because typically water is very absorbing, right?
Yeah, exactly. This is not the normal one.
Click on it.
See, yeah. You're gonna.
Did you send it?
It's right here. There's a Zoom.
It's the imaginary part where you can see that.
Yeah, but
it's really incredible. So
it's not normal water. That's the point. After 10 picosecond, it will become normal water.
So then you put a low pass filter on there to get whatever that is on your bandwidth.
Yeah.
And then the particles as if the water were even there.
Yeah.
So, does the prevent violation of causality? I assume the low pass filter then also spreads out the pulse so that you still have parts of the pulse that are at the front end. So,
It's unbounded, it's time unbounded.
okay,
You can even see it from here. This is nicely time bounded, right?
Yeah.
It's clearly unbounded.
I see. Okay, so
And
low
also
pass
amplitude
filter.
amplitude is it's only phase. Amplitude is, you can see black and red are very, blue and red are very different amplitudes.
Interesting.
Yeah, so unfortunately, causality.
You don't violate causality very easily.
Fortunately.
I mean, it'd be lovely if you did, but, yeah, it's pretty tricky to get.
Yeah, it's exactly, it's always finds a way to.
Right, interesting. That's very, very intriguing.
Is it Dennis or Denny or?
Dennis, just Dennis.
So I did not realize that you were, he had mentioned it and I just didn't connect the dots, but that you were Jared McCall's previous postdoc advisor.
Yeah,
He
yeah.
was here not too long ago and we met him in Faro last year, or 2 summers ago, yeah. Yeah, he's a very nice guy. It's a lot of conversations. So he's one of the only people I know who sort of is bold enough to say that he thinks Shor's algorithm is proof that we have not discovered the classical algorithm that will do it better. And that quantum computing is just a big boondoggle. That's a bold.
That's a strong claim.
It is.
But you know what's funny? 5 years ago, you can basically read the same sentence even in Wikipedia.
You could what?
Wikipedia about Shor's algorithm. It was somebody like deleted that sentence and said that they actually do not know. It's unknown whether it's in P class.
Yeah, yeah.
And somebody deleted it, actually. It was on the first part.
It was too harmful to quantum computing, so that has to go. Okay.
Yeah, it's, but look, there's so many examples that we asked for a few years where people come up with that. And then months later, right?
Yeah.
But I know it's great. It's not bad.
No, it's a good thing, but yeah, if you do ultimately prove that, all of this effort to build quantum chips and processors was a waste of time, then that will be that'll be a tough pill to swallow. It'll be funny, that's for sure. I mean, it'll make me feel a little bit like vindicated that I have the option to go into real quantum computation or foundation than I really chose foundation.
No, but I'm much more pessimistic. Let's say
yeah.
Problem is the cost.
It's never going to be worthwhile for us to build this.
Like the cost of is insane.
Yeah. Well, maybe eventually we'll have room temperature superconductors we can do with. Who knows? Seems like
but it's
yeah. I mean, it's not super. It's not the only reason.
That is separate problem, right? Yeah. It's not even longer than
Yeah.
computers.
Well, let's see. But there are some systems that work at pretty high temperature, right? Like the diamond and decenters turn out to be kind of useless for addressing and controlling the qubits, but they're very stable, right? Yeah, that's what I mean. Yeah.
Stable.
It's a single qubit.
Well, that's always the
There's-
trade-off.
Yeah, that's the fact. Yeah.
So it's a cooling. It's cost of cooling. I mean, I don't know whether you ever seen quantum machines.
Yeah, I've seen the refrigerators that are required.
I mean, it's insane. It's like
yeah.
Wow, they don't show it. They show you this nice little.
It's inside this gigantic refrigerator. Yeah.
Like a fridge inside the fridge inside. It's like five fridges basically. It's just,
So do you think this means that if we can do it and there are better algorithms and we figure out how to scale it, it still will never be worth doing it?
no, I think it's a question of cost.
Yeah. Yeah, I guess
What the algorithm.
it's right. If it does solve some
Something
truly
really
miraculous,
yeah.
we don't know that algorithm yet, though.
But that's another thing people looked at. Quantum chemists, they looked at nice paper called Quantum House Concepts by real quantum chemists. Not by quantum information science person who is developing. No, so it's like because people say, oh, use quantum simulators for doing that. It shows that the accuracy that you need to achieve is like like the current quantum code. Like the accuracy for chemistry is like 6 digits.
Okay. And they know we're close. Yeah.
The errors are.
I haven't looked in a little while. I mean, there is there's there's a scale at which you can do a lot with error correction, right? Like once we can get, good enough qubits.
No, but that's different, that's, I'm different.
Yeah, it's true, you need a
No,
lot.
no, but that's the whole point, to do simulations, so that you do error correction on our, doing, you can actually build circuits, yeah.
Oh, you're talking about like annealing.
Yeah.
Sorry,
Yeah.
okay, yeah, okay.
And we're actually physically, for chemically interesting.
Trying to directly simulate a chemical
Yeah,
reaction.
it's just like accuracy in which parameters needed, just insane.
I've never really worked on this stuff before, but it's funny because we have a physical chemist here who hosts some of these talks. He's commented on the number of plots. It's like, you never get data that looks that good. It's like, you guys have like a line of points on the line. Like, nothing looks that good. So, yeah, good standards.
But do you have that, is it some kind of story somewhere about this vibe?
It's a people. I mean, nobody. Well, yeah.
No, it's a legend, but it's written somewhere because it would be nice to cite.
You should be very careful.
Yeah, I know.
Nowadays, there are movies, plays, dramas about neglected wife. See, she was talented, but I have never read proper historical work on this. This is like small caveat, historians trying to get big problems solved. So I'm not sure, but it is very popular. And if you read secondary documents, which are actually based on plays and novels, you can be fooled. So, I mean, journalist articles are not reliable. And we are not sure because we don't have numerous papers. We don't have anything that you can unambiguously prove that it is her contribution. You see? So that we can be really sure. But when you see this kind of thing, it can be Serbian or Romanian. There is no third.
No, this one, like this couple of
Yeah.
No, it's a.
And there are for example, crucial evidence is that Einstein donated half of his Nobel Prize to her. Now, like one obvious interpretation is to help her taking care of the sons. One boy was ill. It's very expensive to have constant care. But if you want to interpret it, it is like he has guilty conscience and he is like bad in mathematics, we know this. And what we have some evidence that she was very talented mathematician. And people in Serbia say, obviously, this guy cannot do tensor calculus, this requirement for general relativity to, to formulate it properly, because we already have this kind of anecdote that Hilbert immediately wrote down a relativistic invariant, Lagrangian, and he was struggling with it, you see. But this is not proper.
I mean, history is hard to do.
You need to have historians willing to devote his time, but I am also educated in physics. Fine. I don't know if these writings of those collaborators, their friends, properly processed. I'm not aware. I mean, classified according to laws of history. It's not hearsay, real data, tracked. At specific time, you see, if you write down something in your journal, but you wrote it like 1 year in the future, it's not properly related to something. I mean, to track it really, not to be hearsay. This is not the work which nobody wants to pay.
What's the point of
It's probably.
Yes, but if you're a historian.
This is a little bit that order,
Maybe on that trace.
Should put on that exam.
There's, I need to know, maybe at some point ask some, is there people
The gallery,
I didn't read anybody.
Side by side.
I also like regional.
Much better.
Easy.
So easy. No, you're fine.
We think what to do with it.
I think it's about time to start.
But I like the story. Wow, that'd be nice. Yeah.
Oh, yeah? Okay. I think I got it.
I'll ask him later. He could give me an introduction,
Right.
whatever it was.
That's
I-
Log into the.
So they.
I see that. I was asking, maybe I thought it was a character. No, just a Zoom code and.
But wait a second, what is that?
Those places like she's that.
Oh, is it not coming up on the Zoom?
No, that is, I think,
Wait a minute, why was told to go on Zoom?
I saw the big bug.
Oh, maybe there are options.
yes,
Yeah, no, I'm hearing it on Zoom, but it's also.
Oh, okay, so there are two things.
Yeah.
Okay, so this is for local audience, this is Zoom.
That's for people who might
Okay.
not.
Well,
hear.
oh, why are not they doing Zoom themselves?
Okay, please take our seats. We're gonna have a last talk of the day.
too complicated.
Okay, so I'm happy to introduce the last speaker of the session. We have our very own Alice Quillen from the University of Rochester. She is an astronomer by training, but recently she's converted to a quantum person. We're so excited to have one of her first quantum talks here at the Institute. So Alice.
A quantum astronomer.
Over to you.
And we already did the Alice and Bob. Just in case. Yeah, I'm going to talk about connections between classical and quantum complexity, and have way too many topics here. So I'm going to talk about iterators, and iterators are settings where you can get, you can see chaotic behavior and you can see period doubling route to chaos. So I'll ask a general question: what kind of cool iterators can you make that are work on quantum systems? And then I'll look at classical systems that are connected to quantum systems so you can compare them in detail. And in the classical setting, we have tools that let us predict, not just that, let us predict chaos, not just say it's chaotic and then we're done. Actually determine where it is, how strong it is, what the timescales are. And so I was curious about the quantum equivalence, and so I'll talk about a quantum equivalent using the periodically perturbed pendulum model. And that turned out to work really well since we know how to make that system very uniformly chaotic, it turned out to be very straightforward to make a quantum sampler out of that, which is a way of sampling over UN in a uniform way according to the Haar distribution. So that's this particular thing. What I want to talk about is notions of adiabatic drift. In the classical setting, there's this notion of adiabatic resonance capture, and that can be important. Like if you drive a planet to high eccentricity, could cause the planet to hit something. So there is a quantum equivalent for that. And then there's an additional parameter having to do with energy level spacings. So that's also kind of a rich setting to look at quantum classical correspondence. So here's a system that's based on an iterator. So dynamical system is when you start off with a function and you just keep applying the function over and over again. And so the logistic map, x to the n plus 1 is the n plus 1th iteration of this particular map. And it has this nice phenomenology where if you vary the control parameter, you go through these different types of behavior. And so what's actually shown here is if you iterate, you tend to attract to a particular orbit. And here all the points, no matter where you start x, as long as you stay between 0 and 1, you'll attract to a fixed point, and here you'll attract to a periodic point, so it's a 2-cycle. And then there's this, period doubling out to chaotic regions. So it's a nice rich map, but all it is based on this function. So
one thing, like we can put functions on a quantum computer, but this one's not invertible, so it's got this terminology. And one thing to keep in mind is after you iterate it, when you're converging onto one of these either fixed point or periodic behavior or chaotic behavior, you're losing information. And that's related to the shape of this. So depending upon which side of a half on, once you iterate the map, you don't necessarily know which side you were on. And so there's one bit of information removed each time you iterate this map. And that is related.
Because it's not invertible?
Yeah.
That's why?
Yeah. But you can actually quantitatively say how much information is lost. It's one bit of information per iteration. So, right, so let's make a comparison between the classical world and the quantum world. So a lot of the discussion on quantum computers has to do with unitary transformations. So people talk about the number of operations that you need with a gate set to converge onto a particular desired unitary operator. But unitary operators also, you know, display scrambling. So they're not all simple, but they are invertible. Or you can think of them as rotations. So that's what you would see in the quantum world. In the classic world, we have dissipative dynamics, which can give us these attracting fixed points and loss of information. You can also have chaotic behavior, and you definitely don't need invertible functions. But one thing to notice about the classical world is a lot of problems that we want to solve involve classical operations. So if you want to optimize, you want to converge to a particular solution. And so all quantum algorithms on quantum computers actually lie in this hybrid region where you need to both do measurement and then adjust your algorithm based on what you measure. Other settings where you actually want to do hybrid types of simulations are when you're trying to mimic open quantum systems, or you're trying to use decoherence to say, put your system in an interesting state. Quantum error correction is also hybrid because you're taking into account errors and you want to get rid of whatever error happened in your system. So you could record the error and then do a transformation based on what you got. You don't really care what error you got, but you do need to reset the bit afterwards. Otherwise, you'll propagate the error. So hybrids also live in this hybrid. Quantum error correction also lives in this hybrid regime. So we were asking what kind of more general iterator can we make based on just a function of a discrete set? So a quantum computer can be thought of, if you number the number of states, it could be a discrete thing unless you're working in a chemical or an optical setting. But a discrete, so what are the class of iterators that you can construct from a discrete set? And the way that people code those is with what's called a quantum oracle. And so this little black box here is part of what's called black box components in quantum oracle query type problems, algorithm problems, where the goal is to minimize the number of queries you're doing as a measure of computational complexity. So here, there's the quantum oracle. It's invertible because if you have an input which can be register and another input, you record the same input on the output. And so that lets you make a unitary transformation independent of whether the function f of x is invertible. And if y is 0, then what you get out is f of x. But if you want to iterate it, you want to put x back in. And so all you do is swap and then make sure you start with 0. So y always starts with 0. So this is a very easy way to make an iterator. And you can construct it with this bunch of functions. You can describe it as a quantum channel because the reset isn't a unitary transformation. So it's maybe nice to think about iterators you can make with reset operations, because anybody who's building a quantum computer can put it in a particular state, and they work on making that possible. And so resets, you can't really do quantum calculations without a reset function. So you can think of this as quick and efficient and accurate in many settings. So this is the channel that you get, and essentially it traces out the A degree of freedom because you're removing that amount of information. So the logistic map, you can definitely put on this make a quantum oracle that does this function. If the function itself is on the unit interval, but if we truncate it so that you can put it in fractions, binary fractions, then depending upon what n is, you get various versions of the logistic map. And so these are just truncated versions of it. And so this is a quantum channel. So for every discrete function, we make a quantum channel out of this iterator that can be iterated, and you can look at the properties of the quantum channel. And this channel converges to fixed points, or it has cycles. You can look at the complexity of what happens because you're putting it on a finite dimensional thing instead of an infinite dimensional thing. And the properties of the channels, the channel itself is a linear operator. It has eigenvectors, but they can be generalized eigenvectors. So the structure of this graph, which tells you when you iterate, where do you go? And so here you can see they're all attracting to 63 and then going in this cycle. The cycle itself tells you that it has eigenvalues and eigenvectors, eigenvalues of roots of unity. You get fixed points, which you wouldn't get in the true logistic map. So that's an artifact of the putting it on a discrete system. And if you had large n, it would be a pretty good approximation to the logistic map. So we were trying to think of, well, could this actually ever be useful? So we realized that part of Shor's factoring algorithm is the Euclidean algorithm for greatest common denominator, which is really old. It's from 300 BC. And so we're like, yeah, let's make an iterator that can do this on a quantum computer. So this is it. It's not very complicated. Just amusing to think they were like, what's the oldest algorithm you can put on a quantum computer? Okay, so in this particular setting, we're just iterating a number, and the number is based on the number of states. So what does it do if you put in a mixed state? And the channel is dephasing, so it acts essentially classically because we're removing a lot of information with the reset. I put the reset on this side. So there's a lot of information being lost there. But depending upon what discrete function you use, you don't have to remove n bits of information if you have n bits that you're using for your function. So, so you can divide your function space into disjoint sets where each set is got a unique map. And so that gives you a much bigger class of channels. And so the number of channels that you can make that are like this is more than just the number of discrete functions. It's the number of discrete functions and all the different ways you can partition them into disjoint sets. And when we were looking at this, we realized that error correction is essentially in this class. So if you keep things in disjoint sets, you don't touch the quantum information in each disjoint set. It's protected. And that's exactly what you want when you do error correction, is you want to record, you want to fix errors that flip you from one subspace to another subspace. So each of these subspaces is one of our discrete sets. And then you design your functions so that it just maps them all into your encoding space. So, so this particular class of channels includes error correction. So we asked, well, is there a continuous generalization? And there is. I'm not sure how easy it would be to implement on anything, but the logistic map itself, when I mentioned there's 1 bit of information lost, I can just take this line, and those are those would give me 2 maps. And from that, I can construct a map that in the context that would give me an iterator that would give the logistic map, but in this quantum setting where I'm losing 1 bit of information every time you iterate the map, or iterate the channel in this case. So to summarize, it's a class of quantum iterators that are not unitary. It displays interesting phenomena like cycles and period doubling. It has complexity in terms of combinatorics because there's a large number of iterators. They're not very complicated channels in the sense that their eigenvalues are either roots of unity or 0, or their generalized eigenvalues. And so it's a nice setting if you want to explore classification of computational complexity in hybrid classical quantum world. And they include channels that would maintain coherence in subspaces. Okay, so I'm going to change a little bit, move on to chaos now. So yeah, so the logistic map shows you one route to chaos, which is this period doubling route. Another route to chaos has to do with the pendulum and what happens at the separatrix orbit of a pendulum. So what I'm showing you here is a phase space picture. So we have momentum versus angle, and this is a fixed point in phase space, and that corresponds to like the pendulum hanging down and not moving. And then these orbits are librating orbits, so those would be the pendulum swinging back and forth. And then these orbits are the circulating orbits where the pendulum does this. And then there's this point here, it's also a fixed point, but it's unstable. And that's the pendulum being upside down. So it would exponentially move away from that point. But that hyperbolic fixed point is connected to a particular orbit called the separatrix, which has an infinite period. And that's the orbit that goes chaotic when you perturb the pendulum. Yeah, so the first thing I was, looking at the pendulum, it's phase versus momentum, but momentum can go to infinity, and that's inconvenient if you want to turn it into a matrix that you can diagonalize on a computer. So I was like, let's make this finite dimensional. So I moved the pendulum onto the torus, and the model, the Hamiltonian model for that is called the Harper model. And so in the limit of small p, you get back p squared over 2, which is kinetic energy. So it looks just like the pendulum, but it's doubly periodic in both this direction and that direction. And so you can think about it as like being on a donut, it's a torus. So in hindsight, like I picked the Harper model because it's close to the pendulum. I knew the pendulum really well. But you can do this on a spin system too. And so if you have JZ squared and JX perturbations, you'll get something that looks kind of like this on a sphere. If phase space on a sphere. And then people who are used to working with spins are happier, including my collaborators. Okay, so here's the Harper model unperturbed, and then I can add a periodic perturbation. Here I've added 2 terms, kind of gives it a symmetry. So these are, tau is a time it's sinusoidal in time. And I put it in units of the perturbation frequency here. And so this is the unperturbed system. Once you perturb it, you get this. And so what's being plotted, and I'm plotting orbits every time they go back at the period. So it's called the Poincare map. And the orbits that remain not chaotic look like lines. And the orbits that they change their dimension, they start filling up an area. And you can see that the separatrix, which is here, went chaotic. And this particular problem actually has 2 separatrices. There's one here and one here. So there are 2 regions that went chaotic in the system. So there's a technique for estimating the size of that chaotic region in classical setting. And it's called Melnikov's method. And the idea is you look at the trajectory that hits the hyperbolic fixed point. And then, so you have a trajectory that goes to the hyperbolic fixed point and a trajectory that comes from the hyperbolic fixed point. And if they cross, then because the map is area preserving, you have to cross an infinite number of times. And so what is this trajectory? If I take the separatrix orbit and then I integrate the perturbation along it, that tells me how far it went. And so if you figure out how far it went when they crossed, that gives you an estimate for the width of the chaotic region. And so this is actually pretty, it's very good to order of magnitude. It's not great past that, but it's been widely used to predict the onset of chaos throughout celestial mechanics. And so it's been enormously successful at matching a lot of numerical studies. So the idea to use it to derive a criteria for onset of chaos is from a famous paper by Chirikov in '79. He actually did all the work earlier, but this paper also had the standard map in it. So it was very influential. So let's go back and forth from the classical to quantum world. So notions of chaos, it's in the classical world, everybody's used to what we mean when we say chaotic. You get sensitivity to initial conditions. So orbits exponentially diverge, and the speed that they diverge is described by the Lyapunov exponent. You can discuss the properties of an ergodic system where it's in a chaotic region. It behaves as if it's stochastic, even though it's deterministic. And then there's all this other phenomena that lets you, like recurrence and mixing and numbers of periodic orbits and orbits filling phase space. In the quantum world, some people are familiar with these conjectures that say that if I have a classical chaotic system, and it's not chaotic, that their eigenvalue spectrum will be Poisson-like. And if it is chaotic, they will be Wigner-like. And so there's this idea that the statistics of eigenvalues will depend upon whether the related classical system is chaotic or not. There are other notions. So one of them is hypersensitivity to perturbation. So the idea is that a quantum system that's chaotic should, if I varied a parameter describing it, or if I perturbed it, it would be extremely sensitive. And then lastly, there's this idea that in the semi-classical limit, eigenstates fill phase space. And so that's rigorously defined by Schwerelmann. Okay, so I take our Harper model, and we'll just turn all these things into operators. So what's P? So P is just the Fourier transform of phi. So this would seem ad hoc, except that you can actually do this by Bohr-Sommerfeld or Weil quantization. You get the same thing. So, so it's straightforward to go from classical to quantum. And the flow K, so since it's a periodic system with perturbation, what we're actually computing is a flow K propagator, which is based on the time-ordered Hamiltonian evolution. So this is a classical system, this is the quantum system. And what am I showing? I'm showing, take the flow K propagator, find all the eigenstates, and then plot Husimi functions for each eigenstate, showing phase space. And so the idea is that all the orbits here look like eigenstates, but as plotted as Husimi functions. And what you can see here is in the chaotic regions, the Husimi functions start looking fluffy. And this is this view that Schnirelmann had where eigenstates start to spread out. And particularly if you go to high N, you would see they're even fluffier. So one of the hardest things was we diagonalized the propagators. How do I match classical orbits to the quantum eigenstates? And it turned out that the unperturbed Hamiltonian gives you a way to do that. So this shows you another, perturbed system, but the reason they're all in this nice order is because I computed the expectation value of the unperturbed Hamiltonian, and I also computed the dispersion of that. And these are ordered in order of that. So they're ordered in terms of energy expectation value for the eigenstates. And that'll turn out to be important later. So this shows you classical orbits in terms of this expectation value for the classical orbit. So a classical orbit, I can make a bunch of points, and I can also compute the expectation value. And I can also compute the dispersions. And so it really lets you match, here are the dispersions, it really lets you match the classical orbits to the quantum eigenstates of the propagator. And in particular, you see the quantum states that are chaotic, which have that feathery appearance, they have high dispersions in terms of the expectation value. So here's another way of looking at the system. If you look at the transition probabilities between the eigenstates of the propagator and the Hamiltonian that's unperturbed, you see the chaotic region just looks really different than the non-chaotic region. You get this, very localized spreading. And this is a particular chaotic region where I keep increasing the number of states, so it's classical limit. And this shows you that idea of Schrödinger that chaos is related to this fluffiness and the high end limit. Okay, so I mentioned the dispersion of the Hamiltonian. There's this nice classical quantum correspondence, but Melnikov's integral, which lets you estimate the width of the chaotic region, is basically using this integrating the perturbation along the separatrix orbit. So, so the quantum equivalent looks like this. And so quantum equivalent involves looking at finding the eigenstate of the unperturbed system with the energy nearest the separatrix, and then computing the energy change from the sum of all the eigenstates near it. And so I derived this by using a Magnus expansion in the interaction picture. It's the first order term in the Magnus expansion that actually gave something that worked. So it's kind of like averaging over the perturbation, and the eigenstates that contribute are the ones near the separatrix. Yeah, so why is delta H the relevant thing? So it turns out the delta H is related to the, if you in the flow, when you look at the Floquet propagator, you can describe it as an effective Hamiltonian. That's the unperturbed Hamiltonian plus a perturbation. And you can describe that perturbation in terms of this. So this is the way you can relate those two and get a size scale for how big the scatter is in the energy near the separatrix. So we have a quantum counterpart that lets us estimate where a system is chaotic. This is a little bit different than these notions where classical systems that are chaotic will have different eigenvalue distributions, because we have actually a hybrid system. It's chaotic in one place and not chaotic in another place. And in those settings, they don't obey the Wigner distribution the way these very thoroughly chaotic systems do. Okay, so to summarize, the Harper model on the torus is a nice compact system for exploring this relationship between quantum chaotic and classical chaotic systems. And we were able to match up orbits with eigenstates of the Floquet propagator and relate them together by taking expectation values of the unperturbed energy. So that's this measure of ergodicity in both of these systems. And we derived a quantum counterpart to a predictive classical formula for estimating the width of a chaotic region. So this shows you this idea where regular gives you the energy. So this is the spacing distribution of eigenstates for the Floquet propagator. And there's a lot of nearby states, so it's not exactly Poisson. The reason it's not Poisson is these things are nearly degenerate, but we didn't know that with our first paper. But then if you have a highly chaotic system here, then you get this Wigner distribution. So, so we were first motivated by this question: if energy levels repel, so this Wigner distribution, it doesn't have very many eigenstates close together. So if they repel each other, then perhaps driving a system chaotic would help us do adiabatic quantum computation. And so, so we were curious about drifting these chaotic systems. But it turned out that when we drifted them, we found out that the transition probability distribution was essentially independent of the drift rate, which means that they were energy level crossings at all distances. And so that means that, you know, chaotic systems are probably not great for doing adiabatic computing. So, but when we noticed that, we were looking at this thing going, that's an exponential distribution. So it's a Porter-Thomas distribution, which is implying that we're seeing behavior as if the system is uniformly distributed in the space of unitary operators. So we shifted and decided to go see if we could use our system to make a quantum sample. So that's what I will describe. So this, so the idea, so this is the idea. Classical setting, you've got this Lyapunov exponent, which tells you if I have two initial conditions, they diverge. Instead, I can say, well, let me figure out what the Lyapunov exponent depends on. I'll find that control parameter. I'll vary that control parameter, but I can start with two initial conditions that are the same, and I'll still get exponential divergence. And then if I now quantize the system, this will give me a propagator that's extremely sensitive to a control parameter. And so if I take a distribution of control parameters, I'll now get a distribution of unitary operators. And then the idea is then they would cover UN uniformly. So that was the idea. And so why is this different? So most quantum samplers got a lot of publicity because they were used to demonstrate quantum advantage. The way they were generated is with a quantum random circuit. So this is an example of a quantum random circuit where you have locally randomly chosen operators interspersed with entanglement operators. And you don't need you need logarithmically numbers of depth here to create something that's pretty uniformly distributed. And there's a bunch of recent applications, state characterization, which is also called shadow, shadow trajectories. I can't remember the name of that. It's been very influential in the last few years. So instead of doing this, we're going to create a completely different kind of sampler because we're leveraging a chaotic system. So our first thing was we don't want islands because islands are not chaotic. So the trick to that turns out to be have your perturbation be slightly adiabatic. And that's got to do with the maps that are generated near the separations. So I knew that from celestial mechanics, but it's not obvious. Right? So you want to be on this side, you don't want to be on that side. So we knew how to do that. And then we just have to add enough parameters that if we sample over them, we'll cover UN for whatever N is. So I picked, we have these two perturbation strengths. I can shift momentum, shift phase, and shift the perturbation phase. So that's the recipe: distribution of parameters, distribution of unitaries. So we need a way to measure, do we have a good sampler? So what we do is we make a series of samples and then we compute this statistical quantity called a frame potential, where you just take trace UV dagger to some power. And then if this is average over your distribution for all pairs, if this thing matches what you predict for a unitary, then you say it's a K design. And if it's close, you say it's an approximate K design. So we're generating things numerically, so we can't prove that they're exact. In the random quantum circuit class, they can prove they're exact. So we're just numerically seeing. So at best, if we make a few hundred samples, we'll say they're approximate because we just have measurement errors. Or they're not measurement errors, the numerical errors based on the sample size. So this is number of control parameters and which ones we varied. And these are the frame potentials, and the red dots are the hard random unitary values. And so if we're up here, then we have a bad sampler. And if we're down there, we have a good sampler. And so our samplers are all really good. But the amazing thing to notice is we only needed to vary 3 or 4 parameters in a space that's like way, way bigger. So, if we're using 50 or something, then UN is 50 squared big, and we're only varying 3 or 4 parameters. So you don't need very many. These were only for one Floquet period. So it's not even Floquet. I mean, you wouldn't even call something that's one period long periodic. But we're varying something very quickly and getting a sampler. So the recipe, choose 2 angles. So that lets us rotate. And so you can, we can actually evaluate what the frame potentials would be for that setting where you do what's called twirling over the Heisenberg-Weil group. But it doesn't get you anywhere near a good sampler. So you need also so these are rotations, essentially they just conjugate so they don't change the eigenvalue distribution. So you need something that changes the eigenvalue distribution also. So the 2 parameters that change the Lyapunov exponents in the classical system take care of that problem, and the resulting sampler is a 3 design. So as far as we measured. Okay, so this is it shows that you can do it on a sphere, which Mikhail Bloch really wants us to do, so they can make a sampler on their quantum system. So maybe we'll try that later this year. So to summarize, we identified a chaotic system that has a broad ergodic region. We made a distribution of unitaries using distributions. We used both sensitive and rotational control parameters to do that. And we quantitatively described how good they were by calculating frame potentials. So this is really fast. And it's an analog method, so it's different than other samples. So since we can make samplers, we can just view them as a solved problem. We can start putting them in our circuits. So that's what I'll talk about now. So on the theme of iterators, which I talked at the beginning, what if you take the famous Aharonov random walk, which is a Hadamard coin flip on a system that's like the James Cumming model. You can describe it like this. People who like quantum computing like symbols. So it's a Hadamard with a controlled shift to the right, a controlled shift to the left, depending upon whether it's spin up or spin down. And there's interference. So if you start in a state where it's like it's localized at one particular position, there's interference that makes it spread out really fast. And so it gives you this ballistic spreading. So people use this in search algorithms. So we're going to replace the Hadamard with a random matrix and see what happens. So this thing is now a random matrix in U2. And but I'm making it an iterator. So I didn't find anybody. People talk about stochastic random walks, but they don't actually mean you choose a different random matrix every time. So what we're doing is every single time we apply the iterator, we choose a different random matrix. And so the reason for using a Haar uniform distribution is people have calculated their moments. And if you make sure you're choosing a different one every time, then you can just compute the moments. And so in this particular case, the expectation value for all overall random matrices is just the identity matrix. So the channel you get, if you average the channel, is a depolarization channel. And so even though when you compute it, it's deterministic in the sense that you're just applying a unitary operator over and over again, you always have a pure state, but the average is described by the classical coin flip walk. So you recover the classical coin flip walk from this. So I just wanted to kind of connect in classical quantum, only random walks with random matrices. So yeah, what else did we try? We tried an interacting spin chain. And this one, I have Heisenberg interactions. So these are two-state systems. And then we perturb one of them with a Haar random matrix. And then we reset the bottom bit. And so this is like infinite temperature because we're just flipping it around. It keeps resetting it to the ground state. And then because everything's interacting, what happens is if you keep applying this channel, there's a relaxation period of time based on the strength of the interactions, and then you end up with this steady state where the expectation value of the steady state is what you would get if you averaged a channel. So we can compute the average channel again. Again, it's depolarizing the first bit, which is this Haar random part. That's the reset. Those are the interactions. So this thing acts like it has a temperature gradient, and it has fluctuations. So I'm not sure if this is useful or not, but it does have this nice, cool property. It would be pretty straightforward to simulate. So a little bit more for phenomenology, this relaxation, these are the distributions of the polarizations of each bit. So this is another way to look at the idea that we have a temperature gradient in our system. If you view the expectation value of the polarization as a temperature diagnostic. And you can adjust these, so it's very controllable in terms of if you have slightly lopsided interactions, or you have changed the length of the chain. If the chain is bigger, then the fluctuations are smaller. So there's a lot of potential controls over the system if you wanted to highly correlated quasi-thermal system with a gradient in it. Lots of ways you could just deceive to get what you want. So to summarize, we have a class of stochastic quantum iterators that are generalizations of quantum random walks. They have random matrix components, which help with computing expectation values. The average channel depolarizes, even if the operation itself is completely unitary. And stochastic quantum channels mimic open systems in the sense that they can show thermal gradients and fluctuations. And they're actually more general than collision models, and the average channel is a collision model in that particular case, if anybody's used to collision models. Okay, so I'll just say thank you, and this is our many collaborators, so thank you.
Thank you, Alice. Questions? Yutaka.
I have a question about the quantum Harper model. I have a question about the quantum perturbative Harper model. Would you go back to them?
Can't catch what word you're going to say.
The Harper model.
Oh, the Harper model. Oh,
Harper model.
thanks. What about the Harper model? You want to go back to the Harper model?
Yeah, that's the my question is.
That's the Harper model.
Yeah, actually.
Yeah, here it is. There's the Harper model.
That one is you show that this is the latest slide in that sort of Thomas Porter model. Thomas Porter distribution. You can see.
Oh, right. When it's chaotic, we get the Thomas. Yes, that's
exactly. Yeah, this is a quasi-periodic thing. That's normally this is a Harper model is a quasi-periodic structure on this potential. But normally we don't see on any chaotic system, but that the cases on the chaotic one.
Yeah, we added a perturbation.
Yeah. That's why. That's what I want to ask you. It's normally it's a truly chaotic system. Why is that converged to Thomas Porter model?
Oh yeah.
Yeah, Thomas Porter distribution. This is based on the random matrix model. Then that's why it's a purely random cases. No such kind of quasi-periodic structure should be disappear on that in that infinite cases. That's why that's what I'm asking.
So when I take the Harper model, and I derive it quite a bit, then I get a very uniformly filled chaotic region in the classical model. If I make Husimi functions for a model that looks like this, all of the Husimi functions are spread out over all of phase space.
Yeah.
So that means that it's highly mixing, and so there's you can compute many statistics describing how scrambled it is.
Yeah.
And one of them is just looking at the transition probabilities, and that's the one that I showed you that's exponential. But there's also inverse participation ratios and a bunch of other statistical things. So those are for single operator. Then that's not a sampler. It's telling you that it's scrambling. But if I then vary parameters describing it, then I wind up with so instead of computing, so the Porter-Thomas, if I took a random matrix times a state, I can actually use the Luxworks. So if I have some state, a random matrix, and the same state, this winds up having an exponential distribution.
Yeah.
So we were just computing these and making frame potentials, which was equivalent to doing Porter-Thomas. But so I didn't make Porter-Thomas, we did put one in a paper, but we mainly based how well are we doing based on the frame potentials. But the individual operators, the transition matrices, also look Porter-Thomas, and that's because they're very good at scrambling. And so that's what I showed you. But when we saw that, we were like, we're seeing a Porter-Thomas distribution, we may be able to leverage our system to make a chaotic, to make a quantum sampler. You see the difference? There's subtleties in how you're creating something that looks exponential.
Okay. Is this analytically showing converge to that Thomas Porter distribution in the e-finance system?
For us, there's no analytical.
Just only the numerical evidence.
Right, so we didn't find any analytical tools that would predict a Porter-Thomas distribution.
Okay.
But when you see a classical system looks like that and the Husimi functions are all spread out, it's not surprising that you're seeing an exponential distribution in the transition probabilities of the single matrix.
I see.
Okay.
Okay, thank you.
Yeah, I mean, in the high end limit, we would recover that, right? So which is, but there is structure in this actually. And we can tell that they're not exactly, they're not the same as a randomly generated matrix. So I can generate a hard random matrix.
Yeah.
And then I can compare its behavior. And there were distinct differences in the statistics of things like inverse participation ratios and the moments of the transition probabilities. So that's why we needed these tricks with the rotation helped get rid of that problem.
Yeah.
I think Ibrahim, you had a question?
Yeah, so I really regret that I didn't talk about the programmable quantum simulators that we had.
Oh, okay.
Because two examples that you mentioned, we just simulated and the paper just got out last week.
Oh,
right.
okay.
So we simulated the quantum walks or the dynamics on a torus. So it's really an experiment. You program it, it goes and look at the dynamics of electrons in a lattice of up to you will tell me 500. And then I look at the time discrete quantities of that, how the electron evolves in that system, which is exactly the slide that you had it and you showed the Wigner functions for the Floki system. So I'm a little bit puzzled there. When you look at that P and phi, if I remember well, you look at different energies there, right?
Yes.
What is happening with the Bloch vector? Do you know what is happening with the energy relationship? Let's call it the group velocity.
I have no idea. Yeah, you have to explain to me what you want.
So,
but maybe later.
We can talk about it. I can show it to you, and even beyond this, what happens when I give you an entangled system?
Oh, to start with what?
To give it to this chaotic system that you have it. Look at the evolution of them.
Oh, so I start with an initial state that's.
What you start with is a product state.
Oh yeah, okay. So you're not the Harper model, you're talking about the spin?
Just talking about the cases of the torus, the walk.
Okay, yeah, so that's just an n-dimensional system. So I mean, when you say entangled, I need at least a bar.
I will give you two particles.
Yeah, so how do I fit them in there somehow? So how do I relate my n-dimensional thing to your entangled system?
We can talk about
it. Yeah. So I would need a proposal on how to do that. Yeah, I mean, with the quantum random walk, which has a hard random component, I start with an entangled state. It doesn't really matter because it relaxes. And so with the open quantum system simulation, it will lose its.
But even with the quantum walk, even on the lattice, if you go with
not if it has a hard random perturber in it.
If you go with entangled state, depends on the kind of entanglement, then you will get a new kind of Bloch oscillations.
That would be true but I think it would not be true if you had a hard random perturbation involved. Then you would lose memory. Okay. So for the generic random walk, like the Aharonov one, it's very dependent upon what you start with. If I start with it, I could get it to all go in one direction. For example, it's very lopsided.
That one directional that you mentioned, this is what we call it the group velocity.
Yeah.
So essentially, the Bloch vector is assigned such a way the wave function is evolving, either with the dispersion, so without dispersion, or it will be on the two sides, so in one other way. So yeah, we can discuss.
But our walks with hard random components, because it's as if it's being perturbed with noise. I mean, So it loses all memory. You can still go into a very correlated state, but it loses all memory of whatever you started with. It's an attracting channel with perturbations around the attracting channel. So any quantum channel that's attracting loses initial condition. Okay, yeah, we should talk about.
Yes.
Okay, other questions? I had a question about your, when you were doing the logistic map on the quantum machine, you had this formula with the two Krauss operators. Can you show that again? I just was curious about that.
That's how you write you can use operator sum decomposition to write those channels if you want. So this is I mean, that's one. So basically, if you're iterating, you can describe it with Krauss operators that.
Yeah, can you show me the one you had like the integral over the position? Do you remember?
Oh, this one.
Yeah, yes.
Yeah,
So this was interesting to me.
Yeah.
Yeah.
I put this up as a curiosity because it was like.
Yes. So my question is, can I think about this like measuring if the particle is on like the left side or the right side of the?
That's right, because you're
of the
removing
thing.
that amount of information. That's it.
So basically to implement this, and so I would look, is the particle left or right, but then I would forget because but then you want to average over both of
Yeah,
those.
that's right.
Okay.
And that way, that makes it possible to make a channel,
Okay, cool.
quantum channel.
That was very interesting.
Yeah, I put that in as an example just because it was like weird. We didn't know what to do with it.
Yes, so I have a paper with my students from a few years ago where we're looking at trying to show chaos of the quantum state if you continuously measure it. So maybe it's related, it could be related to this. So let's discuss that.
Oh, cool. Yeah.
Yeah.
Yeah, cool.
Okay, any other questions? All right, let's thank Alice for a nice talk. And now true quantum person, right?
Go, Alice.
Can you
I can
tell
tell.
I have a classical mechanics background? Yes, you can, you can.
All right, so we have time just for informal discussion now, and then the dinner is at 5:30 at Culinary Dropout. So if you want to walk with us, we'll kind of assemble as a group here, maybe around 5:10, and then leave around 5:15. You want to go together, or if you can meet there on your own, either way. All right, so thank you all for this nice first day.
Thank you.
Thank you, Andrew. The big boss.
Andrew, question.
Yes, sir.
You had offered me a copy of your book.
Yes.
But I already have a copy. What I really like is a PDF copy, if it's available. Because that way I have one at home and one with me over there.
Okay. I can't give away PDF copies. There's one on, you can get it through, there's an ebook version on Cambridge, the website. I hear from my students that there are some pirated copies floating around the internet as well.
I will get a copy sometime.
Okay, all right. I'll try to direct you.
And the U of R library sometimes says copy. It says it's available.
It's all about like.
Check it out. Depending how it's set up. The easiest way is to get a higher copy for me. That's by the way, my policy is anybody who's ever wants to any of the editions of the book. And second must go free to them.
Okay.
That's just, of course, that's strictly illegal. That's how I.
I think, so I can certainly give you a PDF just from my source file. That's what you would like.
That's fine. Yeah.
Okay, yeah, that's fine. It won't have the nice the Cambridge logo and so on.
You have my book?
I don't think I do.
Send it to you.
Okay, I would love that.
No, I will send it to you. I will just send it to you. It has nothing to do with reciprocity.
Okay.
I'm going to send it to you. You do what you want to do.
I'll be very happy to study it.
On the back of the. Okay, I know the place.
Lovely, yeah. There's a little present for you.
Thank you. But that's the thought is
Perfect.
ID, right for.
Yes.
Yeah, it's about 10 minutes, 15 minutes of walk.
Yeah, okay, nice. Dinner? Well, you're very welcome. We have plenty of.
It's a pity that some
Very good.
big plans they couldn't make it, so it was short notice.
Yeah. So who accept left? Who other than that?
He couldn't make it. Oh, we sent you photos.
Those ones. I see.
Well, the force that they experience is the quantum potential, so that the shape of the quantum potential creates a barrier for them. Yeah. I don't know.
So I'll send this I mean,
And are we leaving from here or?
It's like around 5:10.
5:10, something like that. Okay.
Yes. Yeah.
I will tell you.
Oh, thank you. It does not belong there, does it? You have something to show me?
You mean
They never touch the walls.
The book, yes.
But if you.
I'm told.
I'd like you to do that.
So many things on it.
Very good. Of course.